He has expertise in pharmacoinformatics, quantum medicinal chemistry, synthetic chemistry, computational chemistry, and several other fields. He got several awards and honors, including Fellowship of Indian Academy of Sciences, Fellowship of Andhra Pradesh Academy of Sciences, OPPI Scientist Award, Ranbaxy Research Award, Chemical Research Society of India Medal, Fellow of Royal Society of Chemistry, London, IBM Faculty Award, and several other research and several other awards and fellowships. He has a vast experience, and 1985 onwards, he is working on a different projects. He has more than 20 years of teaching experience. He was Dean in Naipur Mohali from 2016 to 2018 and Associate Dean from 2015 to 2016. He is Head Department of Medicinal Chemistry as well as Department of Pharmacoinformatics. He has a very high impact publication record. He has published more than 250 research papers in medicinal chemistry related journals and several other high impact international journals. They are cited more than 5,000 times, and he has H index of 35. Welcome, Professor PV Bharatam, and now you can start the talk. Thanks for coming.
Good morning, everybody in this particular conference. Today is a festival day in Andhra Pradesh, in Bengal, in Punjab, and many places. It is called Lodi in Punjab. It is called Bhogi in Andhra Pradesh. In Tamil Nadu also it is a festival. Happy festival, but happy studying, happy learning. My talk is on the topic of metabolism and toxicity. We are discussing about molecular modeling as one of the fundamental sciences. My address you already know. As far as the topic of toxicity is concerned, toxicity and metabolism, there are several topics. Mechanism-based inhibition is one of the important ones. This particular process starts in our body, in the liver mostly. There are several enzymes called cytochromes. These enzymes cause metabolism and toxicity. Why? They don't cause toxicity themselves. The chemicals which are produced due to the metabolism probably are leading to toxicity. The enzymes do their job. Enzymes are natural. What is their job? Is to consider anything which is extra and get it out. Xenobiotics. Xenobiotics are excess to our body. Anything we don't want are xenobiotics. Any chemical species. If we supply a drug, we don't want drugs. Our body does not want drugs. It considers the drug as an external chemical species, which is an unwanted species. Food is okay. Food is, our body accepts food and it is metabolized. Food is metabolized and food is converted into smaller chemical species. In this process, CC bonds are broken. And then eventually the whole energy is created. That is what is responsible for life. Now, if the chemicals like those chemicals which have got large hydrophobicity are not wanted. So the enzymes called cytochromes, they act on those compounds which have got hydrophobic functional groups and convert them into hydrophilic functional groups, such that once this is hydrophilic, it can be excreted very easily. Once it is excreted, which is okay, because we don't want. Drugs are species which are not wanted by human body naturally, but unnaturally we want, because some of the reactions which got cropped up unnecessarily, we have to be stopped. That is, some enzymatic action is giving imbalance in our body. That imbalance, to stop that imbalance, we supply external chemical species, and body considers those external chemical species as unwanted species. Cytochromes convert those unwanted species into excretable species. So that is the main purpose. It is a natural thing. Cytochromes are required enzymes. However, sometimes we don't want the cytochromes to function very efficiently. So we supply a larger quantity of the drug such that we can overcome the rate at which the drug is getting converted into the metabolite, but the excess amount of the drug has to reach the site where we want it to act. Anyway, this is naturally happening in the body. Sometimes we want to prevent cytochromes to act. We want to inhibit the cytochromes. Sometimes we want cytochromes to produce better, improved activity, induced activity. Inhibition of the activity as well as in induction of the activity, both we want from cytochromes depending on the situation. So that means we have to understand the action of cytochromes, how they are acting. So for that reason, we need to explore these enzymes in detail. One more reason is that these cytochromes, when they perform action, they produce the excretable particles, but sometimes they may produce reactive metabolites. These reactive metabolites can be safe, can be dangerous. If they are safe, we are happy, we will be having no difficulty. But if this cytochromes produce a set of reactive metabolites which are unwantedly acting, which are acting extra in our body, that can lead to toxicity. So we want to understand what are the reactive metabolites and how to ensure that they are not produced, how to prevent their formation. Very beginning, at the time of designing the drug itself, we may prevent the formation. We may create such a functional groups, such an environment in the drug molecule, such that it shows the pharmacological activity, but it does not produce the necessary metabolite, these dangerous metabolites. So we need to understand the mechanism of cytochromes. Cytochromes are many varieties. They are called cytochromes P450. There are at least 18 families of genes which are responsible for the generation of 43 subfamilies of enzymes. After including all the members of the subfamily, there are at least 250 highly recognized cytochromes. Out of that, a few are very dangerous. Very dangerous means very easily acting on the drugs. Many are there which act on food. Many will act on some other internal processes. But a few enzymes, a few cytochromes are specifically acting on drug molecules. They are cytochrome 3A4 is one of the very important cytochromes which is responsible for a drug metabolism. And it's okay as long as it is producing not reactive metabolites. It is okay even if the reactive metabolite is safe. Only when the reactive metabolite happens to be not safe, we have to become concerned. That is why we are trying to understand it very well. The action of cytochromes can be drawn like this. The cytochrome cycle, this is what they call. Cytochromes have got a catalytic center like this, as it is shown here in the very first step. Iron porphyrin center, which is supported with the help of cysteine, sulfur iron bond is there, and then iron porphyrin ring is there, and then that center is attached to water. That is perfectly safe, neutral, the unreactive state of the cytochrome. But when a drug comes into picture, a substrate comes into picture, then water goes out and substrate goes in. Inside the substrate, there is a CH bond, which is mostly hydrophobic in nature. Because of the environment of the cytochromes, the hydrophobic center of the drug is pointed towards the metallic center. And then there is a CH bond. That CH bond gets oxidized. This is the entire chemistry that is happening inside the site of cytochromes. That is called site of metabolism. Site of metabolism is generally hydrophobic in nature. So that hydrophobic center, the metallic catalytic center actually absorbs an electron, then accepts oxygen, then accepts another electron, then accepts H plus. Finally, it gives rise to a FeOOH, a peroxide type of system, and that peroxide system gets broken. OH radical goes out, and FeO radical is generated. This is a radical species. That means it has got one unpaired electron. This center with unpaired electron is very active, and at that state the iron metal carries oxidation state 4. In this environment, there is a possibility that the oxygen which is attached to metal can be transferred to the CH bond, and then CH bond becomes a COH bond. Any compound with COH bond is more hydrophilic, and then it can be excreted easily. You can see that product is with COH. Substrate is with CH, product is COH. So that is the actual entire reaction that is happening. And this, if we can understand this in more detail, if we can understand it in 3 dimensions, we are going to be successful in getting atomic level details. Atomic level details, molecular level details, and electronic level details. These are very crucial for our research work in cytochromes. Electrons. Which electron? You see this is very first step in the entire catalytic process is absorption of electron. Another step is absorption of another electron. That means 2 electrons are consumed by cytochrome. Okay, and then oxygen is utilized. Then the reactivity happens and a radical species is generated. That is also having 1 electron excess. This is all electronic in nature. If we want to understand the details at the electronic level, we need to solve Schrodinger wave equation. To solve the Schrodinger wave equation, I need to have the 3D structure of the enzyme and the 3D structure of the substrate. So if I think in 3 dimensions, I will be a successful person. If I think in 2 dimensions, it is of no use. So this diagram is a 2D diagram. So let us go to more details. Now what happens inside the cavity of a cytochrome? There is a catalytic center. You can see that is written in pink color. There is a process happening. This is churning out. Lots of processes are happening inside the cavity. These are the catalytic processes. These catalytic processes can lead to, for example, it can convert alcohol. It can convert an alkane into an alcohol, or an ester into an alcohol. It can convert an alkene into an epoxide. It can convert a thiophene into the gas oxide product. It can convert a ring into an aminic ring into an iminic or quinoimine type of a ring. It can convert many things. It can perform many reactions, which are all mostly oxidation reactions. Simple chemistry. So what is happening is simple chemistry by the enzymes. What is that chemistry? How to understand that chemistry in 3 dimensions? That is a challenge in computer-aided drug metabolism and drug toxicity. Sulfur, oxygen, nitrogen centers are there. If there is a alkyl group attached to these centers and dealkylation, O dealkylation, S dealkylation can take place. That means the alkyl group is broken away and hydrogen is created at the sulfur or nitrogen or oxygen centers. Ring cyclization. Ring may be cyclized via oxidation. Again, double bond is converted into epoxide and things like that. Then reduction can happen. Sometimes some of the cytochromes can cause reduction reactions. Then a few of the reactions like aromatization can happen. Sometimes decarboxylation also can happen. Then dimerization also can happen. Isomerization can happen. May of the isomerization or dimerization of the metabolites. So many things can happen, but all are chemistry, simple chemistry which we learned in our +2. Nothing more difficult. Only thing we have to think is that how cytochrome is doing this chemistry. It is not the chemistry being done in a laboratory. It is a chemistry being done inside the cells, inside the cytoplasm, where there are these enzymes are present and they are causing the reactions. So these cytochromes are mostly present in liver. Some of them are present in gut wall. Some of them are present in kidneys. Some of them are present in brain. So likewise, there are 4 or 5 important sites where the cytochromes are present. Okay, so probably they are not present in heart. So likewise, we need to see where are these cytochromes they are showing activity. Mostly they are showing in the liver itself. That means the drug as it is entering into the body in the very first location, the cytochromes are acting. So we need to supply larger dose. Sometimes larger dose of the drug is also being supplied because the cytochromes are acting on them and the drug is not sufficiently available at the enzymatic center. So we need to be paying attention to cytochromes in a very clear manner. So that's why we should start thinking in 3 dimensions. But now let us see what are all things that can happen. This is a slide which is telling that a few structural features of the drugs are somewhat called alerts. Alerts means structural alerts means these are the functional groups which when they are present in the drug, we have to be watchful. We cannot avoid these functional groups. We don't have to avoid. We have to be watchful. Are they causing any negative impact on the drug and is this causing any production of the toxic metabolites? We need to be watchful. That's all. So which are the functional groups? Look at this. The central circle is showing the structural alerts, and the outer circle is showing the metabolites which are generated. Metabolic, the functional groups after metabolism are shown in the outer circle. The inner circle is showing the functional groups present under drugs. Which central functional group causes which kind of metabolite? For example, look at that radicals may be generated, epoxides may be generated, phenols or phenolines or phenolmethides may be generated, carbenes may be generated, S oxides may be generated, imine methides may be generated, then isocyanates may be generated. This is a circle which is explained the generally accepted structural alerts in drug molecules. Next slide is showing the functional groups. Again, the same what is in the circle is shown chemical with chemical names. Alkox alkyl phenols, acetylenes, alkyl anilines, formamides, furans, hydrazines. These are all the functional groups on the drugs which causes the reactive metabolite formation. Ketenes or ethenes or isocyanate. Most of these reactive chemical species which are metabolites, metabolitic functional groups are electrophiles. That means they are electrophilic in nature. If they are electrophilic, they can interact with nucleophilic functional groups of the proteins or DNA or any of the biological systems like antibodies or any enzymes or proteins which are in the body, all macromolecules. All macromolecules contain functional groups which are nucleophilic, whereas the metabolites generated are electrophilic. That means if the electrophilicity of the metabolite is very high, it can cause dangerous reactions with the nucleophiles of the proteins and enzymes. If the electrophilicity of the metabolite is small, the danger is small. So that means there is a scale we can now immediately clearly consider. Which are those electrophiles which are dangerous? That means which are those electrophiles which cause high electrophilicity, which carry high electrophilicity? Which are those metabolites which carry low electrophilicity? Is there any cutoff value? Maybe we can take a cutoff value of 3, unit 3. Any drug or metabolite which is having electrophilicity index called omega, whose electrophilicity index is greater than 3 are dangerous, and whose electrophilicity index is less than 3 are safe. This is a arbitrary cutoff value. It can be plus or minus 3 for the deciding the danger level. But in general, if the cutoff, if the electrophilicity of a given molecule is less than 1, you are sure that it is safe. It is not going to be dangerous. So you can easily say that if the electrophilicity index of a given omega value of a given metabolite is greater than 5, you are sure that it is going to cause danger, 100%. So you have to avoid the formation of such electrophilic reactive metabolites. So that is a cutoff value which is going to help us. So 3 is a cutoff value, plus or minus 1, sometimes plus or minus 2 you can take into account. So that is, how do we know that? We are going to learn in this particular lecture after a few minutes. So mechanism-based inhibition. It is one of the very, very important reactions that are happening. This is called mechanism-based inhibition, or called MBI. If we can understand this reaction, we will be able to know what is the 3D structural information, what is the atomic level information, what is the molecular level information, what is the electronic level information of these compounds. So for that, we need to first understand what are all the various varieties of inhibitors that can happen at cytochromes. Some of the reactions that are happening at cytochromes are reversible. Some of them are quasi-reversible. Some of them are completely irreversible. Quasi-irreversible means those which are directly involving the metal carbon or metal nitrogen bond. They are quasi-irreversible. That means they are sometimes, in some specific conditions, they may be reversible also. That is the meaning. Now, quasi-irreversible are the ones which are showing carbon iron metal bond, nitrogen metal bonds. Irreversible ones are showing the reaction with the porphyrin ring. The nitrogen atom of the porphyrin ring, if it is participating in the reaction, that gives rise to carbon-nitrogen bond, and that becomes irreversible. But iron-oxygen bond, if it is formed, again that becomes irreversible. There are structural, to understand this mechanism-based inhibition, there are 9 levels of different parameters. Saturation kinetics we can understand. Time dependency of the reaction. That means the metabolite formation is going through a time dependent manner. That means again kinetics only. That is if we can measure that. Or the presence of cofactors. Which particular cofactors are causing this formation of mechanism-based inhibition? Whether substrate or inhibitor-based chemistry, catalase or superoxide dismutase-based chemistry, lag time is there or not, scavenger effect is there or not, 1:1 stoichiometry is maintained or not, is it causing irreversibility or not? There are several criteria on the basis of which mechanism-based inhibition can be determined. Now let us take an example. Look at this particular slide where there is a methylene group, that is CH2 group, is present between the two oxygens. This is a functional group which has got very easy accessibility towards the cytochrome, and then it can cause the formation of COH, and that COH can be converted into a carbene with the help of second cytochrome, and then this carbene can form the mechanism-based inhibitory complex. Otherwise, this may also lose carbon dioxide and produce dialcohol, and this dialcohol can easily cause covalent modification. These are all the various varieties in which quasi-irreversible carbenes can lead to mechanism-based inhibition. Look at the 3D structure of the reactive complex. Mechanism-based inhibition complex, or this is also known as MIC, mechanism-based inhibition complex, MIC, or metabolic inhibition complex, MIC. Look at that. Carbenic carbon is directly bound to the iron center of the porphyrin ring. That is a complex. This complex can stop the activity of the cytochrome. That means the cytochrome is producing the carbene, and the same carbene is killing the activity of the cytochrome. That means it is also now called as a self-kill mechanism or suicide mechanism. That means the cytochrome is suiciding itself by creating a carbene intermediate. That means the activity of the cytochrome is stopped. That is dangerous, because if the activity of the cytochrome is created, metabolism is not happening. If the metabolism is not happening, the xenobiotic is not getting excreted. If it is not excreted, its concentration, the concentration of the xenobiotic in the human body is increasing. Suppose you take paracetamol, 1 tablet today. After 6 hours, the paracetamol, more than 90% of the paracetamol is going out of your body. Then 10% is showing its drug action, it is okay. But if the paracetamol that you are taking in the body is remaining in your body for 1 month, that means it is really dangerous. Paracetamol is not safe. Paracetamol is actually a very dangerous compound, but it is safe for only 6 hours. If you take the drug, within 6 hours it goes out of the body. After showing its drug action, we feel very comfortable. It is good for us. If it is staying in our body for more than 1 year, more than 1 month, it can do many things which we don't want. Okay, so we want a drug, whatever drug we are supplying should go out very quickly. That should be one of the mechanisms. If it is not going out, we are going into the danger zone. That is why we say that drug, especially the allopathic drugs, are probably having plus or minus effect. Sometimes we say the drug is causing the problems. The drug is required. It is required evil. This is a necessary evil. So how to balance this? By controlling the action of the cytochromes, we can balance. So now, if the cytochrome itself is killed, if it is committing suicide, that means there is no purpose. Natural purpose is blocked. So we don't want mechanism-based inhibition to happen. That means we have to see wherever whatever is the reason why mechanism-based inhibition is happening, how to stop it. We want to understand that. Another example, let us see that aliphatic and aromatic amines are N containing species, R and ME containing species. What they do, they can with the help of cytochromes, they can undergo formation of CH2, and then as a result, this compound NHR can get converted into RNO, nitro species. RNO. This nitrogen can bind to the metal directly and then cause quasi-reversible inhibition. We want to understand wherever this is happening and how to prevent this. Now again, another example, compounds containing phenylazenes can undergo cytochrome based activity and produce compounds with N and double bond. That means they are colorful compounds, but they may further lose nitrogen gas, and then they form radicals, and those radicals may react with the nitrogen of the porphyrin and then cause irreversible inhibition of the cytochromes. Another example is that if you know compounds containing double bonds can undergo epoxide formation, and oxygen epoxide is generated. That leads to the formation of the alcoholic species. Those can ring open and then cause the formation of metabolites, which are highly electrophilic in nature, and then they react with glutathione and then cause sometimes they get excreted, or they can be producing unwanted reactivities. Next.
27 सूर्य अगर 14 days से अगर सही कर ले तो रिवाइव कर ले.
No, before understanding the whole process.
27
maybe I should stop for a few minutes.
પૈસા આપી દેશો અને રિવાઇવ કરી લેશો તો રિવાઇવ થશે, નહીતર પછી ખબર નહીં.
I'm getting disturbance. Shall I stop here for a few minutes? Okay, now it is fine. So before going into the entire process, we need to think in 3 dimensions. All molecular modeling people, one of the very important thing is that they should get the habit of thinking in 3 dimensions. Most of the chemistry that we learned in our BSc or MSc or in B Form or in BTech, whatever chemistry that we learned is all comfortable to be writing on a paper. When we write on a paper, it is 2-dimensional. Any chemical object is not a 2-dimensional object. It is a 3-dimensional object. So very first thing a molecular modeling scientist should do is to think in 3 dimensions. Drugs are 3-dimensional objects. Macromolecules are 3-dimensional objects. The interaction between drug and macromolecules happen in 3 dimensions only. The dynamical process responsible for signal transduction in the body is due to 3 dimensions. The chemical reactions responsible for secondary messenger generation are all happening in 3 dimensions. The drug transportation process through cell membrane is happening in 3 dimensions. So many things, everything is happening in 3 dimensions. If we think in 2 dimensions, as we are comfortable in writing on a paper, that is actually a wrong representation. We are doing wrong representation intentionally because it is easy to explain to students. The teachers are comfortable in 2D, but scientists should not be happy in 2D. Scientists should always think in 3 dimensions. So because everything is happening in 3 dimensions. Pharmacoinformatics is a topic which helps you in thinking in 3 dimensions. So if you are adopting the molecular modeling, if you are adopting computer-aided drug design, if we are adopting pharmacoinformatics, if we are learning this topic, we have to think in 3 dimensions. This is a habit. You have to habituate this and practice it. To practice, do we have any tools? Our paper and pen are not going to help. So for that, there are many tools available. Some of them are freely downloadable tools available in the internet. There are some of them which are possible by. There are several tools. I don't want to give any name so that I don't want to get. I don't want to support one software here. There are so many software which are freely available, or so many which are commercially available. You can procure any one of them and then practice it. Sit in front of the computer screen, practice it. Again, use your mouse very efficiently. Think in 3 dimensions. The moment you develop the habit of thinking in 3 dimensions, it becomes so easy that you will become a first-class molecular modeling scientist. If you think in 2 dimensions, you are not a molecular modeling scientist. You are only trying to learn and you will fail. Any molecular modeling scientist who think in 3 dimensions is first class. Any person who remains to think in 2 dimensions is third grade.
Hello. Hello, sir.
Professor PV Bharatam is trying to reconnect, so it will take another 2-3 minutes. There is some technical issue from Naipar Mohali. So he is trying to resolve. He will continue as soon as he will be able to log in. So Professor PV Bharatam is not able to connect due to some technical issue from Mohali. We will take a 15 minutes break and talk of Dr. Sandeep Kumar Dhanda and hands-on session will be preponed, and we will start this session at 10:45. So now around 12 minutes break we will take, and immediately after 12 minutes we will start the talk followed by hands-on session of Dr. Sandeep Kumar Dhanda from USA. Thank you. Hello, Sandeep. Good morning from Indian side and good night from US side.
Good evening, sir. Good morning to you. I hope you can see my
How are you?
screen, right?
I can see your screen, yes.
Great.
So we will start in another 3 minutes.
All right, no problem.
So, Suman, you can this YouTube.
Okay, so it's live on YouTube, right?
It's live on YouTube. So now we are also live.
Oh, nice. I cannot see the both screen. I can just see my PowerPoint. I cannot see who else is live there. So
You can actually close this PowerPoint, and once we complete the introduction session, you can start. One minute. 1 minute.
Sure, I can do that. I think
I am just putting it in mute.
Hello.
Hello, sir. So if anybody want to interact with Professor PV Bharatam, they can do that. There was some technical issue in the later period of his talk, but the most important message was already given, and then all the important slides was already displayed. So if any of you want any interaction with Professor PV Bharatam, you are welcome. If you have any question, if you have any interaction, anyone.
Which one is it? Yes. I have not realized the net problem. So any questions? I'm happy to answer. Am I audible? Yeah.
Yes, sir. Yes, sir. You are audible, and these people are muted So if any of you have any question, you are welcome to ask. Otherwise, we will continue with the next session. So we'll wait for 2 minutes because I said that it will be a break and then it will be Dr. Dhanda will start. So
you can type the questions if you.
Yeah, if you are not able to ask, you can type. Sanjana, you said you wanted to ask some question.
Hello.
Yes.
Yes.
Sir, you told us in the slide that paracetamol remains in the body for about 1 month or so. So is P450 unable to metabolize it or not?
No, paracetamol does not remain. Paracetamol, if it remains, which is dangerous. Paracetamol generally does not remain. It gets metabolized to something called quinoamine, NAPQI. It's called NAPQI. NAPQI is easy to excrete, but if we supply paracetamol in large quantity without, if we take the tablet of paracetamol in the absence of the doctor's prescription in large quantities, then the amount of NAPQI will increase in the body, and that can cause two problems of the liver, and then liver damage can happen. That is called this is non-alcoholic fatty liver disease that gets triggered in the human body when we utilize these NSAIDs in large quantities without the if we utilize recklessly these NSAIDs. We have to use all these drugs with the help of doctor only, as per the prescription only. Paracetamol, if by chance if it remains in the body, it can cause this liver damage.
Okay, thank you, sir.
Any other question?
Hello, sir.
Yes.
Yeah. Please continue.
VVO Roli. Sir, I want to ask that I'm also working on P450 and I have also currently I'm working on BP analogs. And sir, how can one make sure that which kind of reactions will eventually lead to the formation of toxic metabolites? Is there any trend in that? Like you said, quinone formation. So I have seen that majorly quinones are responsible for toxic metabolites. So if I want to study the effect of some substrate after the metabolism from P450 and any foreign compound, then how can I make sure that it's gonna be toxic after this particular formation of metabolite?
So it is not very difficult. Once you understand the 3D structure of the metabolite, you need to understand, you can perform something called Fuki function analysis and the omega C function analysis. If the omega value is more than 3, the metabolite is dangerous. And if omega C value is at every atom on the ring system, which particular carbon, which particular nitrogen is dangerous, we can understand by estimating the local electrophilicity of each and every atom. Omega is a global electrophilicity function. Omega C is local electrophilicity function, and related to that is a function called Fuki function analysis. That is also very easy to do. There are simple formulae after performing electronic structure analysis from the wave function of the metabolite. We can analyze what is omega C, what is Fuki function. Based on this, we can determine whether a particular center is causing toxicity or not. So based on that, you can read several of our papers are published. there are at least 3 articles of our laboratory in Chemical Research and Toxicity Journal, CRT. There we have explained, elaborately explained whether quinone is dangerous or quinone imine is dangerous, things like that. Please read those, that will give ideas. Otherwise, you can write to me email. I will also help you.
Okay, sir. Thank you so much, sir.
Yes. Okay, thank you.
Anyone else have any question? If not, let us thank Professor PV Bharatam for his very nice talk. And you can always write him email. His email is available on his website. And you can always interrupt. You will get reply immediately. Thank you, sir. Thank you very much for your talk.
Thank you very much. It is a nice organization. I wish you all the best in future also.
Thank you, sir. So the next speaker is Dr. Sandeep Kumar Dhanda from St. Jude Research Hospital, USA. Dr. Dhanda, you are online.
Yes, I am.
So he is a bioinformatics research scientist. He earned his doctoral degree in a joint degree program of CSIR IMTech Chandigarh and JNU New Delhi. Then he pursued his postdoctoral training from the La Jolla Institute for Immunology, California, USA. He has authored more than 50 scientific publications and also serving as an academic editor for several reputed journals. He is a well-recognized peer reviewer, and he has trained so many young generation. His research led to development of various prediction models and analysis tools that is hosted on IEDB. And he has also developed CRDD website, and those tools are being widely used for the prediction of T cell immunogenicity. So he's an expert in machine learning and also in bioinformatics. Welcome, Dr. Dhanda. And
thank you, Dr. Srivastav.
Thank you.
Thank you. So with that introduction, I will start sharing my screen, and I hope you can see my slides now. All right. So am I audible and my screen is visible, right?
Yes, you can continue.
All right. So thank you very much for having me, and I want to thank all the leadership for organizing such a workshop, and I want to thank all the MMT team for organizing it efficiently, and especially thank Dr. Srivastav for extending the invitation to present my work in this conference. And with that, I will move on with my talk, and I'll be talking about my first project that I got exposure in my PhD degree, and it was very first project that I undertook during my PhD training. So the project is about machine learning application for predicting drug likeness. And with that, I will move on what is going to be the overview of my presentation. And this is what I have selected to present in this session. I will start with defining the problem, how we can address the problem once we define it. And then by defining it, I want to explain what do we mean by drug likeness and what are the available definition and related literature to it. And then we will move on to the second part of it, and where we'll talk about choosing the right data set. Once we know the problem, then we need to figure out what is the right data set to address this problem. And then we'll move on similarly with creating the feature space. That means machine cannot read the raw structure or the sequences, and for that matter, we need to convert this structure or sequence for that matter into the feature space or in numerical form. And then I will talk about selecting the most prominent feature. Obviously, once we have come up with a large feature space, and every feature that we are going to use in the machine learning model are not going to be useful. And there is also some of the feature which might create the noise rather than the signal. So we need to be very careful about selecting these features. And I'll touch base upon how we can select the most prominent feature out of the huge feature space that we can start with. And then based upon these features, I will talk about how we can build the machine learning model itself. And while building the model, what are the different aspects that we should take care of. And one of the things that we should take care of is the cross validation, how we are validating our model. So there could be two different levels of validation. The one could be internal cross validation or k-fold or n-fold or leave one out, that kind of cross validation. And the one could be the external cross validation that I will talk a little bit about related to this project. Then once we have a model in hand and we have already cross validating it, how we are validating, there should be some metrics. And these matrices are like performance evaluation matrices. Then I will talk about how we can come up with the solution and how we can trust certain model over the other. And at the end, once we have a model in hand, how we can help it, how we can implement it over a website or in a software so that the other people in the field can also use it and verify it. And with that, I will start with the very first one, defining the problem. So once, like obviously I was talking about the drug likeness, so it's necessary to define what do we mean by drug likeness. So drug likeness means, is there a common feature in all the drug that make them a drug? So can we predict something like drug likeness? That particular mean, can we find out the feature that makes certain chemical as a drug? So that will be called drug likeness. And is there a way we can classify all the molecules that we have in our space and in drug-like and non-drug? We understand that some of the chemical could not be drug because they could be toxic to us, or they are offering no use, or we cannot metabolize, we cannot have like metabolism system for them. So there should be a system we can recognize this is going to be drug or this is not going to drug. This is a broader definition to classify the molecules, especially the small molecule or the chemical structures. And once we have this kind of a model where we can classify this chemical into drug-like and non-drug-like, then obviously we can start the first step at screening. While we are in going in the drug discovery phase, we can start with screening all the drug-like molecules. Rather than like screening or assaying all those molecules, we can only focus on with a few set where the property of being a drug is more pronounced. And one of the rule that discussed in literature is Lipinski rule of 5 that I will just based upon like the next slide. What do we mean by rule of 5? So the rule of 5 is actually the 4 rules, and every rule has something related to 5. That's why it's called a rule of 5. So that means these are the 4 different parameters we are using as a fundamental while we are selecting this chemical to be as drug-like. And this could be, there should be not more than 5 hydrogen bond donors, or there could not be no more than 10 hydrogen bond acceptor in the molecule, or there should be no molecular weight more than 500 Dalton. And there's also a lipophilicity, which is called like log P or C log P for that matter, should not be greater than 5. So if we combine all of these 4 rules, in fact, then we will classify them as called Lipinski rule of 5. This rule came after a comprehensive analysis that was performed on all the molecules that were approved by that time. And if you see the graphs on the right hand side, you will see the many drugs that are approved over different years from from here 1990 to 97 or from 2008 to 2017, how we are relying on this parameter. And if you see, there is a big graphic, all the drugs which are approved before 1997 are following the rules of 5. These are in the blue in color. The molecular weight is less than 500 for most of them, and it also same case for log P, which is less than 5 for all the blues, and similarly here for rotatable bonds, and similarly for hydrogen bond acceptors, which is less than 10. So if we see all this parameter, this has been followed rigorously in the chemistry while designing these molecules. But it is not like a perfect rule, and we also see some of the drugs which are approved from 2008 to 2017, and we are seeing many of these drugs are actually following, which are following along the bars in the blue and the red. So that means they are also following the Lipinski rule of 5. But there are also some exceptions which are in the red color, but also going beyond this 500 molecular weight in the first graph, and similarly going beyond C log P5, and similarly going for more rotatable bond or hydrogen bond acceptor. That means the rule is not a complete stamp that we can trust on. There's still a way we can find out the better rules from the chemicals. But this was a good starting point, because by simple physiochemical property, we can select few of the molecule that could have the property of being a drug rather than the other molecule space which we are not going to assay. So with that definition kind of in mind, now we are going to move ahead with the set of molecule in a bigger comprehensive analysis that performed in 2014, like how many of all the drugs are actually following all these rules here. So if you see all the oral drugs, they has a higher probability of following it. If you see on the table on the left hand side, I know the text is little like in smaller in size, or you won't be able to read, but the message on this table is about how we can find out all the drugs that are following the Lipinski rule, and there are some drugs which are breaching it. So most of the oral drugs are following it, but then the other drugs which are given through the other route, maybe we call it parenteral route. So those drugs are not following this rule very often, that being followed by the oral drugs. So there is always a breach of class, and some certain class are following this rule, but not all of them. And this rule needs to be revisited, and this should not be set as a guideline, which has been done by most of the industries, and how we can improve it using the latest technology, especially when we talk about the machine learning. Now we can go beyond just talking about the physiochemical property, because now we can understand the very minute fragment inside the chemical structure, and we call them fingerprint. And based upon even those small fingerprint, we can have better rule that could be even better than those are explained by the Lipinski. So moving with this kind of problem, then we need to understand, we need to choose the right data set, because the data point that we are going to select is going to be actually making a huge difference in our model. And if we are going to select the right data set, we are addressing the problem in a right context. But if you are not having the right data set, then we might end up in trouble. And with that, we know, and we have all the positive data set. Machine learning, we need to have like positive and negative data set when you are running a binary model. But at the same time, when we talk about the positive example, that means the approved drug. These are the drugs that we are already taking for various to treat various illness. And in that case of like, we know there is a data set we can provide with the positive example, and we call them approved drug. So we already have a positive data set, but in case of a binary classifier, we also need to have an ideal negative example. So what could be an ideal negative example to classify the drug like versus a non-drug like? So there are various kind of theories put forward that these are related to experimental drug. We should go with the experimental drug, or the failed drug which were running in the clinical trial but failed due to some reasons. And there are also some drugs which are approved at some point, but they are also withdrawn at later on because of the side effect, or there could be random structure. We know these are not even tested, so this could be, we can pick the random structure. So what could be an ideal negative example? So if we try to understand the details of our machine learning model, the best machine learning model will be which can classify between the sister molecule. So if we classify between the very close molecule which are close to approved drug, then we can obviously classify the molecule which are way distant than that. So that means we should pick the negative data set in such a way which is closest to the approved drug rather than being such a random structure. So the best algorithm is the one that can differentiate between the sister molecule and what is the closest to approved drug. And I would bet that could be the experimental drug. Those are the ones which are running in different phases of clinical trial. So with that, we went ahead and searched this kind of data set at Drug Bank, and it has a complete repository for approved drug, from the experimental drug or nutraceutical drug or illicit one or withdrawn one or investigational. So these are the different definitions that they offer, and we can also download all these example from the Drug Bank website from the format, and we can use this kind of formatting to have a clean model of classifying positive and the negative example. In this case, we went ahead by choosing the structure, all the structure from the experimental drug versus the approved drug. So our model is relying on the discrimination between the approved versus the drug in running in the experimental phase. And with that, again, once we have chosen the right data set, then we need to have certain kind of pre-processing. So right now we are talking about the second stage where we have chosen the right data set and we are classifying the approved drug from the experimental drug. And we are believing if we can make this kind of discrimination, we can obviously discriminate between any random molecule than the approved drug. So we need to perform certain kind of pre-processing while we are dealing with this kind of structure. So there could be certain level of pre-processing, let's say remove salts because there are some salt breeze associated with them, and these are more purpose to make them stabilize rather than to be make them more active or more drug likeness. So that's why we can perform certain kind of pre-processing, and the one thing that we have done in this case is remove salt breezes or the salt connections from there. And we can also need to deal with the structure because there could be different format, and we need to preserve the integrity, because while we are dealing with one cytolike smiley structure, we might not have a complete idea of the 3D structure and L and D structure and how we are going to deal while we are converting from one format to the another. So we have to be really careful about these stuff, that we are sticking to one format and we are not losing any information because of the format conversion. And with this kind of information in mind, we have moved on with approved drug was the experimental drug, and this kind of be a good example, and I want to explain it taking the PC example. If you see on the lower side, there are some red and green and blue dots. So the red dots are related to the experimental drug and the blue dots are related to the approval drug. So these, if you see these data are very much overlapping, that means if we can have a model that could classify between these two, then we can obviously have a better system to classify than the random or distance molecules. So the feature space overlap between and the approved drug and experimental drug was verified, and it seems to be a really good problem. And we are not able to see a distant line when we plot PCA for them. And this is the upper side shows the number of component, and you say like the first PC and PCA to how much variance is explained by them. And I will touch upon the PCA part once we have a classification model, and we also use this feature which we derived from here in our machine learning model, and I will touch based upon once we talk about building the model itself. Let me move on with the other part of it, which is like creating the feature space. In feature space, I mean, we already have the structure in hand this time, and we know these are we going to treat as the positive example, and this is we are going to treat as the negative example. Then we need to transform this structure or this chemical list into certain numbers, and because machine could not read all this information from the structure itself, that's why we need to convert them into some numerical form, and this numerical form should come from only this small molecule or the molecule in our hand. So we need to understand that there are some software where we can transform this chemical structure, or we can find out the feature related to those structure, and we use paddle descriptor in this case, and which offer various 2D feature, 3D feature, or fingerprint that I will touch based upon in our next slide. In the next slide, like I'm creating the feature space. So 2D feature are like representing the outline of the molecule, like what's the volume, what's the size, or polarity, or physicochemical property. Or 3D are related like L form, isoform, or which are the different coordinate in the molecule. So representing those kind of features are labeled as the 3D or 2D. And there are also different sets of feature that it offered. These are called different fingerprints. So these fingerprint are like 10 types of fingerprint are offered by this Paddle software. These are called PubChem, Mag, Substrat, Calicut, Roth. So these are the different types of fingerprint. What they do is explain on this figure here. So once we have this kind of chemical structure, then we can obviously break it down to different bonds, and then we can say if the chemical is having this kind of bond, we are going to have a feature set that's down there, a vector form. It's going to be 1. If it is not there, then we can put 0 here. So these are the different moiety that are present inside the molecule, and then we, based upon this moiety, we can break it down to smaller fragment, let's say alcohol fragment, ammonia fragment, or those kind of fragment. If it is present there, we are going to put that feature as 1, otherwise it will be as 0. So it is simply binary conversion of the structure molecule, and then we need to have the big space there. Let's say for PubChem there are more than 800 features that we can have this vector. For Max is around 166, similarly for substructure and Calicut Roth. So if you combine them in total, there are more than 10,000 different features that we can combine all this chemical information into the number. So once we have this huge feature space, then the next step is like these are the number of features that we had that time. So the fingerprint, one of the fingerprint is like 100,000 fingerprints are there. In case of extended, again 1024 is there. For Max 166, for PubChem 881. So In total, we have more than around 10,000 of fingerprint coming out of a single structure. So single structure could be then have a vector of 10,000 long information. And from that information, then we can generate the machine learning models. And obviously we understand that all these 10,000 are not going to be useful. Some of them redundant, some of them empty. So we need to have a system where we can find out the useful information in those fingerprints. And for that, we need to select the most prominent feature. And that's why I said some of them will be empty, because none of our chemical structure might be having that moiety which is assigned for is like a different chemical structure which is not there in approved or the experimental drug. So that's going to be empty for all the chemical structure. So those kind of empty features are not going to be useful. They are going to create even noise if we use them in the machine learning, or they're going to be additional bias or weight if we use them. So rather it's better to just remove them at the first step. So we need to remove the feature which are like, let's say, empty or shown less variability. That means one feature in one fingerprint might be having a very similar output for the another feature. So we need to be consistent that these features are showing the variability. If they are less variable among each other, so we are going to remove them. And we also need to take care of redundancy. So in this fingerprint might be the fingerprinter are actually explaining the same feature which are there in the graphs only, or maybe in the substructure. So we need to remove all the features which are redundant. And we also need to remove the highly intercorrelated. So two features, they might be explaining a different thing, but their correlation for the approved drug and for the experimental drug remains the same. So that means the information quotient could be explained by just one of the feature. So we don't need to use both of them. So we need to remove this kind of feature, but we also need to keep certain feature. And we need to understand there are two different points where we are going to select this feature. The one is this should be explaining the diverse property, and there should be high correlation with the drug likeness, and there should be minimum intercorrelation. So with this in mind, we selected feature space, and I will explain how much feature were selected after that in this slide. And one of the approach that we followed that time is we have all these fingerprints here listed in this table in the first column, and the next is description what they explain, like this sub FP13 explaining the primary alcohol, this sub FP41 explaining the 1,2-diol, this sub FP48 is explaining the aldehyde, and these are the number of time it's found in the approved category. So this is the number of fragment is found in the approved category. Similarly, not found in the approved category. This is the same way we found in the experimental and not found in the experimental. And then we can use this frequency found in approved versus the experimental, and then based upon this frequency, we can decide which of these features are really useful, are contributing more to our discrimination between the approved and experimental. So this is the way we selected the most prominent feature. This is I'm explaining for only one of them, for sub FP, which is coming out of this table. The sub FP is this one, 307. So these are the most prominent features that we could find based upon our correlation that we did based upon the frequency. And similarly, we did for the max, and we also kind of determined what the accuracy we are going to achieve if we just use this feature. So if we use just this feature, we are going to achieve this much of accuracy, and this is the frequency it could be found between the approved and the experimental drug. So if you are wondering what are these max, if it's just a name for you, this is the way to explain. So this is the legend here on the bottom side, and upper side is the max. So it explains if this moiety is present in this form, we are going to consider that as one of the fingerprint, just like max 138, similarly max 66. So this is the moiety present, it would call max 66, otherwise called empty for max 66. So these are the one which we could find out to be most prominent one in case of classification of approved and experimental drug. Then we move ahead with building the model. So while building the model, I'm going to show you this feature, this kind of a plot where we have this blue and the red dot, which could be related to class 1 example or class 2 example. In this case, it could be approved and the experimental drug. And while building this machine learning model, we took an example of support vector machine. What support vector machine does it to try to create a hyperplane or the line between these two colors of dot, so that we can find a margin, the greater margin between them, the dots that are closest to this line, as compared to which are closest to this line. If we have a bigger margin, then we have a better model. And these are kind of a plotting, a kind of throwing the dots in the 2D into a hyperplane. And in that hyperplane, we are going to find out a line where we can discriminate between our positive and the negative example. And we can not only have a linear line, we can also have the radial or the binomial lines. So based upon the different kind of kernels we used in support vector machine, we can have similarly the type of model that we could generate from them. The complexity of the model is defined by the kernel then. And with that, I will move on with the next type, which is related to cross validation. As I mentioned initially while I was introducing it, so there could be two levels of cross validation. The one cross validation is for internal purpose, which we are going to use in our data set, and we divide our training data set into different folds. And in this case, let's say we divide in our 5-fold. We are going to use only the 80% of the data in the training, and the remaining 20% is going to be used as a test, so that whatever the model built on the 80% data is going to be used in the rest 20%. And we shuffle this 20% again and again and again till all the sample in our model are used once for the testing, and the rest of the time it was used for the training. And we are going to do it to find out the parameter. And once we know the parameter, then we are going to use all the data together. And when we throw all the data together with those parameters, then we are going to use those parameters and build the model and evaluate the model on the independent data set. That's why we call it external cross validation, that I will touch upon the following slide. And with that, I will move on the performance evaluation. While we build the model based upon these two approaches, building the model, choosing a right algorithm, or choosing the cross validation approach, then we can find out how we are going to evaluate how our model is doing. So for that, there is a matrix called where we can divide our data set into and actual data set for positive and negative, and how they are predicted. So if our, let's say for positive sample, it is approved drug, and if it is predicted as an approved drug, then we will count that particular instance as the true positive. If it is approved drug, but it is predicted as the negative, predicted as the experimental one or the non-drug like, then we are going to call it as the false negative. And the same way, if we have experimental drug or the non-drug like, then it classify as the approved drug or as drug like, then we will call it a false positive, and we will call it a true negative when it was not a drug, actually approved drug, and it was not predicted in that class. So that's why it was not approved drug and it was predicted as not approved. So that's why I call it true negative. And based upon all these four number, true positive, false positive, true negative, false negative, we are going to have a matrix that is related to sensitivity, where we have this mathematical formula to convert this true positive, false positive into sensitivity. And that's actually a metric to define how we are performing in predicting the drug-like molecule. And then another matrix we have used is specificity, where we see like true negative, how we are doing, how specific is our model. That means how specific are we predicting the non-drug-like molecule into non-drug-like. And what's the accuracy is a combination of sensitivity and specificity, where we combine these two together and we use this formula. And there is another approach. All of these are approach related to true positive and true negative, and there's a similar correlation approach which is called Matthews correlation coefficient, which balances between the sensitivity and specificity. We know we do not have the equal data set, like our positive example were not equal to the negative example, so it is not a balanced data set. In case of imbalanced data set, this performance matrices like sensitivity, specificity, or accuracy might skew toward one of them, and MCC is a correlation coefficient which balances the sensitivity and specificity and not allow it to bias to only one of the prediction. And all of these are based upon the threshold. Threshold means once we are predicting, we are having a score, and based upon that score, let's say it varies from 0 to 1, and we are putting a cut of, let's say 0.5. Above that we are classifying in one, and below that we are classifying into another. But this is all of these parameters are threshold dependent. So we also use some threshold independent evaluation matrices, that is ROC, where we plot true positive rate on y-axis and false positive rate on the x-axis, which is not visible here in this figure. I'm sorry for that. And then we plot an area under curve, how we are doing over the different thresholds. So it's threshold independent parameter, and we can have this kind of plot. Then if our value is random, then we will observe this kind of line, the dotted line which is shown it here. So if we are having this kind of model, then it is very well equivalent to the random samples, and the AOC value would be 0.5 in this case because it's explained only the half of the curve there. If our value is greater than 5, that means our model is working to some extent, and the extent will be defined by what's our value. So let's say our model could be maximum, the value could be 1 if it is a perfect model, which is rarely the case, and our AOC will be closer to 1 if we are having a decent performance. So with all these numbers in mind, I will now throw some table to the screen and will let you evaluate how we did in classifying the positive and the negative example, or what drug-like versus the non-drug-like molecules. So this is the performance of our model while we were using only the few features which were selected by 2 different algorithms. The 2 different algorithms that we used, we built the model based upon support vector machine, but we select our feature based upon the Veka, which has a huge list of feature selection approaches, and we used only 2 of them. The remove useless, that means these features are either the empty that I explained from the slide, either the empty, or they are having the same value as the 4 others, or they have high correlation among each other. So it removed all of them, the remove useless, and these are the different fingerprints that you see on the left hand side. And out of the, let's say, I remember there was 1024, and how many were removed if we use this one, how many were removed if we use this one. So if you go with the max that I remember, there were 166. If we use the remove useless algorithm, then we left with 159, only removed 7 of them. But if we use the CF subset eval, which is a more regressive algorithm, which takes care of the correlation between the feature and also between the class that we are going to use. So these are the 2 algorithms applied to all the different fingerprint, and these are the number of fingerprints that we left after applying to this algorithm, and this is a threshold that we use. And based upon the threshold, we achieve this kind of performance in terms of sensitivity, specificity, accuracy, MCC, and AUC. So actually AUC is independent of threshold, but this is a threshold for rest of this matrix for sensitivity, specificity, accuracy, and MCC. And if you are not want to go into detail, then I will show you a plot simply there, which shows the MCC values for features selected by one algorithm versus the another. So now you can see this is the MCC value, and the highest MCC value were formed in max feature or the subcount feature. So this is the MCC value that we achieved, which is relevant to around 0.77. It could be maximum 1. So our performance is somewhat acceptable, or maybe decent one. And we are having a good AUC value of 0.95. That means it could be maximum 1, and we are achieving a very decent performance if we compare it in terms of AUC. So with that, we went ahead with the max feature, and then we applied different kind of approaches, different kind of hybrid model, how we can find out the best model that can classify, and how we are performing on the independent data set. So with that, I said I was going to explain a little bit more upon the principal component analysis, and from here we had chosen 166 feature from the max because that was the one which was performing the maximum with the minimum number of feature. Substructure count was also performing with the same performance, but we were having more number of feature in this case. That's why we have went ahead with the max one. And while we had chosen to go with the max, we also plotted them using the PCA that I have shown earlier. And in PCA, kind of once we are plotting this this dot on X and Y axis, the PCA is actually try to classify them and reduce the dimensionally and transform this this feature into 2 dimension, so that we can find out the dots which were close to each other and we now could be distant from each other. And it transforms in such a way where the first principal component, the PC1, explain the highest variability. So the highest variation is explained by the PC1, followed by the PC2, and so on. So if we choose the feature based upon the PCA, how our model is going to perform, that we have tested in our paper. And we have seen that if we are using all the 166, we achieved a performance of 0.79 in terms of MCC. But if we choose top 20 based upon the PCA, that means we have chosen these many features from here, then we achieved a performance of 0.72, or similarly we have used top 15, top 10, or top 5, and we see there is a fall in the performance, but the fall is not that significant as the fall in the number of features that we have here. But we have noticed that we are having a better performance only with the 10 feature rather than going with many feature from the max. So only 10 feature without any PCA could be even more useful, and it achieved a MCC value of 0.67, which considered to be decent one by considering only the 10 features. And with that, we went ahead with creating the hybrid model as well. So rather than just selecting on the max feature, can we combine the different feature space? So we try to combine taking the top 5 based upon the rank. So we ranked all this feature based upon their correlation. So we took the positively correlated 5 from each of the 10 fingerprints. So in total we have 50 descriptor, and this is the performance we achieved if we take 5 feature from each of them based upon the correlation with the class. And similarly, we did the bottom one, which is the negatively correlated with that one, and then we achieved this performance. And then we combine the first two, then we achieve this one, then we try the another hybrid model where we took all the feature, but these are one which are already selected feature based upon the CF subset well. So we combine this 9, 25, 40, 43, and we end up with around 300, so 296 to be exact, and we achieve this performance. And even though we can also perform the feature selection on this 296, the same CF subset eval with stringent parameter, and we come up with only the 22 feature from different fingerprint, and this achieved us to a around 0.7 MCC and around 0.9 AUC value. So this is the final model that we implemented in our model. Then we further validate this kind of model by dividing the data into training set and the validation. We already use like the shuffle our data like from the training set, only use the 80% of it, the training the model, then use this the rest of the 20% of the validation and how we perform that one. Then we try to do the same stuff for different sets of combination. Let's say for model selection based upon the top 20 principal component, or a model based upon the max feature that we have selected previously. So we tried all sort of combination, and our performance remained consistent. That shows we have done a pretty good job while selecting this model, and it has robust enough. It is going to work even if we shuffle our data a number of times. And it is not only that we should boast upon our performance based upon the training data, because everyone could have a very good model which works very good on the training data, but the real model should be validated on the external data set. That's why we have chosen to be take out some of the independent data set, and our model show like 84% sensitivity and 39% specificity accuracy with the independent data set, which was created using the comparison of the drug bank version 2.5. It should be 2.5, not 2. So when we compare the 2.5 and the 3, so it achieved a performance of 84% sensitivity and around 40% of specificity. But if you see this 40% as a low benchmark, and then I would mention here like about 61% we assumed this is going to be potential approved in the future. So these are the experimental drug which are classified being as the drug-like. So these might approve in the future, and which happens to be very true when we compared while we were creating the data set. So that time there were 21 drug which went ahead from the experimental class to the approved one. And when we run our prediction based upon only on those 21 drug, they were all classified as the approved. So that seems interestingly our model is working very good with the chemical and identifying them which is a drug-like. So which is one of the like a good benchmark for our model. And we have also performed this on the screening of different data set. We also screen the Zinc database, and you can also download all the class and the files that are relevant to this kind of screening. From here, we have screened more than 10 million compound from Zinc database and some around 20 million from CHMBL, and it seems to be having a 78% drug-like and around 72% drug-like molecule in Campbell. And you can find all this result from this CRDD website. And with that, I will move ahead with the implementation of model. Once we have the model in hand, the real purpose will be served when somebody could use it and they can really validate it on their chemical set or their validation. So they can also perform virtual screening, they can design analog, they can search in the database that we have already screened, or they can also see how our algorithm is working on here, and they can reach out for any question to us. And this server is already running on this particular website, CRDD OSDD OSCAD Drugment. We named it as a Drugment. That means a server for identification of drug-like molecules. And with that, how you can use it, I will show a little bit of a small demo. Here you can provide your chemical structure. Either you can apply in one of the chemical format. It could be STF, mol2, mol, or smile, and you can paste it here, and then you can browse from your file and then hit submit. Then you will end up on this kind of page where we will show you the molecule ID that we assigned for your molecule, or it was given already in the structure. We can repick it from here, let's say 6505, and it's the same here, right there. And then it will show you what is the SVM score if you are interested in to go in that detail. Otherwise, you can just move ahead with it is a non-drug like molecule, and the probability of our prediction, how reliable it is the prediction. The probability is very high. So very high or the high, and if you select any of the structure from here, it will display the structure of that molecule in this JS mode. And if you click on this particular kind of structure, then you can also move ahead with the another page for analog designing, so that you can change a little bit of this moiety and add few of them and see will it going to be drug like if I add or delete this particular fragment in the molecule. And this was very exciting project for me and one of the very first publication, and I'm glad to be a part of this excellent team. I want to thank Dr. GPS Raghava, who is happened to be my PhD mentor, and I want to thank Dr. Alok Mandal, who is our collaborator in this project, and Dr. Deepak Singla, who is also a co-author and helped me to learn all this technique. I want to thank the CSIR for giving me opportunity to work in such an excellent lab, and also thank the ICMR for providing me fellowship while I was doing my PhD. And with that, I will be happy to take question, and feel free to connect me over the networking site if you have anything related to my work, or I can help you with some of the questions that you might have related to drug-like molecules. And I'll be happy to take more questions right now and ending my slideshow here. Thank you. So I'm not sure how we are going to take question. Is this going to be in the chat box, or someone can like unmute themselves, or they can ask this question, or are there no questions?
Hello, sir.
Yeah, hello.
This is Nidhi here. I wanted to ask that you told about the screening of the molecules. So how do we exactly do it? Like on what basis do we screen these molecules on Campbell? And so how did you manage to do like 12 million and 20 million molecules and say that they were drug-like? Like on what basis did you conclude that?
So I was already explaining the model that we developed. So our model is based upon classifying the approved drug. So in indirect way, it would be a way to say how close this all the chemical molecule are related to the approved drug. If they are having the same kind of the chemical patterns that are there in the approved drug, they would be classified as the drug like.
Okay, okay. So, like on these databases, we could also have the patterns, and we could also find these approved drugs also, so we can compare them with the
Yes,
patterns. Okay, thank you.
you're welcome.
Any other question?
Hello, sir.
Yes, you please ask.
Sir, I'm Anamika from BBAU. I have a question. You told us about Lipinski rule of five,
Yeah.
and I just want to ask, is the rule applicable for all type of drugs, means for all diseases, or is confined to any specific field or part?
So if you go the fundamental of the Lipinski rule of five is more of a like the drug which are taken orally. So it's working most of the time because of lipophilic index and the molecular weight, the small molecular weight, the hydrogen bond acceptance and donor combination. So it works very well with the oral drug, but it is not an universal. It is not going to work with, let's say, for natural compound. It's not going to work for many of the antibiotic. So it worked pretty good in some cases, but there are many approved drugs which are breaching this rule, and still they are drug, and they are already approved one.
Okay, okay. Thank you, sir.
Yeah.
Hello.
Yeah.
Yes,
Hello.
please
Yeah.
introduce yourself and then ask.
Yeah. Hello. Good morning, sir. I am Suyash from Naipur, Kolkata. So I have a
Mhm.
question. Like you told that we need to remove, like, if there is high correlation between two class of descriptors. So
Yeah.
what kind of problem we can see when we are considering those descriptors in our model? Means,
It will depend if I go in the detail that it will depend upon what kind of machine learning model you are choosing. Let's say if you are choosing the random forest, that they might not interfere anything. Okay, but if you are going to use like something like support vector machine that's going to come up with an algorithm at the end which combine the contribution from a different feature. So one
yeah.
feature is contributing that is already been contributed by the another feature. So that means it's not going to be helpful, and additionally going to cause some noise in the model.
Okay, so this will be in the case of like will we face any problem like when we are making classification model or or in the regression model? Means,
And
is there
it
any?
will be the same either you are creating a regression or the classifier model is not going to make any difference, but the information that is provided by the one feature, if the same information is provided by one other feature, that is not going to add into the performance.
Okay, so means we need to look into the which algorithm we are going to use when we are facing this kind of problem.
Yes, and the algorithm, if we always prefer to have the less number of features so that we can explain how our model is doing. So if we have, let's just say, only one or two feature, then we can directly correlate and then we can explain our model is working because it's kind of based upon these two features. It take like edit them, is subtract them, is going to use them in a way which is easy to explain.
Okay, thank you, sir.
You're welcome.
Anyone else want to interact? So some people are asking question in the chat box.
Mhm.
Do you want me to read or you are having?
Yeah, I can also read if that's okay.
Yeah, you can. So somebody is writing that at our level, how can we use machine learning technology?
Yeah, so I'm not sure about what do you mean by our lab level. So I have already used it at my lab level. So if I could use it for my very first project in the PhD or when the very first project while I was introduced to the research. So almost every lab could use it then, right? Because I did not come from a computational background. I came from a biological background. Then I start learning the programming and could implement it in my PhD program. So I would definitely say you can do it by your lab level. You need to understand what kind of problem you are going to address with the ML technology. The problem is more important than the technology itself.
Okay, and if somebody is writing, if we have some ligand molecule from binding DB database, can we generate QSAR model and can we use it for screening?
So obviously once we have this kind of molecule and they have either a IC50 value if they are binding ligands, right? So if they have IC50 value, then we can obviously create the QSR model, which is based upon the regression model in machine learning. Yes, and if you can also put them a threshold like less than this IC50 value, we are going to consider the positive hit, and the other than we are going to negative hit, then you can generate the QSR model for the binary classification.
So yes, Adhikari is asking, Weka tools can be used for this type of analysis to build a model or not?
Yes, you can
WEK.
do the Weka tool to build the model or to select the feature. Yes.
Okay. And Wasim is asking, sir, in PSA plot, what is the base of plot PSA1 and PSA2? What is the base?
PCA1 or PCA1, the base is like the PCA model is a model where it transforms your values, the transform your feature into low dimensionality. The low dimensionality means the first feature is going to explain the highest variability, and the next is going to explain the second most variability explained by a single feature. It's a transformed feature. So once we plot the PCA1 and PCA, that means you are already explaining the most of the variability in your data.
So Senthil Raja is explaining his question again. He's saying that, I mean, what is the basic level machine learning software available free of cost to carry out our work?
Yeah, the similar question asked by some other participant about the Weka. So the Weka is already free and it's easy to implement. It has graphical user interface. So only you need to have a data set in your hand and you can practice. And if you do not have data set in your hand, there are also some example data set given with the Weka that you can start practicing with and understand the concept and then implement on your model, on your lab work.
Okay, anyone else, if they want to ask any question, they can always write to Dr. Sandeep Kumar Dhanda to his email.
Yeah, so feel free to reach me out over the networking site, let's say LinkedIn or any other networking site that you feel comfortable with, or you can write email to me. So if you think like some of the participants asking, can we take help from you? Yes, I'm happy to help if I could do something for you, and feel free to interact or reach me out for your questions.
Okay. So now this talk is over. We will continue for the hands-on session within 5 minutes.
All right. And with that, I want to thank all the organizer and the leadership in the NIPER Guwahati and all the MMTT team for giving me this opportunity. And a special thank you to Dr. Srivastava for extending this invitation to me. Thank you, sir.
Thank you, Dr. Dhanda, for a very nice and informative talk. Thank you. So all the hands-on participants should stay, and Dr. Dhanda will continue hands-on. And all other participants can see it on YouTube Live and on Microsoft Teams. Many people are saying that
so
they
are
are
going to continue with the same link, right?
Same link.
All right.
So if you are not able to connect to the Microsoft Teams, probably you are using it through your browser. You should use it only
I'm
through
using the app, so I think I should
not
connect.
Some of the participants they are saying, so maybe you can watch it on YouTube, this hands-on session, if you are not able to connect. There is no difference.
Yeah, sure,
you can watch it on. Okay, so then. So now we. Yes.
In my demo, I would be talking about the very same concept that I was talking in my talk. So this session will be about how I did all this machine learning model and how did I come up with this model. So I will start with the very first thing, that download the data and where could I find the data and how you can download it and what's the format and how did I convert it. Once I had this format in hand, how did I make the feature out of it? And once we have the feature in hand, how we can make the machine learning models. So I will touch base upon all this part one by one. And with that, let's starting with the first problem, that finding the real data set or finding the new data set. And I think I can share my screen again. And I'm not sure where can I see a desktop window. So if I share it again, then I assume my old desktop will be visible, right? So I will just close all this up and open a new. So now you see I am opening just drug bank here. So drug bank is a database which enlists all the molecules which are already approved or running in the clinical trial in experimental, or are they under the investigation phase, still in the preclinical phase, or they are withdrawn. So I mentioned all of this stuff and you can find them all here in structure, and you can download this structure in the SDF format, which is the one of the format that I have used. but there are another format that you can use for the similar purpose. It could be SDF, MOL, MOL2, PDF, or Smile. So you don't need to worry about the format much about these days. And then you can download either all the drug from here, or you can just choose all the drug where we have the 3D information, or the approved one, or the experimental one. In our case, I have downloaded the approved and the experimental drug while I was doing this kind of analysis. And you can also find the same kind of data set that we have used, the exact same data set in our DrugMint homepage. And if you just search for DrugMint, it will land up in the same homepage where you can find the data set. And these are all the data set that we have used, and we explain how we perform this kind of analysis. And these are the main data set classifying the approved, experimental, or this is what the independent one. And from here you can just download from this link. So you can just go ahead and download this slide and this SDF file from either from here, if you want to go with the old version, because we have downloaded from the 2.5 and now it is 5.1. So the latest would be way more comprehensive. So you can download this set from here. And once I did it, so I just close this up. And then I open a new one, and this is the site where I have this downloaded. So in this approved drug, we have this approved drug, and you want to open it up, you can open it in any of the, the editor. Yes.
Hello, sir. Can you tell a little bit slowly, sir?
Okay, so the first point that we were doing is to find out a data set, right? And to find out a data set, we have used in this case is a data from drug bank. So you can search this drug bank data at this website. If you just Google drug bank, it will help you to go on this link, and from there you can visit the download. And in the download, you can go to the structure part, right? And in the structure, you can find out all this information related to approved drug, experimental drug, nutraceutical, illicit, withdrawn, investigational, that you can download from here. In alternatively, that if you want to do what we have done, so you can download our data set from these link. This is the link that you can find out on the DrugMint website. So you just Google for DrugMint, and it will link you to this data set where you can go to the data set and download it from here. So with that, I assume now you have downloaded the SDF file for positive and negative example, and the positive example in our case is approved drug, and the negative example is experimental drugs. And once you have downloaded that one, you can see that kind of data that I have already downloaded, and you can find that out in this directory here. And this is the SDF format. And the SDF format means it will have few lines where it explains the name of the drug. Then it will have the starting point here where it has different coordinates, and this coordinate explain the different, let's say, elements and what's their feature space right there. So we are not going to go to see all of this file. So that is a way of writing the SDF format. Then the next thing that we are supposed to do is to convert this structure file into the numbers, and that we call features. We can do that by visiting another software. We call them Paddle. So if you search for Paddle software, I think Paddle is something different. We need to type Paddle software. Then we will end with Paddle descriptor. So to convert your structure into the numbers, for the fingerprints or 2D or 1D information, you need to download this software. That you can do from this website, and you can download it from here. And if you have already downloaded it, which I have done, I will show you how you can do it. and it will require the Java to be installed on your computer. So if you not have installed Java, then you need to install the Java from here and the software from here. So once you will download this pedal software, what you will get at the end is these many files. So once you will download and unzip, you will see these many files are downloaded there. Okay, so you can go ahead and check what is there in the descriptor.xls, what is there in the descriptor.xml, what is the license information or the different library that it is using. So rather than going in the details of this particular software, how it was built, what it does, so we are most focused on how we can use it for our list of chemical. So for that, as I mentioned earlier, you need to have Java on your machine. And once you have Java on your machine, you can type Java open with -jar and then open this particular jar file. So this is a command so that you can open a paddle descriptor. So once you press enter and it will end up on this page. On this page, that means your software is already installed and it is running on your machine. And how to use this one? So if you see the description here, it mentioned you the molecular directory file, where is a directory where it can use to create the feature from that chemical list. So you can provide a location to the directory, or you can provide a descriptor output file. What is the output file that you want to use, and what kind of feature you want to extract out of here. So either you can extract 1D information, 2D information, or the 3D that remove salt and detect aromacity. So all of this stuff by default are the really useful. You can just go ahead and select this one, or you can also go in the advanced one, like I want to have this kind of thread or that thread. So based upon the capacity of your computer itself as well, or the retain order of the molecule. And with that, you can also select the 1D and the 2D information, like all the parameters from here, or you can also select the 3D. If you are going to select all the 3D, that is going to take much of the time. So it's better to unselect all of them for the demo purpose. But if you want to select them, you can also use them as the input feature. And this is the list of fingerprint. So by default, it has only the pubchem. So let's go with the pubchem only. I don't want to select all of them because that will create a huge list of feature and that we might not be able to use at this point. So this is how you can use the paddle software. And once you have selected everything from there, then you can define your molecule directory as the input file. So you need to provide input here. The input here is the directory which contain the structures, the structure related to positive sample and the negative samples. So I will just pick one of them. I know these are in download and I have the approved drug and I also have the experimental drug. The experimental drugs are like I have chosen only a few of them. So I will select the experimental drug and let's say select this one. Then I will define my output where I want to save the output. Then I say there is an output directory already in my download. I want to use that output directory and this is the name I want to use. Okay, so it's going to create a CSV file, but you can also create CSV file further into the format that you are going to use with the machine learning model. So in this case, you can just select the experimental feature output, whatever the feature the name you want to give, and then just say save. So once you have defined your input and output, the rest of the thing you can select from here that we have already talked about. I have just deselect most of the 3D so that we can run it in a given time in the demo session. And then we just picked only one of the fingerprint. In our case, I picked more than 10 and I run it again and over and again. I don't want to do that kind of exercise here. And then once we have selected everything, then we will hit start and it will start creating the feature out of the SDF file that we downloaded either from DrugBank or DrugMint. So in this case, I just picked only 32 samples from the experimental drug. That means I am not using the 3200 that were there. And it took only, let's say, 17 seconds to create the feature from my input file. I will show them in a CSV file, in an Excel sheet, how these are converting the features.
Yeah, hello.
Yeah.
Sir, like in this pedal, there are three different options like 1D, 2D, 3D, and fingerprint. So, what criteria should we follow? Whether we should calculate all the descriptors, or we should only specify like which descriptors we want to calculate?
Yeah, so that's a very interesting question. You can do it in two different kind of experiment. The one, when you know this is going to be relevant to my prediction, right? Okay. So that you can obviously go with those features at the first step. And when you do not know what feature is going to be helpful in my data set, in that case, you can select all of them and then select based upon the knowledge that you are getting from your data set, the supervised feature section.
Okay. Means after performing this descriptor calculation, we can use those two methods to select like what are the descriptors which are correlating. One is
yes.
two methods we have shown in
I just use two of them, but there is a huge list. Okay. You can even be more creative.
Okay. Thank you.
All right. So in my download, I'm expecting an output folder, which is right there. And I said I have already done this exercise because I don't want to run in hassle in the demo, so that I could show something useful to you. So I already done this exercise and I will show what is there in the input feature. So now this is our CSV file. Now you all understand the Excel format, right? So this was the name of the first molecule in the experimental drug, and this is a number of acid, A log P, or all these different values. And this is the value which we got after running this SDF file coming from experimental data set. These are the 32 in total. And these are the different value that we got. And this is the different for NB, count for B, count for C, count for N, count for O, sulfur, phosphorus, and all these numbers. And then we have this another feature called ATS01. I don't understand all of them, but I just see there are a number given for each molecule, right? And now we have converted our structure into certain numbers. And if you see how many of them, so there is a huge list. And these are the number of bonds, there are number of bonds in two, number of like, different way of calculating the number of bonds. And these are all the numbers that are there for all the descriptor that we selected. And this is the hydrogen bond acceptor, hydrogen bond donor, and all those parameters that are relevant to a chemical. And now again you see 1D, 2D, and at the end we will see our PubChem descriptors. I just moving on the right side. And these are number of rings found in the number of heteroatoms, rotatable bond found in each molecule. And with that, we end up with these many features. So if we count this number is around more than 1400. If we not even selected the 3D and many of the fingerprint, if we would have selected all of them, it would have been more than 10,000. So this is how we can generate a numerical data out of chemical structures. So with that, I will just close this up. Now we have come down to our creating the feature space step 3. So are you able to follow this up?
Yes,
up
sir.
To step 3?
Yes, sir.
Great. So if you do not have any question, then I will go to the next step, how you can select the most prominent one, how you can build the model. That I'll be using only the Weka in this case. So if you have not downloaded the Weka, you can download the Weka from here. You just type Weka and you can download this tool from this website. And that's very easy to download. You can just click here and it will be downloaded on your computer. I have already done it before, And if you have downloaded it, so you can open this up. I will try to see if I can open it directly. So this is the Weka that I have. And I just opened this one, and now it is opening a pop-up where I can choose from Explorer, Experimenter, Knowledge Flow, all of this stuff. And in the same way, we have created the feature for positive example. In the same way, we can create it for a negative example or the positive example for both of them. And then we will add a class. These are for the positive and these are for the negative, and we will combine them together. So Weka will take a file where we have combined the feature from the positive and the negative, and we have already defined the class. That means we have already added, this is our positive example, this is our negative example, and this information is right there in one of the columns. So I have already created a CSV file which combined features from approved drug and feature from the experimental drug, that I will open from the open file that is right there, and I will try to find out where is that. So you can convert it into the ARF format, but you can also use the CSV format if you have already a CSV file. So that is up to you. That is not going to make a big difference.
Hello.
Right? Yeah.
Sir, why you are calculating descriptors for your positive and negative data set separately? Why not combine?
Yes, we can do it at the same time, but again, sometime like at that time, if I remember it correctly, we were not able to have like this information in the output. If we have this information in the output, then we can already change this column into the positive and the negative. But if we didn't have this kind of information, I think that was the reason I calculated it differently. But yes, you can do it in the same run.
Okay.
Yeah,
so
and that might be like I did not
providing
understand the complete concept that time, and I started to calculate it differently.
Okay, thank you. Means yeah, I think maybe drug bank was providing in a separate column, like for experimental, for approved, for withdrawn.
Yeah, that could be the another reason to do it separately, but even though it's already a SDF file, so you can concatenate this file and you can do it in the same run.
Yes.
But you just need to remember what are my positive example, what are my negative example. So you need to add a additional column here, which says these are my approved one, these are my experimental one, or my positive or the negative examples.
So we need to convert that into the numerical value 0 or 1, or we can just simply keep it.
For Weka, you can just use the name itself. And for another software, let's say SVM Lite, or maybe for another software, you might need to convert that into 1 or 0.
Okay. Thank you.
You're welcome. So already, so I have converted this into the format that it will accept. And I just said from the open file, you can choose it from the format, and the ARFA format is no different from the CSV. We can also choose from the CSV. It is the same format, but written differently. So now you see these are the different attribute 1, 2, that were around 1400 that we just discussed. So all these 1400 are here, and at the end I have added another column, class. So that means 1 or 0, or you can add approved or experimental. So it will not make any difference if you add 1 or 0 or this one, right? So this is our CSV file.
So
or if we had done it from the,
sorry to interrupt you. So can you show us the approved drug, the output file of approved and experiment drug file that you are opening over
yeah,
here?
this was the output file from the descriptor calculation.
Okay. So you just said that you actually combined both of them, like the experiment one and the approved one. So how did you do that?
So you
Because
can just
that
copy
is the
and
file
paste
you
at
opened
the
up.
bottom of it. That's what the only thing.
Pardon? Can you repeat?
You can just paste the data from your another class at the bottom of the sample from the first class.
Oh, okay. So we can just paste the data below the.
Yes, let me open that up and show you the
Yes.
example right there. the exact one which I was doing. Where is the output file? Let me see what is the name. I forget the name of the file. Approved experimental. Yeah, so this one is the CSV file. So it open in another app from the Mac, which is the same like Excel sheet, and it has the data from the first data set and then a similar data set from the another one. This is only for the approved. So I can just select everything from there and copy and paste it at the end of the file that we have the data from the experimental one. So there will be exactly the same, the column will be in the same order. So we don't need to worry about whether we are matching up in the data merging. So we have created in the same way. So all the columns should be in the same order.
Thank you, sir. I got it. And hello, sir.
Yeah.
And so here we have to make one more column like for approved and then experimental below column, so that we can recognize which drugs are approved and which are experimental.
Yes. So in case of CSV file, it's better to do it at the end if you are using the Weka software. But if you are using any other column, then while reading it in the Weka software, you need to define this is the column which contains the class.
So there is a column class referred at the end.
Yeah, so this is what you can see in this file here. So these are all the attributes, the attribute 1, 2, 3, or you can name it anything, which are very similar coming from the same data here. And at the end, you will see a class. And if I could open the CSV file, then I can exactly show what it was there.
Yes, sir. That is what I actually wanted to see.
Yeah, so these are the same feature. Now you can see the same names from the while I was reading from a CSV file. The first column is name, the second is an acid, and at the end I have added this class column which says approved and experimental.
Okay. Thank you, sir.
And we understand that this column is not useful and not providing any information, so it's better to delete the first column which is related to the name. So we are starting with removing the first column. Now we have all this column that I have shown you here in the Excel sheet, starting from here to the end, around 1400 of them, and these explain everything. At the end we have added just another column for class and experimental and approved. Okay, so these are all experimental, so you can just drag up to the experimental and then you can add the approved.
And then we can add approved one, copy paste all the data.
And then you can drag and paste all these values from the approved data set that you have calculated differently. But I'm not explaining all these steps one by one because then we will lose all this 1 hour in just data transformation rather than building the model. Okay, so I will go ahead with the next step, and if you see at the end, which is a class, and these were the example that I'm starting with 22 sample here from the approved and 32 from the experimental, so that we can see there is a slight difference. And you can also visualize which are the feature most contributing to our discrimination between the positive and negative example. So you can see the A log P value is very different in approved and the experimental. You see the red dots here, green and blue dots here. So these are the showing how different is your approved and experimental data. And you can easily find out which feature are going to be most contributing from the visualization part. But if you are not interested to go in the detail, you just wanted to select some attributes. So there is another tab here, select attributes, and these are the by default algorithm. So we use the same CF set eval in this case, but there is a set of algorithm that you can start with. And there is also a remove useless algorithm that you can find it from here, or you can also find it from the another system. Okay, so rather than going with all this list, I will just say go with the default for starting, and we have also used the by default option. And once you have already uploaded your data, and you can then select the select attributes, and then you can hit start. Then it started with the total number of attribute or total number of feature at 1445. And after running for a few seconds, it has given you only the 16 feature. So these are the 16 feature that you can use. This is the name, the anatomic, this anatomic LCTA, mean I, these I don't understand all of them, but these 16 feature contains the information that is different in approved and the experimental drugs. And you can build your model just based upon this 16 feature. And similarly, you can also build your model based upon all the features that were there. And for building the model, so if I go in my slides, so this is the part I'm talking about, creating the feature space. We have already discussed like 1400. And we have created the space, and we are selecting the most prominent one. So this is called the feature selection. And we can easily find out the top 16 features that are contributing to our feature. In the next step, you can perform the building the model and the cross validation, and then I will go touch based upon the performance evaluation. So let's go ahead with the model building. So right now, either you can save this data set from here. If you right click, and then you can save the buffer, or you can visualize the reduced data, or you can save the reduced data that you can do all this thing, everything from here. Or you can reapply the feature selection algorithm what you want to reapply. So if you want to see all the feature, you can save the reduced data, and then you can upload it again. And let's select reduced data, and I am saying it in my home. And you can go back again, and then you need to find out where is your reduced data. And that is the system that I do not understand why it is not showing the reduced data right now, because we have selected ARFF, not selected the ARFF one. That's weird. We are expecting to show it the reduced dataset file right there. No, where is that file? Anyways, if it is not showing it up here, I think I have not saved it properly. That's what I can do it again, or though I was very careful in saving it in the right place. Save reduced data, and let's say I'm saving it on the desktop. Will it allow me to save on the desktop? Yes. Okay, so in that case, I will go pre-process and see if I can select it from the desktop. That's weird about it. I could not understand completely why it is not showing up me that file that we just saved. And I remember it, we saved it on the desktop. Anyways, you can figure that out, what's going on there, what I'm not doing properly. But the real purpose here is to rerun, kind of reloading the file. So once you will reload the file, then you can go to the classify model. So rather than building our model on the reduced feature, I will show you in demo how you can build it on all the feature. It will be very similar to do it on the reduced feature set. And here you can choose the different machine learning models. by default, let's say Bayesian net, these are the different Bayesian algorithm, or in the function SMO is relevant to SMO is machine learning model, that is support vector machine classifier, and you can read the detail if you just go and mouse over that particular name. And this is voting perception. Similarly, we have the random forest, we have meta, we have woods based or the tree based. So in our case, we have used the SMO or the support vector machine, and you can just select SMO from here. And then it will automatically pick up what kind of option are by default, but you can also play around and change any of the option that you wanted to choose or you wanted to select or change. And if you go click there, you can perform like one of the things that I was mentioning, the different kernels. So you can choose different kernel. One of the kernel is RBF, polynomial, or this stuff. And for practice purpose, we can just go with the default one. All right, so I'm not showing all those detail, and then you can say I want to cross validate it based upon the 10-fold. You can change the 5-fold, 10-fold, or leave one out or percentage split, or you can also supply your own training or own test set so that you can train on the data that you have defined by yourself rather than what is defined by the Veka. And once you have picked all this parameter, then go and hit start, and it will say a NN value was generated while normalizing VPR. It say OK, and we do see OK, it's not running because there are some empty or NN values. So that means our feature was not accurate. So that's why it's not creating running or reading them properly. So if we have the reduced feature set, then we would have used that as a better one. So if I choose the another algorithm, let's say Bayesian, will it run? So I just picked another one. Will it run for that one? Yeah, it is running for this one. So anyways, if our SMO, we could run the SMO. I don't know what feature that we are not doing it properly. So some of the feature is having the value that is not readable by the SMO algorithm. That's why I picked the another Bayesian algorithm. And in this case, once we have 22 approved drug and 32 experimental drug, this is the evaluation metric that we can use. And now we are on this step, cross validation and the performance evaluation. Cross validation, we just picked 5-fold, 10-fold for internal cross validation. And we can also use our training set and the spy test set for external cross validation. And moving on further with the performance evaluation that is shown here in the slide at the end related to performance evaluation and implementation of model. So while performance evaluation, you need to take care of these numbers. And this is the MCC value that we discussed. This is the ROC area. And these are the true positive, false positive rate calculated from this number.
Hello.
Yeah.
Sir, what while choosing the algorithm, like for model development, what criteria should we follow? Like it's completely on like where we are getting the better correlation, or there is something else?
I personally do it by where we are getting the best performance, but okay, they can also go based upon where it is easy to explain. Let's say the linear model are easy to explain, but they might not be going the best performance, but you can explain it to someone who is working on the similar data set. If you ask me why we are getting this many, this is performance on 1400 features, so I won't be able to explain all of this stuff, right, going on their background.
Okay, that
so
is why
in that
we are
case, it would be better if you are
our...
using the very simplified or the linear model.
Okay. Means that is why we are filtering out the descriptors.
Correct.
Okay.
Okay. So this is the confusion matrix, which is related to true positive, false positive, true negative, and false negative. And this is the true positive number because we have 22 approved drug, and out of 17 of them are classified as A, which is approved drug, and 5 of them are classified as B, which is experimental drug or the non-drug like. So that means our 5 of the sample are classified as a false negative. And similarly, all our experimental drugs are classified into the experimental one, which is non-drug like. So all of them are true negative. There is no false positive here, which is 0. And based upon all these 4 number, we can calculate all this parameter, MCC, this sensitivity, specificity, or accuracy for that matter. But for balancing data set, we can just use the MCC one.
Sir,
And
can you
this is
please
the
explain
AUC.
again the confusion matrix?
Sorry?
Can you please explain this confusion matrix again?
Okay,
More time.
confusion matrix is a combination of 4 numbers in this case.
Yeah.
In this case, 4 number because we are running a binary classifier. It could be even more if we have more classes.
Okay.
So in confusion matrix, this is A and B. How many times A means approved drugs are A and predicted as A. So that number is 17. How many times the approved drug are classified as B? That means this is false negative. And similarly, this is a false positive, which is 0 in this case, and this is true negative. So these are the 4 numbers: true positive, false positive, true negative, and false negative, which constitute all the number in our data set, and from where we can calculate the different matrices that I shown in my slide, and I can just revisit that slide. So based upon all these 4 numbers, using this kind of equation, we can calculate the sensitivity, because now we know the TP, true positive and false positive numbers, right? Now we understand specificity, we can calculate this number. Similarly, we can calculate accuracy, MCC, all those stuff we can calculate. And we, based upon, this is coming from a threshold by default, which is like 0.5 in Veka. If we allow to vary the threshold, then we can also calculate the AUC or the area under curve by ourselves. But Veka is giving it by default, and so the area under curve for this one is this 0.9. Okay.
So we can use this data of ROC to plot also, just the way you showed us that ROC, AOC, and
right now I'm not sure it is allowing us to plot directly from here, but if you can just copy and paste it in the Excel, you can easily plot it.
Yeah, we can do that also, right? We can just copy
But it
paste
is not allowing to directly plot the data from this point.
Okay. Also, sir, what I was asking is that the confusion matrix, like on what basis did this Veka, just plotted out that these 17 numbers of molecules are drug-like, that is true positive, then 0 are false positive. So how, on what basis did they do, like? It is just because we did. Okay, sorry. So
no,
it
go
was,
ahead. I want to understand your question first.
Yeah. So did they do on the basis of the ML which we chose, that is base, and or maybe we could have done SMO and it could have shown us different, or
Correct.
on what basis? Like, I didn't understand that part.
Okay, so let me choose another algorithm that will answer one of your question, and then we will come to the next question, right? So I will choose one of the trees, and for the random forest that I will pick, and then I will hit start, and then it will take some time, and now we are seeing a different matrix. So that means it is based upon the machine learning, which answer your one part of the question. The next part of question, how it does. So how it does means it is using one of that machine learning and see based upon this feature and using this algorithm, how we are correctly classifying our positive example are picked up here on the A part. And similarly, it then start with the negative example, how we are doing with our negative example. And if you are predicting them correctly, though, it will put it here, otherwise it will put on the other side. So it is doing based upon the machine learning and a threshold.
Right, sir. So these models we have selected, and that's why it is showing us this. But then how do we know that what kind of ML do we select or model do we select for our purpose?
Correct. So in this case, if we just compare, we have only 2 algorithms. Our SMO is not working for some reason. So let's say our Bayesian and random forest, we have 2 algorithms. So we can easily pick based upon the performance. And the performance, if you compare, let's the standard of comparison is MCC or the AUC curve. So you can pick any one of them. And the AUC curve for random forest is 0.997, which is 0.944 in case of Bayesian network. So we are already having a better performance with the random forest. But again, the question comes with both of these model are tricky. I cannot explain the details of it at running at the background, right?
Yes, right.
If we had just a small feature set, then we might be able to explain it. So in that case, if you can explain it, go with the easier model. And if you could not explain it, go with the better performance.
Okay, sir. Thank you.
All right, so with that all understanding in mind, now we can we come to a point where we can pick our model, we can see how we are performing, how we are doing, and this is all stuff we have done in our lecture first, then we have seen the demo part. And once we have this model, then we can save this model. Even from Weka, or we use another algorithm there. From here, if you right click and you can save this model. So once you can save this model, you can also load this model again, so that you can predict on the independent data set, or you can also perform it based upon the screening that I was showing. Somebody was asking how could I screen 12 million or 10 million compounds, because I load that model and I run all the structure and convert that structure into the numbers and then predict using loading this model. So this is what I did. So similarly, you can even save this model and apply this model while running a new sample set. And once you have this understanding of web implementation, you can implement your model saved from this point to the web server, so that if anybody submit their molecules there, at the back end it calculates their descriptor and then use the same model to make prediction based upon the molecules that they are providing. This is how we can do the implementation part, which we have done with the Drugment. And with that, I think I have completed with my demo stuff, and I also done with it, my presentation, and will be happy to take question and the discussion now.
So you were going to show us something, a graph which on your slide where there was margin in between. I don't know what you called that time,
Okay.
but there was some slide related. Right? You told you were going to show us something related to it.
Yeah, I think you are talking about the building the model stuff. So the building the model stuff, this is about the model building. So this is a representative figure which explains how these machine learnings are expanding the space between the positive or the negative samples, or the two classes of sample between them. So what they do, they take these dots that is right there from our plot. Let's say in this case it is here, and it is not visible to us how it is doing, but what it is doing actually is taking all these dots together, and we cannot discriminate them into our visible sense. But if we expand them to a huge space, if we throw them in a huge space, then we might be able to draw a line between them. That's what we call hyperplane in case of support vector machine, and these are called differently in different algorithm. So the purpose of a machine learning is to find out a hyperplane in case of support vector machine, so that you can see that there is a margin between the positive and the negative example. And between these two lines, the greater the margin, the better the prediction model to classify. So this is a representative figure to show you how these classification models are working mathematically. Is it clear?
Your voice is not clear.
Yes, sir.
Okay, so let me repeat it again. So I was talking about the support vector machine. How does this support vector machine classify? So we know that there is a plot that we have made out of our data, and we understand that based upon the feature that we have, our data is overlapping between positive and the negative examples. So we cannot easily draw a line between them. But if we throw them into a space using some mathematical equation, let's say multiply each value by 100 times, then if we have difference of, let's say, zero point 0.1, we might see that difference in a hyperdimensional space. So that is what this machine learning algorithm is doing, is throwing that data into the hyperdimension and then trying to find out a line that could discriminate between the positive and the negative example, so that you can find out those hyperplanes. It is called hyperplane, those lines where your positive and negative sample could be easily discriminated, and bigger the margin between those hyper and those planes is called as the discriminatory power of the model. So this is how you can create mathematically this model, but this thing is already running in the background while we are selecting this model at this Veka website on this Veka software. And based upon that margin, it is giving you the positive and the negative numbers, which is given right there in the true positive and the true negative sense.
Okay,
Anyone
yeah,
else
that's what I was asking you at that time, like on what basis it was, differentiating between these. I got it now. Thank you.
You're welcome.
So anyone else have any other question, or they want to interact with Dr. Dhanda? If not, then let's thank Dr. Dhanda for his very nice talk, followed by a very informative hands-on session. And I am sure it is very useful for all of us. And this video is available on YouTube. You can always watch and contact whenever it is required. Thank you, Dr. Dhanda. Thank you very much.
Thank you, Dr. Hemant, and it's been a pleasure to share my experience in your workshop and in your conference. And with that, I want to thank you for giving this opportunity, and thank you all the leadership for organizing the workshop. Thank you.
Thank you, sir.
Now we have lunch break. After that, there will be a talk by Professor Sam Deveser from University of Manchester, UK. That will start at 2:15 p.m. sharp Indian time. And then we will go for lunch now. So see you at 2:15 p.m. Hi Sam, this is Hemant here. Sam, can you hear me? Sam, you are muted.
No, I'm mute. Now I'm on off mute. Sorry. Okay. I hope you can see me.
Hi Sam. So this is Hemant. How are you?
I'm good. How's everything down there?
Yeah, good. So everything is working fine.
Going according to plan.
It looks like so. This is good actually.
Okay, I didn't manage to attend much so far, but but I hope it's been interesting.
Yeah. So your talk will be in another 1 hour and 8 minutes.
Okay, yeah, that's fine. That's what I calculated, didn't I? 8:45 my time. Yes, that's good.
So
no, I just wanted to double check. Just wanted to double check with you that I calculated the time difference correctly. That's why I mentioned that. So, so how do I share screen in this? Because I usually use Zoom.
So in sharing a screen, I will just.
Is that share tray? Is that share screen?
Yeah. So you can share it. That there are 3 dots. No, besides that.
Sorry.
There are 3 dots you can see on your screen in your Microsoft Teams app.
Yeah.
Beside that, there is, if you take your mouse there, you can see share screen.
Oh yeah, enter full screen. Yeah. Okay, it's all fine. We'll figure that out. So that's fine. That's all I need to know because yes, as I said, I usually use Zoom, so I haven't used Microsoft Teams that much. So I hope it will work.
This is also a very good platform.
Okay. Yeah, it should work the same way as what did I say, Zoom? So no problem. So you're still on your lunch break?
Yeah, it is lunch break, so it will be over in another 1 hour approximately. And immediately after lunch, the talk is scheduled.
Okay, that's fine. So I just keep my window open and I mute myself and I switch off my video.
Fine.
And then you just give a shout when it's my time. Okay.
And I got your detailed profile also. So see you in 1 hour.
Yeah. So is that all you needed to know?
Yeah. Yes. That's all.
Okay.
Thank you.
Okay, that's good. See you in an hour then.
Yeah.
Bye for now.
Good afternoon, everyone. Welcome to the post-lunch session of third day of MMTT 2021 International Workshop. In this session, the first talk will be given by Professor Sam Deveser, who is working in University of Manchester, UK. Sam did his PhD in 1997 from University of Amsterdam, Netherlands, and then from 1997 to 1999, he was a postdoc at King's College London. He also did his postdoctoral research in the Hebrew University of Jerusalem from 1999 to 2004. He has more than 250 publications in very high reputed international journals, including JACS, Enzymatic, and several others. They are all highly cited. He has H index of 65, and he has made very advanced and very useful research in the area of enzyme reactions using his QMMM calculations. Good morning, Sam.
Good morning, Hemant, and good morning, everybody who's on the international workshop. So thanks for inviting me to give a talk and give a chance to give some presentation on work we've done in my group. Can I share the screen? Can I just start? Will that work?
Yes, yes, please.
I'll try. Let's see if it works. Oops, sorry.
Yeah, it is working.
It's working. Okay, that's good. I hope you can see it. At least I can see it. So, and I hope you can hear me well over the long distance. So yes, we're also working from home here in England. We're in lockdown with all the situation, and in the background you see my kitchens, but we're still getting modeling done because computers are unaffected by this sort of viruses that spread the world. And my group has been doing some modeling on, and particularly as Hemant introduced, on enzymatic reaction mechanisms. So I'm going to give you a bit of a brief overview of the type of things we've been doing in our group over the years. And essentially the main focus in the group is twofold. First of all, we try to understand nature, so we look at natural enzymes and we try to understand how they operate. So these are, for instance, enzymes in the human body, in the liver, that metabolize drugs. There are also enzymes either in the human body or in bacteria or plants or whatever, involved in interesting biosynthesis reactions. Such as antibiotics or hormones or that type of things. And often these biosynthesis reactions, particularly, these are highly selective, sometimes regioselective or stereoselective or that type of selectivity. And we try to understand how nature triggers this selectivity, because sometimes it even attacks a non-favorable site of a substrate. And finally, I'm based in a biotechnology center, so I have a lot of collaborations with people who do biotechnology, and we also look at biotechnological applications, for instance, in biofuels. So I show you two fancy pictures at the bottom of the page, which were fronty pages in Chem European Journal issues. One where we studied the system where we investigated the metabolism of drugs by a Cytochrome P450 system, and the picture on the right is an enzyme, it's another P450 that picks up long chain fatty acids, and in one particular channel it does a decarboxylation to form a hydrocarbon, and of course a hydrocarbon is a biofuel. And I may, if I have time for that, I may show a bit on that system later on. In addition to that, we not only work on enzymes, we also work on synthetic model complexes, and that's mostly work we do with Professor Sastry and Professor Kumar in Guwahati and in Lucknow. And for instance, we've worked on this Sidon manganese peroxo system, and investigated how that reacts with substrates. We also worked on this iron oxo biomimetic systems, and these biomimetic systems have the coordination sphere of enzymatic active sites, but of course miss the protein around it. And when you remove the protein, sometimes that affects your reactivity dramatically. And that's how we understand how the first and the second coordination sphere of an active site, of an oxidant or a cofactor or whatever, affects reactivity patterns. And then here on the top right, we have an example where we studied an enzyme with quantum mechanics, molecular mechanics, QMMM, where we actually show that the second coordination sphere is very important to trigger a specific reaction mechanism of, in this case, an ALK-B repair reaction. So as I said, we do computational biochemistry or bioengineering, where we investigated mostly inorganic reaction mechanisms. So most of the systems we work on have a transition metal, which is usually iron, but we've also worked on manganese and a little bit of vanadium as well. So in general, what we look at is we try to understand how the reaction proceeds in nature, and either the real system, the enzyme, or in the biomimetic model system. We try to find out what is the rate determining step in the reaction, what establishes the active oxidant, and can we characterize short-lived species, which then can be characterized with experimental methods. So as soon as we understand the natural system, we then try to modify the natural system and engineer the system, and ideally improve the catalyst, or change the substrate selectivity or the products we get out of it, and we sometimes do that with bioengineering these proteins. So if you set up a model, and the model is of course the most important thing, it needs to reflect the real system. So one thing you can do is, of course, you can do QMMM, which is a very popular technique these days, but the QMMM is quite a risky technique to use, because first of all, you need to use the whole system. And when you have an enzyme, if the enzyme is just on its own in solution, then you can use the whole enzyme. But sometimes an enzyme is latched on the surface of a protein or a membrane. Sometimes the enzyme comes in a cluster, or it has a redox partner bound to it. So you may need all these extra proteins as well to get a good representation of the real system. Moreover, the QMMM has large groups far away. These may be wobbly, they may be moving, and that all affects your reactivity. So of course, if you're only interested in a reaction all the way in the center, then these outer regions may not be so important. So you can strip them away. So one thing when we set up a model, therefore, what we can get away with. So we typically use cluster models rather than QMMM, because in a cluster model all the atoms are described with the same method, a quantum mechanical method, and that's generally quite accurate. As soon as you do QMMM, you've got some atoms calculated with a very good method, other atoms calculated with a poor method like molecular mechanics, and then you need to question, how do I describe the border between the QM and the MM region, and where do I put the border? So obviously you can't cut through a double bond because there's charge smeared out over that double bond. All that sort of issues you need to take into consideration. So we do the same when we create a cluster model, and then I'm talking about cluster models of 100, 200, or sometimes even 300 atoms. And that's then the first and the second coordination sphere of your active site, as well as your substrate binding and positioning that you take into consideration. So we of course have, if we for instance have a metal center like here, an iron 4 oxo, then of course this iron has several first coordination sphere ligands in the axial and equatorial positions. And these ligands itself are not necessarily innocent, because sometimes one of these ligands can undergo a hydrogen bonding interaction with a nearby group, and this hydrogen bonding interaction can push charge to or from the equatorial ligands, which then also means that the iron charge is also affected, and that affects then your redox potential and your reactivity. So, for instance, that's an important issue that's, for instance, seen in the Cytochrome P450 enzymes, where you have a thiolate actual ligand. If you add some hydrogen bonding interactions to that thiolate ligand, you change the redox potential of your compound 1. In non-heme iron enzymes, there is an equatorial ligand with 2 carboxylate groups, typically an alpha-ketoglutarate. And of course, a carboxylate group likes to form salt bridges with, for instance, an arginine residue. So when you set up your model, you either need to include the whole salt bridge or not the salt bridge at all. So if you just take the dangling carboxylic acid group in your model, someone has done that once and discovered that there was suddenly radical character on that carboxylic acid group rather than an anionic form, and that's because if the salt bridge and this positive charge of the arginine is missing, then of course you miss your charge interaction of this carboxylic acid, and suddenly loses the overall charge sometimes. So it's very sensitive. If you see a salt bridge, you need to take it into the whole model. So these hydrogen bonding interactions and also charge interactions, so I've drawn here the K plus the atom or an ion. So if you see a K plus ion in your second coordination sphere, it's sometimes important to take that into consideration as well. So recent studies of us with the Vaibhav Dixit group from Pilani in India show that actually the redox potential of P450 systems is highly affected by the positioning and the number of these positively charged alkali ions in your second coordination sphere. So we need to take that into consideration. So there's a lot of things you need to look at when you set up a model, and if you missed one or two of those sort of features, you may have actually a wrong representation of the whole model. So that's what we try to do. We try to set up the models as good as we can. Often we test different type of size of models to make sure that the results are consistent and reproducible. And I'm going to give you a few examples of studies we did on specific cluster models of a few hundred atoms. So the first example I'm going to give you is a recent study we just published a couple of months ago in ACS Catalysis on the catalytic cycle of vanadium haloperoxidases. So vanadium haloperoxidases are an unusual set of enzymes because they have a vanadium atom. Now, vanadium is not an unusual metal on planet Earth. Its abundance is quite large, actually, and particularly in seawater, I've understood. But actually enzymes rarely use a vanadium atom. There are only 3 or 4 enzymes in nature that have that are known to have a vanadium ion in the active site. And one of them is the vanadium haloperoxidase. It's been crystallized. As you can see here, there's a crystal structure of this system, and in the resting state, this vanadium is 5 coordinated with 2 oxo groups, 2 hydroxo groups, and it is linked through this axial histidine group to the protein. So what experimentalists also know is that when they add hydrogen peroxide and an external proton, then they can actually characterize another species, and Sidon vanadium peroxo with also an oxo and a hydroxo, and this intermediate has been characterized, and they've suggested that it's probably a catalytic cycle intermediate, in the first stage in the reaction with hydrogen peroxide. And it's been proposed experimentally that probably the side of peroxo reacts with a halide, it could be a Cl- or a Br- or an I-, and then formed hypohalide. This is either then OCl- or HOCl. It's not exactly clear what is formed initially in the catalytic cycle, but on this center, this hypohalide is formed, which then drifts out of the enzyme, and on the enzyme surface there is a substrate bound that reacts with this hypohalide to form halogenated substrate. So we wanted to set up a cluster model for this reaction. So in principle, you can of course take this minimal model like I drew here in this ChemDraw drawing, which just the vanadium with its first coordination ligands, the two oxo groups, the two hydroxo groups, and an imidazole or something like that for the actual histidine, and then study its reaction with H2O2. Now the problem when you do that is when you compare it now with the crystal structure on the left-hand side, there are all sort of positive charge and hydrogen bonding interactions in the vicinity of this active vanadium cluster. So for instance, there's a positively charged lysine residue here on the left, which hydrogen bonds with one of these oxo groups of the vanadium center. There's another positively charged now an arginine residue, which also interacts directly with one of the oxo groups. In the back is another arginine residue, which interacts with the hydroxo group. There's an alcohol group of the serine hydrogen bonding nearby. There's also an aspartate in the binding pocket and a histidine in the back. And these dots, red dots, are all water molecules. So there's a big hydrogen bonding network down there. And the key thing is 3 positively charged residues very, very nearby this vanadium dioxo dihydroxo center. So we reasoned if we are going to run calculations on the catalytic cycle, then particularly these positively charged residues are going to be very important, and we should try to include them in the model. So we created 2 models. So the small model is in the blue circle, and all the residues outside the circle are in the even larger model. I think it's 200 atoms, the large model, yeah, 229. And it includes, of course, the vanadium dioxo dihydroxo with the actual histidine as methyl histidine, and the side chains of these positively charged residues, the 2 arginines, the lysine. And then we added a small peptide chain, ser-gly-his, which is in the binding pocket and where the serine hydrogen bonds to the hydroxo and the histidine hydrogen bonds to the other hydroxo. Of course, we don't know the protonation state of this histidine, so we did 2 sets of calculations. One where the histidine is singly protonated, and one calculation where the histidine is doubly protonated to consider a low pH situation. And then we also explored a bit larger model where we have the layer outside this inner coordination set also into account, which, as you see, has this phenylalanine. It has 1, 2, 3 proline residues, 3 water molecules, and this tryptophan chain and this aspartate chain. So we run calculations with, I'm only going to show data on the large model. The large and small model are more or less, give more or less the same results, but as I said, I trust the large model a little bit more. So when we do a geometry optimization of the large cluster, and I show that here on the right, where I overlay the optimized geometry of the large cluster, and that's colored in purple, with the original crystal structure coordinates, and then you can see that actually most of the residues are in more or less the same position as we see in the enzyme. So our cluster model still has the features of the active site of the enzyme, and that's one of the key things when you set up a model. you want to stay as close as possible to the features of the enzyme. You don't want change to move dramatically from one position to another position, because you don't know if that's possible in the enzyme with all the pressure of the third coordination sphere around it. Okay, so that's our starting model of the resting state, and we believe that it's close enough to the crystal structure, so that seems a reasonable geometry. And then, as I said, this first step of the catalytic cycle contains a proton transfer. Now, this is a bit messy figure, but the key thing is there are many different proton transfers possible in this particular system. So, as I mentioned, there's a protonated lysine, which could deliver a proton. There's a histidine, which could deliver a proton. There are two arginine residues that technically could deliver a proton. And then, of course, we also have hydrogen peroxide in the model that also could deliver a proton. So those are all the different proton transfer channels that we tried. We also considered one option where hydrogen peroxide first binds to the vanadium center before a proton transfer occurs, and I will mention that as well later on. I'm not going to show all the results on these different pathways because some of them are quite high in energy, and I'll focus on only the low energy pathways. So the lowest energy pathways was simply the proton transfer from the hydrogen peroxide. So sadly, no amino acid residue here that delivers a proton. All the amino acid residues kept their protonation states as in the resting state, according to our calculations. So the hydrogen peroxide preferably protonates the equatorial OH group to form a water molecule and OOH minus, which then binds to the vanadium center. Now, of course, this gives a 6-coordinate vanadium, which vanadium doesn't like, so it splits off a water molecule very rapidly to form back a 5-coordinated vanadium hydroperoxo species. And then the proton of this hydroperoxo species attacks the other OH group and forms another water molecule, which is also split off and then can form the Sidon vanadium peroxo species. So what we can see from this mechanism is that hydrogen peroxide can deliver a proton with a fairly small barrier of less than 5 kcal per mole and bind to the vanadium center to form a relatively stable vanadium hydroperoxo species. But the interesting bit is that actually this experimentally proposed Sidon vanadium peroxo species is not the lowest energy state in this stage of the mechanism. We find it actually higher in energy by about 6 kcal per mole or so than the Sidon vanadium hydroperoxo species. So we think it's actually a side product that's vanadium Sidon peroxo rather than an intermediate that is involved in the catalysis. As mentioned, we also tried, that's the red curve here at the top, we also tried hydrogen peroxide binding first to the vanadium before a proton transfer takes place. And as you can see, that's quite high in energy because you form a 6-coordinate vanadium species, and this vanadium hydroperoxide bond is relatively weak. Whereas with a hydroperoxide, you form a more stronger anionic bond. So we couldn't find the sensible pathways for that system. So next, so this was only the first half of the catalytic cycle where we use hydrogen peroxide and activate it on the vanadium center. And now we need to study the reaction with the halide, which we decided to do with the most stable structure, with the vanadium hydroperoxide, as well as with the Sidon vanadium peroxide. So if we attack the halide on the hydroperoxo species, then we get, as you see from this animation here in the bottom right, a very efficient OH transfer from the vanadium hydroperoxo to the halide. where it's essentially just the Cl moving from the oxygen to the halide efficiently, and it's more or less an OH plus transfer reaction, as you can see from the charge distributions which are drawn here, where we see that the incoming halide has lost charge. The charge on the halide dropped from -1 or went up from -1 to -0.36. So it picked up a little, or lost a little bit of electron density, and the OH is slightly positive, 0.15, whereas the charge on the oxo group has also gone down to 0.64. So this has a barrier of about 18 kcal per mole for halide transfer. So that's not a very high barrier. That's a doable energetics in enzymatic reaction mechanisms. And we then formed a hypohalide nearby the vanadium trioxohydroxo. Now, of course, this needs to pick up a proton from the protein somewhere to return back to our resting state, which is a vanadium dioxo. And this proton transfer from, I think it was from the nearby lysine residue, which was the lowest energy step in this case, led to for a small proton transfer barrier to our back to our resting state and hypohalide as our product. So we also, so yes, the HOCl is formed through an OH plus transfer from the vanadium hydroperoxo complex to a halide. So that is contradictory to experimental suggestion. That's that it should be a side-on vanadium peroxo that does that reaction. So we then try to find the transition state from the side-on vanadium peroxo with the halide, and actually found a barrier of more than 50 kcal per mole. So according to the calculations of this particular model complex, we can say that the side-on vanadium peroxo complex is a side product from a side reaction, and it doesn't react with halides to form a hypohalide. It is a vanadium hydroperoxo species that is the active species that reacts with halides, and it can be very easily formed if this hydrogen peroxide binds to this vanadium center and then reacts with the halide. So to recap the studies on the vanadium haloperoxidases, so we created various DFT cluster models, and one model had 229 atoms. And that model incorporated the first and second coordination sphere of the vanadium center, including a couple of charged residues in the second coordination sphere and key hydrogen bonding interactions in the second coordination sphere as well. The proposed vanadium peroxo intermediate that has been experimentally characterized is in the calculations not the active species that react with halide. We think it's a hydroperoxo species that reacts with halide through a very simple OH plus transfer to form hypohalide. An interesting result that comes from the calculations as well is that we don't see the vanadium change in oxidation states. So in this project we teamed up with Chris Blanford, who is an electrochemist, and Sam Hay, who's a spectroscopist, and Emily in my group, Emily Girard in my group, who is doing some experiment as well as computation on this system. And we were really hoping to have a vanadium 4+ system because that has a radical, but sadly there doesn't seem to be a change in oxidation state in this particular system. So we're still trying to do some experiments on this system, and Emily has made quite good progress with finding some reaction products and so on, and to confirm that the mechanism that we've proposed here is indeed sensible. Okay, so as I mentioned, electrostatic perturbations are quite important for reaction mechanisms. So I'm going to give another example where we use the cluster model, where these electrostatic perturbations are really important. So in this particular case, we look at a non-heme iron enzyme, and this particular non-heme iron enzyme is called TAMP-A. And it has uses this substrate where we have an ethane molecule with a phosphate group on one end and a trimethylamine terminus on the other end. And this molecule is part of a biosynthesis reaction in bacteria, because what it does, it does the hydroxylation on the C1 position of this carbon atom here, and as soon as it's hydroxylated on the one position, this phosphate group comes off, and you get an amine alcohol as a product, which is then used in a subsequent step of a biosynthesis reaction. Now, interestingly, there's a crystal structure with a substrate bound in the binding pocket. And when you look at the crystal structure, you see that this is the C1 atom down here. In light blue is the substrate. It is close to the iron here in orange, but also the 2 position and the methyl groups are actually quite close to the metal. So you would expect these could be activated as well, but surprisingly, those are not products that are being obtained. So we again set up a DFT cluster model that takes into consideration the oxidant and its near environment, as well as the substrate and the substrate binding pocket. So in this case, we have 242 atoms, where we have an iron oxo as the active species. So this iron is bound to 2 histidines in a carboxylate. So the actual histidine is abbreviated to imidazole, whereas the other histidine and the aspartic acid are part of a short chain we kept in the model of his, THR, ASP, ASN, pro, tyrosine, and all these residues that point into the active site that are all included in the model. Then we have another small chain from serine to asparagine, because that has an arginine group that was shown to interact with the phosphate group. So this phosphate group also interacts with 2 tyrosine phenol groups, which we also kept in the model. And then there's another small chain of an asparagine, leucine, alanine on the side of the trimethylamine we also included in the model. So we then ran the full optimizations of the hydrogen atom abstraction steps. So we try to abstract an hydrogen from the C1H bond. We try to abstract a hydrogen from the C2H bond, and we try to abstract a hydrogen atom from the methyl group of this trimethylamine substituent. And as you can see, the lowest energy barrier we find is of 11 kcal per mole for a hydrogen atom abstraction of the C1 position. So that matches experimental observation quite well, because that's the product that is being obtained experimentally. And a few kcal per mole higher, about 4, we have the energy for abstraction of a hydrogen atom from the methyl group of this trimethylamine group, and way higher in energy, almost 8 kcal per mole. We have the hydrogen atom abstraction energy from this C2 position. So the calculations reproduce experiments, so that's good news. So that means the model appears to be okay, and the model seems to be gives a reasonable explanation. So then we tried to understand the results a bit. So we took the substrate by itself, just the substrate in isolation, and we calculated the bond association free energies of the C1H, the C2H, and also the CH group of the methyl group. And when you just take the substrate in the gas phase, what you see is that the weakest bond is actually the C2H bond, and the C1H bond is way stronger. So that was a bit surprising result to us, because in the enzyme you get hydroxylation of the C1 position and not on the C2 position. So it seems to have done something against what you would expect from a gas phase bond dissociation energy. So what we then did is that why don't we put an external electric field on our substrate and recalculate the bond strengths of these 2 or 3 CH bonds. So that's what we did. So I have here a drawing of what we did. So we took the optimized geometry of the substrate, and we took the optimized geometry of the substrate minus a hydrogen atom, and then we did single points in Gaussian with an external electric field along either the X direction or the Y direction or the Z direction as specified here in the figure. And we also changed the magnitude of the field, so it ranges from, of course, 0 in the gas phase, which is no field, to about plus or 200 or minus 200, no, 0.2 plus 0.2 atomic units or minus 0.2 atomic units in electric field. And as you can see, the CH bond strengths are highly sensitive to the magnitude and the direction of the field, because when you apply a negative field, the weakest bond is the C1H bond, and when you have a positive field along the Y direction, your weakest bond is actually the C2H bond, like you see in the gas phase. So here's some examples here on the right hand side. With some factual numbers. So if we have plus, that should be 0.1 atomic unit in the Y direction, we have a very strong C1H bond of 144 kcal per mole and a much weaker CH bond of 96 for the C2H bond. So with an electric field of 0.1 along the Y direction, you would expect hydroxylation of the C2 position and not on the C1 position. If you then put a field along the negative direction of minus 0.1 atomic units, then you suddenly see that now the CH bond strength of the C1H bond is only 48 kcal per mole, whereas the C2H bond strength is 88 kcal per mole. So we suddenly see that the weakest bond is the C1H bond rather than the C2H bond. So an electric field along the Y direction in the negative direction on this substrate should make the C1H bond the weakest of the two, and you should get hydroxylation at that position. So we then wondered, how does the enzyme does that? Can the enzyme indeed affect the substrate CH bond in that type of way? Because in the enzyme we get C1H hydroxylation, not C2H hydroxylation, and it seems that the gas phase results predict the opposite. And indeed, when you look at the enzyme, there's a large dipole moment. So this orange vector here is the dipole moment in our cluster model, the optimized geometry of the reactant complex. And when you follow the vector more or less, you see it's more or less along the Y direction of this isolated species. So this the cluster model we created indeed creates a perturbation, an electric field perturbation along the C1H bond, and then favors C1H hydroxylation. And when you draw an electrostatic map, and that's this blob drawing here on the right. So here we show the charge distribution in the full protein. So this is just the PDB, nothing done to the PDB, and you see the negatively charged residues in red and the positively charged residues in blue, and as you see, there's a lot of negative charge in this system, so there must be a huge electric dipole moment working on the enzyme, and also an electric field effect as a consequence of that. And probably these charge distributions guide the substrate selectivity in this particular enzyme. So this is, as I said, the dipole moment with the model, and these are the charge distributions in the protein. So to summarize this TEMP-A results, we did DFT studies on this TEMP-A enzyme using a large 242 cluster model that includes the first and second coordination sphere of the enzyme and substrate binding pocket. That has all these key hydrogen bonding interactions that keep everything in place. We find the correct selectivity in comparison with experiment for C1H activation. Interestingly, the C2H activation would be expected in the gas phase without the protein around it. But when we look at this, the model as well as the full enzyme, we see electric field effects and electric dipole moments that may affect the individual CH bond strengths in the substrate and guide the selectivity due to their charge distributions and dipole moment into the right direction to trigger this C1H hydroxylation process. Okay, so I'm going back to talk a little bit on the Cytochrome P450 because the meeting is also about drug metabolism, I understood. So I wanted to highlight some data which we obtained on the P450s. So the P450s are liver enzymes that catalyze a lot of interesting reactions, and they metabolize drugs, for instance, in the liver, but they also detoxify xenobiotics and are even involved in the biosynthesis of hormones such as estrogen. And we did several studies of it, as you can see from this cover page, where we used a minimum cluster model of just the heme and a substrate and looked at what are the different pathways of a substrate activation, which channels can we go into. So the P450s are also iron enzymes. They contain a heme, as already mentioned, and the heme is linked to the protein through an iron-sulfur bond of a cysteine residue. And typically they use one molecule of oxygen, 2 electrons and 2 protons, and then stick an oxygen atom on the substrate to usually form an alcohol. So the catalytic cycle of the P450s is well known. So it starts from a resting state where your P450 heme is in the iron-3 state with the water bound in the distal ligand. When substrate comes into the binding pocket, this water molecule is released, the system is reduced and binds molecular oxygen to form an iron-3 superoxo. This then picks up another electron and a proton to form compound 0, which is the iron-3 hydroperoxo species. Now, in contrast to the vanadium haloperoxidases, this one, iron hydroperoxo, is not reactive, at least not that we know of. It just picks up a proton from the solvent to form compound 1, which is an iron-4 oxo heme cation radical species, and that species reacts with the substrate, usually by oxygen atom transfer. Now, most of these intermediates in the catalytic cycle are very relatively short-lived, particularly the ones where oxygen are bound and hence are difficult to study experimentally. And that's why doing modeling on these systems are quite useful, because that helps experimentalists understand their data and guide them with their work. So over the years, we studied many different possible reaction mechanisms. As I said, compound 1 reacts in many different ways, mostly oxygen atom transfer. So for instance, with aliphatic groups, it forms an alcohol with double bonds. It can form a spin state, a quartet and a doublet that are close in energy. And as such, there is a mechanism on the doublet and a mechanism on the quartet. The rate determining step, however, is usually the hydrogen atom abstraction, which is the first step. And after the hydrogen atom abstraction, the OH rebounds to the radical to form the alcohol. So as I said, we studied it a few years ago, 5-6 years ago, on this for some drug molecules such as this ethyl carbamate. which pharmacologists have shown can actually do two types of reactions. You can form hydroxylation of the terminal carbon atom, but there's also a possibility of a channel where you get a double bond in the ethyl group. And we studied the pathways leading to these two different product channels. So in general, there's a rate determining hydrogen atom abstraction leading to a radical intermediate, and then either there's a second hydrogen atom abstraction to form the double bond, or the OH rebounds to the radical to form the alcohol product. So when we did that for the minimal cluster model, we showed that on the doublet spin state, we have very small barriers for desaturation and hydroxylation, whereas on the quartet spin state, we have a relatively small barrier for OH rebound, but a very large barrier for desaturation. So based on these small model, cluster model reactions, we came to the conclusion that on one spin state we probably have a product mixture, whereas on the other spin state we have a hydroxylation pathway only. So clearly on the different spin states you sometimes have different product distributions as a result, which of course makes comparison to experiment a little bit difficult sometimes. Now these small cluster models, as I just mentioned, only had the heme and the substrate. It didn't take the substrate binding pocket into consideration, and that's actually quite important in particularly the P450s. So here I've drawn 3 substrate binding pockets of 3 more or less random P450 isozymes. So the first one is P450-COM, which binds COM4 and hydroxylates it selectively, and that's a bacterial enzyme. And as you can see, it's just the shape of the substrate binding pocket is essentially the shape of COM4 and the more or less spherical molecule. When we look at the middle structure, which is another isozyme P450-BM3, which is an enzyme that typically binds long-chain fatty acids. And then, as you see, this is a totally different substrate binding pocket, which is long and thin, and that accommodates, of course, these long-chain fatty acids. And the final structure I show here on the right is P450-2D6. That's a liver enzyme in humans, and of course this has a very large substrate binding pocket because it needs to accommodate as many different substrates as possible with various shapes and sizes, and as a result it is quite a large and open pocket, and clearly the substrate activation by these 3 different enzymes will be affected by the shape and the size of these substrate binding pockets. So yes, you can expect different product distributions. So one example of finding different product distributions in the P450s is what we studied in this particular project. So I had an undergraduate student who wanted to study cosmetics metabolism. So then I Googled what sort of compounds you find in cosmetics and discovered there are phthalates, which is this sort of molecule here in cosmetics, and some of those are actually metabolized by liver P450s. And as you can see from this scheme here, there are many different products you can get from bottom to right. We can get hydroxylation of the aromatic ring. We can get epoxidation of the aromatic ring here in the middle, or at the top we have 2 examples of aliphatic hydroxylation, one at the terminal chain here and one here more in the middle. So of course all these products vary dependent on the P450 isozyme that binds it, because in some the substrate will bind in a different orientation, and consequently you will get a different set of products. So clearly when you do study this sort of reaction, you need to take as much as possible of the shape of the substrate binding pocket into your model, which sometimes is problematic because that makes the model very large, but it does give you the possibility of finding your product distributions and matching them to experiment. So in one particular example, we recently did something like that. So this is not a human P450 because I don't think humans can eat wood. Lignin is part of wood, and fungi can biodegrade wood components. So now the P450s can't handle a complete lignin chain because it's a large polymer with a lot of different side chains. But if the lignin is chopped into small components by lignin peroxidases, for instance, you get small components like guaiacol or syringol, then these two compounds, they can actually be activated by P450s. And there is evidence from experimental work from, for instance, the Jennifer Dubois group in Montana, of these P450 GCoAs, that they react with these type of compounds and then give either a hemiacetal or an acetal as a product. So Hafiz in my group decided to investigate that mechanism using a large cluster model. So first of all, we looked at the isolated substrate and checked what is the bond strength of the various bonds, what is the most likely pathway we get. So we calculated the OH bond strength of the phenol and the CH bond strength of the methoxy group. And as you can see, the OH bond strength of the phenol is extremely weak, 76 kcal per mole, whereas the CH bond strength is much stronger, in the 90s, 93 kcal per mole. So clearly these two different bond strengths show that when the OH group points towards compound 1, then probably that's the only pathway you're going to get. You're only going to get OH abstraction and no CH3 activation. So if you want products originating from methoxy group activation, we're going to need to position the substrate OH bond away from the active center. So that's what we did. So we so clearly in the gas phase without perturbations in the protein substrate binding pocket, you would expect products of only OH bond activation. But as I mentioned, the experimental studies suggested also products from methoxy group activation. So clearly there must be substrate binding positions where the OH group points away and therefore get a different product channel. So we decided to create a cluster model that takes into account this substrate binding pocket. Sorry, I talk too much. Okay, and particularly all the key hydrogen bonding interactions of the model, the substrate binding pocket. So here's the model. How many atoms? 300 now. So I go up with the number of atoms. So in this case, we took the heme. So we kept most of the side chains, most of the aliphatic side chains of the heme in this particular model. We did chop off the carboxylate groups of the propionates because these form salt bridges with arginine residues, and we thought, well, if we want those, we also need the arginines, and we decided to keep them out. The cysteine NAT was abbreviated to methyl mercaptate. And then the substrate binding pocket was taken by these various chains. And so here, there's a chain starting with Val241 all the way going down to Glu249, which has this carboxylic acid group, which can donate hydrogen bonds, but also has some other, of course, peptide hydrogen bonding groups, but also aliphatic groups. We've got two phenylalanine side chains in the model, an isoleucine structure in the model, and another small chains here on the bottom right from isoleucine 292 till 309-296. So that's the model with the substrate. As I said, we want at least one substrate binding model where the phenol OH group points away from compound 1. So we have two conformations. structure A, where the OH points away and the CH3 points towards compound 1, and another model where both actually are bound close to compound 1. So we have two different substrate orientations for this particular cluster, and then subsequently using those two conformations, we studied the reactivity and the various products that could be obtained for those two orientations. So obviously in binding position A, where the phenol points away from compound 1, we only can get methoxy hydroxylation, and that's the only channel we see for this particular substrate binding orientation. For the other substrate binding orientation, we've got this very complicated landscape. Apologies for that. So we've got a compound 1 structure, as shown here in blue on the top left, where the OH group and the methoxy group both form a hydrogen bonding interaction with the oxo group of compound 1. So we then studied either hydrogen atom abstraction from the phenol group or hydrogen atom abstraction from the methyl group. So obviously hydrogen atom abstraction of the phenol group has very low barrier because the OH bond energy is very low, and indeed we only find barriers of about 1 or 2 kcal per mole for this particular step. If we abstract a hydrogen atom from the methoxy group, we get barriers which are more in line with what we normally see for aliphatic CH abstraction of around 13 to 17 kcal per mole, dependent on the spin state. Nevertheless, if we abstract a hydrogen atom, we get from either these two groups, we form a radical intermediate, either with a phenoxy radical, which is very low in energy, or a bit higher in energy, obviously, when we have a CH2 radical. Then in the next stage, we tried hydrogen atom abstraction from the other group. So after the phenoxy hydrogen atom abstraction, we then abstract a hydrogen atom from the methoxy group, which is very low in energy, that still has teeny tiny barriers and leads to a biradical on the substrate with a radical on the oxygen and the CH2 group and an iron-3 water system. And this system very quickly does a ring closure to form this acetal product and an iron-3 water, which of course is our resting state already in high exothermicity. So we can form this biradical species also by first doing a hydrogen atom abstraction from the CH3 group, and then in the second stage in abstracting a hydrogen from the OH group, we get to the same position, but obviously we have a much higher first hydrogen atom abstraction barrier. So it seems that this pathway with the two groups, the OH groups and the methoxy group pointing toward compound 1, will give a very quick acetal product formation with barriers that don't seem to be much higher than 2 kcal per mole. So those are very low barriers. So yes, binding position B gives an acetal product. So what we're seeing here, for instance, in this lignin activation P450 is using the cluster model of 302 atoms. We studied the various pathways of syringal activation by compound 1. We study a desaturation pathway leading to acetal and a hydroxylation of the methoxy group to form hemacetal. And what we see is that depending on the substrate binding and the substrate orientation, we either get hemiacetal or we get acetal. So the product distribution will be determined by the various ratios of the substrate binding in the substrate binding pocket. Nevertheless, these large cluster models, as we've seen, they capture the features of the substrate binding pocket well and show that how you, with different binding orientations, you can get different reactivity channels. Okay, so the host needs to tell me if I run out of time. Otherwise, I continue a bit more. I can talk a bit more on the P450s.
You have 10 more minutes, then.
I have 10 more minutes, so that's good. I didn't time my talk, apologies, so I put just a few things in it. So I wanted to talk in the final few slides a little bit on the P450 peroxygenases. As I mentioned, the P450s are normally monoxygenases that take oxygen, 2 electrons and 2 protons, and hydroxylated substrate. But there are also peroxygenases that take hydrogen peroxide and a substrate. They don't need a reduction partner, they don't need external protons, they have that in hydrogen peroxide and still can do a substrate activation or oxygen atom transfer. And we looked at those because these are quite interesting, these P450 peroxygenases, because they take long chain fatty acids and then they can give all sorts of products. They can do a desaturation of the fatty acid, they can do a hydroxylation of the fatty acid, but they can also do a decarboxylation and form hydrocarbons, and that of course is relevant to biofuel synthesis. So in this particular case, there were some experimental studies, and this is an experimental figure, which I find very complicated. But what these experimentalists done is they took this OLT, P450 peroxygenases, and fed it different substrates. So if they have a long chain fatty acid, which is either linear or has a small methyl group as a side chain, then the reaction pathways they see is mostly decarboxylation and a little bit of beta hydroxylation. If they use 2-butyrates, that's this middle substrate, as a substrate, so then now you don't have a long chain. Now they don't see any decarboxylation. This small substrate only gives alpha hydroxylation or a little bit of desaturation, so it gives totally different products than a long chain fatty acid. And then they tried a third substrate type, which had a phenyl ring on the alpha position and a methyl group also on the alpha position. And this substrate gives a little bit of decarboxylation, but mostly alpha hydroxylation. So as you see, based on the experiment with 3 different types of substrates, you get hugely different product distributions and reaction channels. So they came to us and said, can you do some modeling on this and see what is going on in this particular system? So Fabian Cantu-Reinhardt was in my group doing a PhD on P450 related work, and I asked him to investigate this system. So he did some cluster models. And these cluster models contained the substrate binding pocket and the heme. So now we have a very small, just a bare porphyrin without side chains. I think it was thiolate for the actual cysteine residue, and we took most of the residues or the amino acid chains that were pointing into the active site, which in this case are mostly aliphatic and aromatic residues: phenylalanine, valine, alanine, isoleucine, leucine, phenylalanine, proline. But there's one arginine residue that obviously binds to the carboxylate of the substrate. And then we studied 2 methyl butyrate, either in the R or the S form. And the first thing we did is, how is it going to bind in the substrate binding pocket? And then we studied for all these different conformations the complete landscape of this 2-butyrate leading to alpha hydroxylation, desaturation, beta hydroxylation, or decarboxylation pathways. And we calculated all these different product channels if possible. So first we, as I said, we docked this substrate in, and then we optimized the geometries in various different conformations. And for the R form, which are shown at the top here, we found 3 different substrate binding orientations. We also showed the overlay here on the left-hand side in nice colors, where the substrate in position 1 is in red, in position 2 in amber, and in position 3 in purple. and you see the carboxylate either forms a double hydrogen bond with the arginine in the first two cases and a single hydrogen bond with the second case, and the alkyl groups point either up or down, which gives a little bit difference in energy for the various conformations. In the S form, Fabian managed to find 5 different substrate binding orientations of various energies. So that gives an idea of how stable these various different substrate binding orientations are. Next, what we did is, and I'm only going to show here the data for the different the S conformations. Next, we try to study these reaction pathways, and I'm only focusing here on the hydrogen atom abstraction, the initial hydrogen atom abstraction from either the alpha carbon or from the beta carbon. Now, in some substrate orientations, the alpha carbon is pointing away from compound 1, so it's inaccessible, so we couldn't find any transition states, so those are the dashes I show here. And in some orientations, the beta carbon is pointing away from the compound 1, so in those cases we also couldn't find these different hydrogen atom abstraction channels. Nevertheless, we did calculate it for its doublet and quartet, quartet in parentheses, spin states. So as you can see in substrate binding orientation 1, and that's S1, we can do a hydrogen atom abstraction of the alpha and the beta position and find transition states for that. When the substrate is bound in orientation 2, the alpha position is inaccessible, but the beta position still is, and we can find barriers for those. In orientation number 3, none of these two positions are accessible, so there are no products from those two channels expected. In position 5, we can access the alpha carbon, but not the beta carbon, and in position 6, we can also not access any of the alpha or beta carbons at all. So as you can see here from these results on these different substrate binding orientations in this large cluster model, which incorporates the substrate binding pocket, you get different product distributions based on the orientation of the substrate in the substrate binding pocket. And in some orientations, there are multiple channels possible. In other orientations, there's only one channel possible. And in other orientations, there's no reactivity whatsoever. So it's very important, clearly, what is the most stable substrate binding orientation and how long it stays in that orientation to be active. So to recap on these peroxidases, we studied in this particular case the DFT cluster model that has the heme, compound 1, and the substrate binding pocket, and studied the substrate binding in various orientation, and then look at this reduced selectivity of hydrogen atom abstraction for the various pathways. And then we show that we can get a mixture of products based on the different binding positions of the substrate in the substrate binding pocket. Okay, so to summarize what I've been speaking about today, so we think computational techniques and resources are quite powerful these days, so we can study large quantum chemical systems with good accuracy. As I said, we like our DFT cluster models because then you have everything calculated with a good method. We take as much as possible of the hydrogen bonding network into consideration, particularly the charged residues that define the substrate binding pocket, the substrate binding orientation, and the positioning with respect to the oxidant. And we have been able to do predictive studies on biomolecular models. We look at enzymatic and biomimetic models and find reaction mechanisms. I didn't do all the work myself. I need to thank some people who have been involved. I think I gave a big overview of various work of students in my group of the past 5-6 years. So Matt was one of the earliest PhD students in my group who worked on these non-heme iron enzymes. Yomi is so Matt is now in Cardiff in Wales. Yomi is now an academic back in Nigeria. Fabian is doing a postdoc still in Manchester. Kadri finished his PhD last year, and he's now an academic in Malaysia. Hafiz is still in my group, is writing up his thesis. Jan Ting is still in my group, is writing up his thesis. Emily, as I said, is doing combined experiment and theory on the vanadium haloperoxidases. We worked together with the Faber group in Austria on the OLT system. We have a long-term collaboration with David Kumar in Lucknow and CV Sastry in Guwahati. I showed some work we did with G. Lee and Jose Maria Luis, Andy Monroe, Sola, Rudy van Aldek, and Yon Wang. And I thank you for your attention. And the floor is open for questions.
Thank you, Sam, for such a nice and this informative talk. So this is open question. Anyone who is interested, they can interact.
Hello, sir.
Hello.
I'm from Lucknow Central University. Sir, I have one question, and I want to ask, after analyzing the key residues involved in second coordination as well, as you said, which are also important for the better positioning of substrate and reactivity of the mechanism, how do you design those initial geometry on any chemical software like Gaussian or Jaguar? Like, can you give us the basic idea of designing that geometry?
Oh yeah, sure. Yeah, so we usually start with a PDB file. Maybe I need to stop. Can I stop sharing this screen? Is there a way to do that?
Yes,
I
please,
don't know how to
stop sharing.
Okay, I don't know how to stop sharing my screen. How do I stop sharing my screen? Ah, no, now I see. Okay, now. Okay. Anyhow, yeah. So what we do is we initially start with usually the crystal structure coordinates, which we get from the protein data bank. Now these PDB files, they are not always complete, so sometimes there's a substrate missing, sometimes there's a cofactor missing, sometimes there are mutations in it, so you need to modify it to the starting point of the studies you want to investigate. We typically add hydrogen atoms in Chimera or something like that, which is a software package you can download for free from I think it's from Chicago. So that's what we do. We do check protonation states of all residues, because sometimes these software packages that add protons not always do them in the right place. So we do check it manually. And then we simply select our coordinates, which we think are important, from the PDB file, and open it in Gaussian. So then you have your the model you want to study in Gaussian. Of course, you need to tweak with it, because when you take an amino acid residue from the protein data bank, it terminates in a peptide bond. So we usually cut these peptide bonds away in Gauss view and then stick a hydrogen back in the place where it belongs. So there's a bit of a tweaking in Gauss view usually in the setup. And yes, you can also add water molecules, which we do try to solvate things. So first, we also do a molecular dynamic simulation very often.
Okay, so thank you so much, sir.
Okay, no problem.
Any other question?
Hello, sir, this is Anvesh Pandey from BBAU.
Okay.
Sir, I have one very basic question. Sir, suppose we start mutating the residues. So I think we can repeat the entire chemistry that you did. I mean, we can reproduce each and every reaction.
Yes, sure. Yeah, that's entirely possible. We sometimes do that. That's a good point. So sometimes so we did work like that with the Kumar group in Lucknow some years ago, where we studied a specific reaction mechanism, and instead of the S product we wanted the R product. So based on the geometry of the transition states, we said, well, if this group moves to that place and that group moves to that place, then we get the S form rather than the R product. And we made some predictions on how to mutate the system to get the substrate binding position slightly different that would enable that other product. And these mutations actually they did work. So yes, you can also engineer your system in a later stage, which we sometimes do, where you have your cluster model and say I'm knocking this phenol group out and I put a phenol group or whatever. So yes, you could try that. Yes.
Thank you so much, sir. Thank you, sir.
But of course, the groups need to be similar in size, like in the protein.
Yes. Thank you, sir.
No problem.
Any other question from the participants who are inside?
Yes, sir. I have a question, sir, regarding this metabolism.
Your voice is very, very low. Who is that?
This is Prasanna, sir.
Hello?
Hello.
Can you speak a bit louder? Or you can write this in the chat box because you are not audible.
Hello, sir. Is it audible now?
Yes, it is audible.
Yeah, I can hear you now.
Yes, sir. Actually, I just want to know, can we predict the metabolism of a chiral compound? Because the way the individual isomer will interact with the enzyme, and if we go with the racemic mixture, how will be the metabolism with that respective enzyme?
Yeah, so as I said, predicting the product distributions is not always easy. So
Okay.
first of all, you need to find out in how many different orientations your substrate can bind. So often what we do is we start with the simple docking of the substrate into a substrate binding pocket to get a little bit of an idea in what sort of orientations can you expect to the substrate to bind. And based on that, you can then take some low energy conformations and study the full reaction pathways. Yes, that's right. So we could do that. We've done that with a few examples, like I mentioned, of the cosmetics biodegradation that we studied various pathways in various P450 isozymes, which gave different product distributions, as well as with the biofuel system, where we put the substrate into various orientations and show that some channels are suddenly not accessible and others are. So yes, you could use the methods for that sort of modeling.
Okay, okay,
Some
sir.
people are writing this in the chat box that can we predict the probable metabolic and degradative pathway of any drug on the basis of the structure?
People are trying to do that, yes, but I don't know how accurate it is. So the people have been trying to do docking for many years to predict metabolism, and I think they've had mixed success with that. So I don't know how accurate and how successful they have been with that sort of studies. So I think there's a lot of flexibility in a protein which you still need into consideration, and on the various substrate binding positions. So I don't think it's that easy.
Okay, any other question from anyone? If not, then let's thank Professor Sam DeBezer for his very nice and informative talk. This talk is available on YouTube Live, and it will be available in future also. So if you find any question in future, you can always contact him. Thank you, Sam. Thank you so much.
Thank you.
Now we have a small break, and at 3:45 sharp, we will be having Jastra session by Dr. G. Pillai. So it will be a tea break till 3:45 p.m. Thank you. I hope you have all installed whatever the information was provided by Dr. Pillai. If you have not done this, please do it as soon as possible.
Yes, sir.
Yeah, who is that?
No, sir. It was me, Nidhi. We have done it. Like I have done it personally.
Fine.
So I just
Okay.
said yes.
Then see you at 3:45.
Yes, sir. Thank you.
Good evening, all. So in this session, we have Dr. Garinad Pillai, who is Director of Jastra Innovations, Bangalore. Dr. Pillai is a scientist and founder of Jastra Innovations. Formerly, he was a Marie Curie Research Fellow at Molcode Limited, Estonia. He carried out his PhD at University of Florida with Professor Allen and Professor Carlson at University of Tartu. He worked as musculo-repellent with the US Department of Agriculture, including SAR methodologies, and he worked on several other research topics. Dr. Pillai is a computational medicinal chemist with experience in structure and ligand-based drug discovery and drug repurposing by applying a variety of methods based on available data. And he is expert in QSAR, molecular dynamic simulations, virtual screening, binding free energy calculation for protein ligand complexes and for DNA ligand complexes, and various other computational techniques. He has published several research papers, and currently he has 2 PhD students working under him. Today he is going to give you a demo on Jastra. Over to you, Dr. Pillai. Dr. Pillai, you are muted.
Can you hear me now?
Yes, yes. Please turn on your video also, and then please continue.
Okay. Yeah. I hope you can see my screen, right?
Not yet.
Oh, I shared it actually.
Yeah. Now it is coming. Now it is coming.
Oh. Okay. You could let me know when I can start. I will start then.
Yeah. Now it is over to you. You can start whenever.
Oh, okay. Yeah. Thank you so much. So thank you, Dr. Hemant and all the other organizers for this opportunity. And I'm sure that many participants are here already installed the softwares, the license, the workshop material, and other all details has been shared with you yesterday. So if you have any difficulties, please let me know now before starting the session. And few of them also contacted us saying that some installation permission issues. I hope you were able to fix that with your operating system. But otherwise, if there is any specific questions or expectations from this session, please let me know beforehand so that I can show the demo accordingly. Feel free to stop me anything. Don't worry to wait till the end. Initially, I'll start with a short presentation. Sir, video might not be possible because my camera has a distortion.
Okay, fine.
So, sorry about that. Yeah. So, yeah. So that is the thing. So if you have any questions or expectations from this particular session, please go ahead. Let me know right now so that we will. So it's mostly an interactive session, and I hope you have the software with you. Please do not use the software right now because I have already given you the tutorials in 2 PDF documents. After the session, you can do it parallelly looking at my session and you will be not able to do productively. So it is better that you completely be attentive here and you have software license for more than a week and you can try it yourself. So don't be anything hurry-burry. Just listen to this, and if you have any questions, you can shoot it up. But right now, if you have any concerns or expectations, please let me know. I will address them. Okay. I hope everybody can unmute themselves or put in the chat if any queries are there. I'll be not able to read the chat, so it's better that you speak out. So today our main aim is drug discovery. Now, drug discovery, when you're talking about, are we really making the drug tomorrow morning, or are we really making the drug in the lab and tomorrow giving to the citizens? Actually not. Our aim is to try to do the preliminary steps before clinical trials, ideation, optimization. That is completely within our scope of research. This can be done and achieved very tremendously, very successfully also. So we need to know and we need to learn from failures. So in earlier years, we understood that from several papers and studies from 80s to 90s, many of the drugs failed just because of poor ADME and strategies. Also efficacy, mainly efficacy. But later from 90s to 2000, we found that ADME is being safeguarded, but toxicity and as well as strategy is the biggest factor due to failures of drug discovery. So it is not simply synthesizing compound testing and reporting IC50 is called discovery. There's something beyond that. Today, Professor Bharatam also mentioned about that. And day before yesterday, or yesterday, Dr. Shastri also mentioned about that. So we might listen to it and we might forget it, but it is actually we have to apply it. That is where I always say that you have to transform your information, whatever you know, to knowledge. In order to transform that information to knowledge, you have to apply somewhere. You have to experience it and you have to relearn it. Relearn means you learned, you might be there is some mistakes or you want to optimize it and then you have to relearn it. That is exactly called machine learning also. Today we had a session, I think a session before the previous one. So there was a machine learning session. So similarly, that it's a relearning process. So it is very mandatory that we reach to the right drug candidate. I'm not going for a drug. I'm looking for a drug candidate. Could be called as drug-like or lead molecule. That is absolutely our aim today with this hands-on workshop. So let me tell you before moving forward, we are not yet completely ready with AI or ML in drug discovery. It takes time like Human Genome Project. So don't worry if you do not know ML. Don't worry if you do not know Python programming, but it is the right time for you to start learning it. This is something that I usually tell everybody. So it will take them, but to be in par with them, so be ready with the skill set. My slides will contain some of the pictures or videos that is taken from web articles, lectures, and tutorials. It is not that I can create every content here, and it's copyrights is with the respective authors. The technical slide, this particular slide and other training slides are already available in my SlideShare. I hope you are able to see my seconds. I'm on my second slide, and the hands-on videos, some of them are already in my YouTube. If you want to look at Autodoc, Modeler, Padel, QSTR, and also Gromacs using Jupyter Notebook and NAMD for binding energy calculations. And all the sample scripts and workflows are available in the GitHub too. I am on my third slide. I'm not sure whether is it okay with you? Yeah, sure. So right now, what we are looking at is how we can reduce the cost of medicine. As a normal civilian, he doesn't worry what is research, whether the vaccine is effective, what is its efficacy. He just knows, okay, someone suggested, the doctor suggested, so he is prescribed and got it. That's it. But ultimately, the civilian is concerned about the cost. Being with an audience of pharmacy institution of national importance like NIPER and any other, it is what that we have to look at is how can we cure the high cost of medicine. One of the simplest answer is reduce the reason or drug failures. That is one of the easiest way to reduce the cost of medicine. There are many things involved when I talk about failures. I'm not going into that direction anyway. But these failures can be identified with different drug discovery approaches. So for example, based on the data availability is what you have to choose your tools as well as what kind of method you have to apply for drug discovery. It is not that you already have a tool with you and you have to use some project. No, it is the other way around. What is the kind of data you have? Do you have an X-ray crystal 3D structure of the protein? Whether that crystal structure has a good resolution, whether that protein is bioavailable, whether it is druggable, whether it can bioavailable means whether it is present in the models for testing and others. Is there any multi-conformations present? Is there any missing residues, missing atoms? Many questions prevail in order to confirm whether your protein starting structure is a better one to start for docking studies. Second, ligands. We always try to easily convert 2D structures to 3D structures. Keep in mind, all your 3D structures, whatever you are optimizing, after docking, your biological complex conformation will be different. What I mean to say is, let's say you synthesize a compound in the lab and you through NMR or X-ray crystallography, you take the 2D and 3D structures and composition, everything. And let's say it is being consumed, approved as drug, and it's being consumed, it binds to the biological system and it forms a biological conformation or bioactive conformation. The conformation of the bioactive conformation of that compound and the compound as it is in the shelf, both the conformations will be different. So why we are doing molecular dynamic? We wanted to find out the right bioactive conformation. Did I talk about score here? I'm not talking about score because score is not my criteria to say whether it is bioactive or not. Score is more of a geometrical term, but bioactivity is more of biochemical and mechanism term. So that's why I was mentioning we want to look at for a mechanistic driven drug discovery. So molecular docking is a structure-based drug design when you have proper structures for both target as well as your ligand. Now, many of us skip molecular dynamics because we say, I don't have resources, it's too difficult, too much of biophysics and all. But ultimately, you have to understand most of the molecular docking, your protein is rigid and you make your ligand flexible. But in reality, is that your protein is rigid? Never. So that's where molecular dynamics helps you to make it flexible and also try to understand whether your ligand still will be able to stick into the binding pocket and have a good, strong interactions as what we predicted using molecular docking. So molecular dynamics is mandatory. It's not about 100 nanoseconds, 200 nanoseconds, all depends upon what is your requirement and what is your objective. Next comes with the fragment-based drug design. Let's say you have a protein, proper protein structure, and then you try to dock with Cambridge Structural Database and other databases. And you didn't find any specific ligand that is binding or bioactive conformation with your protein. At the time, you have to design something. That's where we call it as de novo or scaffold hopping. And that's where we call fragment-based drug design. And then we come to ligand-based drug designing. When you don't have a protein structure information, you just have compounds and its activity data. It could be inhibition data or bioassay data, or let's say you don't have an activity data also, but you just have the bioactive conformation. And that's where you can apply Pharmacophore, 3D Pharmacophore mapping and screening, 3D similarity, or QSAR. QSAR can be 2D and 3D. Keep in mind, 3D QSAR is one of the dangerous way. You have to be very careful while choosing the right data now. I'm sure Professor Kunal Roy will be discussing more about it, about QSAR. So when you come to 3D, ensure that whatever structures you are using for your 3D QSAR, the geometry is a bioactive conformation. That means after the docking, the best conformer you have to use for calculating the 3D descriptors for QSAR. But most of the time what we do, we just simply take 2D structures using MMF or MM to convert it to 3D, calculate the descriptors and go forward. But how do you know that? That is the conformation is a bioactive conformation. So there are small things we need to be very careful when you talk about 2D and 3D. But 2D QSAR is one of the safest. You need not to worry too much about all this conformation challenge, right? So that's where ligand based. And the final one, when you don't have all these data, you want to do a high throughput screening or virtual screening. That's where you do a CombiChem or high throughput screening. So this slide is very important because based on the data availability is what you have to choose your method. It's not that I have few compounds, let me do some QS here, not docking. No, it should be completely dependent upon what kind of data you are going to use it. That is where we have to understand molecular docking then and now. In 1894, even I also learned when during my academic career that it is a key lock hypothesis. But now in 2021 or 2020, this is only half of the truth. Many things have changed in molecular docking. Now, why do we do molecular docking? We want to determine the optimal binding structure of a ligand to a receptor and quantify the strength of the ligand receptor interaction. And this is where the ligand will bind. That's what we wanted to understand, where the ligand will bind and how will it bind, how strong it could bind. What is the role of solvation and desolvation? I think yesterday Dr. Madhavi Shastri would have spoken to you about the role of water. Right, so I'm not talking about the water solvation, or it is about the water that is present in the protein PDB, as well as solvation also including. So role of solvation or desolvation, and also what makes a ligand bind to a receptor better than the others: selectivity, specificity, sensitivity. So we are trying to understand what all these are the different things that to be taken care of. Then translation and rotation of ligands. Also torsions, which is similar to dihedrals. Did I talk anywhere about score? No. This is a picture that I have taken from enzyme methodology book. And this is exactly what you have to say after doing molecular docking. What is a catalytic function? Now, if you say too advanced, we don't want to do that. But that is where that is the expectations. Molecular docking from molecular, what we are trying to achieve the outcome, these are the expectations, not a score value. So what is a catalytic function in your protein? Regulatory mechanism. Are you trying to hit the active site or the allosteric site? Cleft detection. When you identify a pocket in your protein, it doesn't mean that the software will automatically take care of the functional site, mechanism-based catalytic site. No, it will just identify an empty, unoccupied space and it will predict the pocket. It is our job as a user to identify whether the pockets identify the software has the catalytic site or the key amino acids or the functional site. We have to analyze it. Then geometrical analysis, whether there is any conformational changes happens during the docking. Coming to flexibility, we want to understand apo and substrate bound, which kind of flexibility that we are looking at. And then conservation. If you're working on cancer drugs or anti-cancer drugs, we wanted to see, you might say that my compound is very much active or inhibiting breast cancer. And then my question was, okay, how selective and specific it is? You might say, yeah, it is good. But now the question, my answer to the question was, yeah, it is very selective to cancer, breast cancer, not for lung or skin cancer. So we want to look at conservation. We have to have a comparative analysis, sensitivity, selectivity, and specificity. And even in docking, we can do that on similar kinds of proteins or mutated ones, mutation happenings, all those things. Surface characteristics, where is solvent accessible area? Is there any other lipophilic or hydrophobic regions? And finally, we talk about energy, that is binding energy or interaction energy. In some terms, it is called as delta G, where it is desolvation and solvation is taken care. Otherwise, we also talk about free binding energy as you get from Autodoc. So here today, we will be using a tool called as CSAR, C structure activity relationship. That is a full form. So here, what it takes care of it is, it does not minimize your protein, but it does protos, that is protonation, tautomer, and water selection of the protein. Now you might ask me why we are not minimizing the protein. If your protein is perfect without any missing residues, missing atoms, why do you need to minimize? Because when you minimize, you are putting in force fields. Do you think X-ray is inaccurate than force fields? I don't think so. But if you have missing residues or missing atoms, absolutely you have to model it and then you have to minimize it. That is mandatory. So that's the reason why we do not minimize here. So if you have any missing residues, of course you can use modeler. I have I have a Jupyter notebook created for homology modeling for modeler, which is available in my GitHub. So there you can model it, minimize using Gromacs or NAMD, then bring it here. Those both are possible. So we try to protonate. Now protonation is simply, we learn that is addition of hydrogen. Now the question is, what is the orientation of that hydrogen that is added? Very, very important. It's not simply the angle or bond length is important. Orientation is also very, very important. And then we have to optimize and score, visualize and edit. Let me go to more details. Don't worry about the equation. What I want to try to say here is we are trying to calculate the energy, understanding the dehydration and the bond. The main criteria here is hydrogen bond, the log P and desolvation terms. So desolvation terms means with water, I mean bound with water and without water. So hope yesterday's presentation you would have clearly gone through. So only if clash and torsion strains are low, values are meaningful. I'm sure many of you have used Autodoc. So in Autodoc, you might have observed intraligand and interligand clashes or interactions happening. That is not acceptable, in fact. So even the strain should be low and the clash also should be low. Then only all these energy values are meaningful. That's why I said, just looking at scores and energy doesn't mean that your conformation is bioactive. You have to have a visual focus and understanding of that. Subtle electronic effects cannot be also captured. What I'm trying to say here is, other than docking score, what will I get? See, docking score is mainly used for virtual screening. Virtual screening means, because as you all know, recently we had a drug discovery hackathon. I am one of the coordinator for drug discovery hackathon. So there in your result submission, it was clearly asked enrichment factor. I hope everybody knows it, what is meant by enrichment factor. When you do virtual screening, we wanted to know, when we analyze the data, we wanted to know what is the total number of compounds you have selected for your database. How much was being filtered? Finally, how much you are reporting. And that tells you what is the enrichment factor. And that is where you need docking score for you to rank the compounds the best one. But when you have 2-3 compounds, or let's say 5 compounds or 10 compounds, and you wanted to do optimization as a medicinal chemist, as a pharmaceutical chemist, and then that's where the docking score, just docking score is not going to help you. You need in energy terms also, and also wanted to identify whether this conformation is really viable or not. So let's look at this example, then I will go to the demo. So here you can see the torsions are being analyzed. If the bond for this particular torsion is green color, it says that this particular bioactive conformation torsions are present in Cambridge Structural Database. I hope you all know Cambridge Structural Database is a crystal structure database for small molecules. So they try to do a statistical comparison to understand whether they are similar or it's being observed. Another example is that if you have a yellow colored bond, it's unusual. However, it is being still observed in CST. And if it is a red color like this one, then red is very rare and observed in CST. Here we did not talk about docking score. Here we are trying to understand whether this conformation is really crystallizable, whether it can form a co-crystal or not. That is what we are trying to understand based on the torsions. And then another analysis is looking at affinity. Can you predict the affinity using software? Of course, yes, we can predict the range, but can we say it is 13 nanomolar and tomorrow you test it? Do you get 13 or 15 or 12? It might be within some range. We cannot be very sure. And can you complain that software did not predict well? Never ever, because it's a prediction. There will be error. So here what we are trying to understand is, what is the contribution of your atom within the ligand on the binding affinity, both in the terms of desolvation and solvated state. So here, when you see corona, of course, not coronavirus. So the round circle, whatever sphere that you see around the sphere. So if it is a red color, it says negative contribution to the binding affinity. If it is a green color, positive contribution to the affinity. or it is good for affinity. That's what we are trying to say. The other means is like we also wanted to understand the size of the corona. If the corona size is larger, we are trying to say it has more contribution. So larger the size, stronger the contribution. So this also tells you like this. For example, if you see here this red line for the total energy for this atom's contribution is 7.6 kilojoules per mole. If it is green, you can see it is negative, minus 3.4 kilojoules per mole. The total of all these atoms' energy, when you calculate, that is what you call it as total binding energy, right? But the affinity will be in nanomolar or micromolar or millimolar or picomolar. That is what is the range. So here in energy terms, we are understanding the contribution of each atom. Now, what is the advantage of knowing this? For a chemist, it is big advantage because he or she will come to know, okay, this particular region is having a negative contribution. So that let me think of making new derivatives at that region. Or I have some unexplored region in the pocket after the binding. Let me try to see the exploration there. So docking basically helps a chemist if you're doing some optimization steps to come up the best derivative. So docking also reduces the gap between a modeler and a medicinal chemist to look at the possible derivatives in 3D optimization. That was the topic of this particular workshop also, like 3D and 2D lead optimization. How can we do this process? Of course, we learned a lot about optimization, but how it is going to be useful for a synthetic chemist based on a modeler is going to speak. Now, the least desirable properties, what we are looking is for a compound is biological activity, related analogs, bioavailability, absence of toxic groups, irreversible interactions with biological target. These are the key properties that we look at a compound. Now, this is what I was telling you earlier about inter and intra-ligand clashes. So you can see here, the orientation matters. The same compound, there is no big difference in energy. This is a quite small tilt here. And the same thing when got turned in this side, you can see there is a clash. You might think it might form a bond. No, there are not required distance and others to form a bond. So it will form a clash. These clashes is going to badly affect the energy criteria. That is where we look at chemical spaces because we want now idea to come up with more, sophisticated databases to come up with designing new molecule. So we use NME, then WUXI, Galaxy, all those things to generate new, building blocks. So what we are trying to do is, let's say you're giving a cook ligand or any ligand, whatever it is, into the software. And it will try to do a pharmacophore based similarity search. Again, repeating, not structure based, but pharmacophore based similarity search. You can see this particular region found similar with this ring, and their similarity is 0.61 or 61%. Now this region, okay, this particular colored region with this region having a local similarity of 91% or 0.91. But overall similarity between this one UHO structure and virtual hit structure is 80%, that is 0.80. So this is what we try to say, pharmacophore based, and that's where we are trying to find out which could be the best hit. So we are completely designing new molecule and which is IP protected. And we do have also options to predict the retrosynthetic pathway. So keep in mind, this is not completely a computational chemistry. This packages are a mix for medicinal chemist, pharmacologist, and even people who look at screening, virtual screening also. Right, so you can check out what could be the retrosynthetic pathway, like what you use in SciFinder. Okay, now before moving forward to the next step, let me go to the demo. Now, I don't know whether I'll be able to hear all of you or whether you are able to unmute yourself. Just let me try. Yeah, so can we start the demo? Hands-on session, that's what I'm asking. Hope you all are ready.
Yes, sir.
Great. So all of you installed, or do you have any difficulties in installing the software? So for CSAR, let me tell you, now we are going to look at docking and CSAR quickly. For CSAR, let me tell you that you need to have latest drivers of your display driver. It doesn't require graphics card. It doesn't require any sophisticated machines or RAM, but mandatory is that it requires latest display drivers. Otherwise, it will not work. Then another advantage with CSAR is that, let's say you are working on an i7 machine or an i5 machine or the latest series of i3 machine, and your machine is having 4 core or 8 core. CSAR will help you to run the docking program in all the 8 or 4 core. The advantages here is when you do virtual screening, you can run 4 compounds at the same time parallelly. So it all depends upon how far you have. But otherwise, let's say you have only a 2-core machine with 2 GB RAM, still it works, but a large data set of databases for virtual screen, let's say 1 million compound, it takes ages to finish. Any software, not only CSAR, even Autodoc, Pyrex, Vina also takes ages. So it depends upon. So if you have only less compounds, it's absolutely fine. But if you have any difficulties in installation or anything, please let me know. You can put it in the chat or in the question. I'll be able to answer. Otherwise, I can start directly how to do the demo. You are being shared with a PDF file. It is not necessary that you have to use a PDF file. You can, the same PDB file within this PDF that is mentioned, you can use anything. So today, the CSAR, I am using Mac, of course, Windows, Linux, it all works. 64-bit is recommended. 32 versions, earlier versions are there, but not the latest versions. So most of the packages now support 64-bit. Now this is just the interface of CSAR. In the middle, if you go mouse over it, there are plenty of options which talks about different modes. So first one is if you want to make any modifications in protein. If you want to mutate a amino acid, you can do that. Binding site, whether you want to define your co-crystal ligand and generate the binding site, whether you want to add additional amino acid to the binding site or remove some of the amino acid from the binding site can be done. Protein editor, which I told you already, if you want to mutate an amino acid or if you want to change the orientation or tautomer, all those things can be done within the protein editor. Analyzer, you can load as many compounds to analyzer and you can check the binding affinity. For example, let's say you did the docking using Autodoc Vina and you wanted to bring into CSAR in order to calculate binding affinity or do optimization. You need not to redo the docking here because you already did docking with Vina. So you can load all the compounds to analyzer and generate the binding affinity and do modifications. Let's say you're a chemist who knows where to break the bond and where to make the bonds and joins and all those things. There you can make molecular editor, so optimization can be done. When you make modifications on the fly, it will do the docking and it will generate the binding affinity. Of course, extensive docking can be done, but this on the fly, it will show you just to get an idea. Another is called Inspirator. Inspirator is a fragment-based drug designing approach, where we will be providing databases. So databases from PDB, a Zinc database, as well as from CCSD. So these fragment databases can be used to generate the scaffold hopping. So 3 types of scaffold hopping is there. One is replacement, one is growing, and one is linking. For example, anybody working on PROTAC? So PROTACs, I hope you have recently heard a lot of many papers coming in. So linkers can be easily designed using Inspirator. And then you can perform docking. Of course, docking here, it uses FlexX in the background, which is being developed since 1980s. And yeah, FlexX does the docking and you can choose how many cores. Pharmacophores and all those can be defined. And also how many number of poses to be generated. Conformator and superposer, which is coming in the next version, where we will be looking at generation of conformations and checking reconfirmation of the comparison of the bioactive conformations. So Any one of you have a choice of PDB ID? I can give that. Because always I get complaint from students and faculties that you always show a tutorial, and not only me, everybody shows a tutorial. That works perfectly all right, but my PDB doesn't work. So I thought to take an opinion from the audience. So do you have a preference on the PDB ID? Otherwise, I'll give my PDB ID. Okay, I don't hear from anybody. So I'm just going with one STP. Usually I show one DWD. Now I'll go for with one STP where there's biotin. So the co-crystal ligand here is biotin. So when you load the PDB itself, you can see that the ligand, co-crystal ligand biotin is there, and surrounding protein is also there. I have done a demo on this using NAMD, how you can calculate the binding energy for this biotin in one STP using NAMD. So that's why I thought to take the same for docking also. So the first step is to define your ligand. If you wanted to define this particular biotin as your co-crystal ligand as a reference molecule, you have to select this. I hope everyone is being attentive here, not doing it in your computer, because already the guidelines, tutorials, everything is given in PDF. So I request everybody to please be attentive here so that you don't miss the key features and other options. So if you uncheck it, that will be like you're not selecting this co-crystal ligand as your reference or a co-crystal molecule. Let's imagine that you don't have a co-crystal in your protein. There's a protein or maybe a hypothetical protein which there is no co-crystal. In that case, you need not to select anything because there won't be nothing. There won't be anything there to select. And then I can simply click this orange button, which is saying you have not defined a ligand. All molecules will be treated as cofactors. For example, if you have heme, or if you have disulfide or chlorine or something else. Of course, if you don't select, it will be considered as a cofactor as part of the protein. But if you select, of course, this will turn into green, which will tell this is a co-crystal ligand as a reference. So both ways, I have showed you the example. You can click the button here, even if it is orange, it will go to the next step. So here I have the co-crystal, I clicked it and say, apply the ligand definition. Now the ligand definition is defined. That means the ligand is being considered as a co-crystal ligand, which is not part of the protein. Now, if I come here, I can see the ligand. You can see the 2D structure of the ligand also. So now I need not to explain. The first is a table contains a protein. The second table contains about the ligands, what you define. The third shows you the 2D structures. And finally, it will tell you all the sequence with the numbers. You can also select them. And you have some key buttons here. If you click this, you can say whether you want a ribbon to be displayed or not. Then whether you want to hide water molecules or not. So you can see water molecules are there. And then if you wanted to have any metal, if there is any metal atoms or not. If you want to display the ligands or not, of course, we do have. And then residues, if you want to identify, you can see some of the residues are getting highlighted. And finally, if you have individual protein, for example, I told you can load multiple proteins in order to do comparison between selectivity and specificity of interactions. So you can load multiple proteins also. And another advantage in analyzer, you can load, let's say, minimum of 5 compounds where you have done docking, binding affinity studies, as well as IC50 studies. That means wet lab bioassay studies. You can load all this data into analyzer. It will give you a statistical report. It will not give you a correlation report, but a statistical report in the analyzer. So that is also there within the analyzer. Okay, so now we have defined everything. We are in the protein mode. Now I'm going to ligand here, STP, and I'm saying add to binding mode, binding site mode. That is the next step. So what I'm trying to say is now, please consider this particular co-crystal ligand as a reference to generate the binding pocket. Okay, I'm just scrolling using the scroll wheel in your mouse. Okay, and I'm doing this turning around using the right mouse button, and the left mouse button is just for selecting. Okay, just for, you can see it, just for selecting, I'm doing it. So if I want to deselect some amino acid, just double click on it, you can do that. Okay. So that is for selecting. If turn around is again the right mouse button. In this context, let me explain some of the buttons here also. There are very few buttons in this interface. Going to visualize, I can also enable and disable binding site surfaces when it is being generated. I can label them, label the amino acids, atoms, and the angles, distances, and utilities are there. And appearances, if I want to change to dark or light, it is possible. Personally, I prefer dark, but for presentation purpose, I changed it to light. I can increase the label size, and if you have any blindness, color blindness can be also done. Now, for the recore or fragment-based approach, you have to have the recore indexes that to be loaded here. I'll show you when the step comes in. Okay, so let me do it in a different way. Just let me reset it. Let's imagine that you don't have a co-crystal ligand here, and still you wanted to predict the pocket. Okay, what are the binding pockets available? For that, you have a button here called Show Unoccupied Pockets. If you click that, it will use DocSite server. It is a algorithm, DocSite algorithm, which tries to predict what could be the possible binding pocket. So we have only a single binding pocket. If there are more than one, it will be represented in different colors. And now, in order to select the neighboring amino acids, you click on this button and say add surrounding residues. Automatically, it will add surrounding residues to that particular pocket. This was an example which I told you when there is no co-crystal ligand. Now, let's say that now my protein is going somewhere in the corner of the window, but I wanted to make it to the center. The easiest way is just press the space bar. I just press the space bar. It comes to the center. So it's easy for you. So even if I'm zooming out and space bar, it gets zoomed and gets into the center. Now, again, I'm resetting because I do not want to use this pocket. Rather, I wanted to use my co-crystal ligand to define the neighboring amino acids. I select this and say add surrounding residues. So surrounding residues are here. Let us go to the bottom and you can see some of them are being colored in purple or magenta, whatever color you call. So you have the certain amino acids being included. Let's imagine I read a literature and I did some pro site analysis and catalytic site analysis. I understood that phenylalanine 29 also could be considered as a part of the binding pocket. So I click the right button and I say add residue to binding site. I can do that. So phenylalanine also will be considered. So tomorrow, let us say after software being predicting the binding pocket, we wanted to not consider this particular amino acid. We want to remove them. Click again on the right button and say remove the residue from the binding site. You can do that. Now let's imagine I want to focus mainly on glycine 26 to see the orientation. I can click the right button and say focus view onto this component. So this is the glycine 26. How do we know? Go to label measure, show label, and then click on it. You can see here, glycine 26. So this is what is used for labeling, okay? This particular label measure, show label. And if you want to calculate distance and all, it goes on. So now we have the key amino acids, which is being defined based upon the co-crystal ligand. And then you have to click this green arrow. Always it's a green arrow is the same. Now, software automatically identified the possible highly contributing and comfortable water molecules within the pocket. So we will later see whether this water has any contribution or not. Whether this water is happy or unhappy. So I think yesterday all of you have been attentive to Dr. Madhavi Shastri's talk on waters maps and other things. Something similar to that. So we also wanted to understand which will be the key water molecule which could contribute or enhance the interactions. And stable, of course, comfortability is very important. Now I again click on to biotin and asking it to add to docking mode. Now my step is to do docking. This is where you see the key amino acids within the site. If you want to see the pocket in a surface, click on this binding site surface, the surface gets generated. So you have the surface here. And if you want the surface to be colored in lipophilic, you can color it in lipophilic. Element based, you can color it in element based. Both are possible. And now I just select my ligand. This is my co-crystal conformation. Okay, it's not the docked conformation, co-crystal conformation. You can see here it is there. If you want to quickly calculate the binding affinity of the co-crystal conformation without doing any docking, so you can also do that. So I will say here, click into this particular menu option and then say calculate estimated affinity. When I click on that, it is calculating the affinity, and you can see most of them are red color. Okay, and affinity is given in the range. This is what I told you earlier. None of the software can predict affinity accurately. We can only estimate the affinity. So here it is saying it could be between nanomolar and micromolar, but more favorable to nanomolar. And the result of the bioassay is also very close to nanomolar. But if you want to calculate the energy, let me go to the label again, show label. And if I click on this, I will be able to see the energy contribution of that particular atom. Energy contribution of this oxygen. Energy contribution of this particular carbon in biotin. Nitrogen. The same way we will be able to know all these contributions. Let's imagine what could be the torsions. You can say calculate torsion quality, how this bioactive conformation is. So let me enable the torsions also. So I could see some torsions here, orange, that means yellow or orange color, which tells you a graph how far it is present in the CST databases. And also we have a red one. Let's see. Yeah, this is very close to the yellow one where we have a 122 degree on the torsions. So this is the visual interpretation. There are several papers being published in Journal of Medicinal Chemistry where they have used a CSAR for lead optimization to come up with new derivatives, synthesize them, and compared the wet lab studies with the predictions. But keep in mind, when you do modifications, it's better to be sitting with a chemist because ultimately you have to synthesize them. If the software is predicting the synthetic feasibility and synthetic accessibility, doesn't mean that a chemist can synthesize easily. It just tells you what is the linking rule and breaking rule of inorganic chemistry. But when you make modifications, we have to understand the binding affinity and also checking whether it is on reality synthesizable. That's what we are looking at. So here the ligand, the lipophilic ligand efficiency is okay. Then torsions, intra and interligand clashes are not there. That's why it is in green color. So none of are being given in numbers, and none of the publication reviews are asking for numbers. You need to put a proper discussion for these writings. So that's why I said we are not talking about score. In CSAR, still you get score. When you do virtual screening, you will get the scores. You will get FlexX scores. That is anyway there. Now, let's imagine that we have analyzed our binding, co-crystal ligand. Let me do a docking here. I wanted to do a template docking, which is very similar to the bioactive conformation. So in order to do template docking, I have to select this. Then this will be active, which generates based on the template molecule. If I unselect this, there will be a normal docking. So I select this to do a template docking. I'll do the template docking. By default, it will generate 10 to 3 or 3 to 10. Let me check how many are given. I have given maximum number of poses as 10. I can go to up to 500. Flash tolerance from standard, medium, and high. Let me tell you, if your compound is containing more flexible and rotatable atoms, you can go up to 40 poses. Anything above 40, it's waste of time. If it is too rigid, especially when you're working on phytochemicals, something between 10 to 25 is fair enough, because phytochemicals, we mostly know they are very rigid, not so flexible, most of them. So you have to be very careful to save time. So if you have computing and time issues, no need to worry, you can give the maximum. But let us do something very meaningfully. And then if we have docked it, so let's see how the docked conformations have come. So you can see slightly it is being changed. But if you want to compare the conformation of the co-crystal ligand, you can define this as show as a reference, and you can define what color you want. Let's say I want something red color. Okay. And then if I select this, you can see there is a change in the slight change. It's not a large or huge difference anyway. So the software was able to identify similar conformation. Now, in order to calculate the binding affinity, I select all of them, go to this calculator and say estimate affinity. It calculates and generated those coronas. And you can see this one is giving the best estimated affinity, right? And all of them are in green color, favorable. Of course, you can predict some of the physiochemical properties like TPSA, log P, molecular weight, and few others. But you know, for different conformations, it is still the same. For that compound, it is different from the other compound. Now let's imagine you wanted to include some other molecules. You can go to this menu button, load molecules. I'll try to load this a bit larger molecule. But before that, let me show you how to load this into Analyzer so that we can do some editing. So I'll go to Analyzer. I'll go to File, Load Molecules. I'll load neurokinin 2. I have some set of compounds already here. Now, why this is taking more time? That is why purposefully I took that. If your database is in 2D structures, it is a 2D, only it's a planar, right? Automatically software uses 2D to 3D conversion, as well as ring conformation, ligand minimization, stereoisomer, all those isomerism, everything will be checked, and then only it will load to the software. So basically you need not to convert it to 3D. If you have already converted it to 3D, the software would have already loaded the compounds, no doubt about it. So now this is in 2D structures, almost 1,000 structures are there. And that's why now it is converting 2D to 3D, including ring conformations, and then load the molecules to the CISA. Now let's imagine I don't have time, I don't have patience to do that. I want to cancel it now. You can do that. When I cancel it, whatever structures are already loaded, that will be here. So it is not that the whole data is being gone. No, up to 63 compounds, it has already loaded. If you click on that, and you will be able to visualize the structures at the bottom. You can see here, right? You can see some of the structures here. The problem here is they are quite large. So we have to see how far they will be able to dock. So now I loaded all them to Analyzer. I'm going to pick only 2 molecules to go for docking, for example. Otherwise, I can directly load it to the docking mode also. It will dock everything. I want to show you how the Analyzer is being used. I selected only 2. If I want to do any affinity studies, I can do only if you're loading the poses from another compound's docking result. Otherwise, if I want to load these 2 molecules to docking mode, let's say we are going to docking mode, you can see none of the structures are loaded other than biotin, right? Now I am going to load the structures which are from Analyzer. So I'll select 2 molecules and I'm saying add checked molecules to the different mode and asking it to go to docking mode. Now you can see I am in the docking mode now. Apart from the, I think I have selected 4 of them. Yeah. So apart from biotin, you have 4 other compounds also being listed here. Whatever compounds that is being loaded into the first table of docking library, all will be docked. So it is better that you bring the compounds from Analyzer and dock it accordingly. But if you're doing a virtual screening, you can load everything here and then do the ranking and other things. So now let me do a docking. So the docking is running. It has finished and it said no poses generated. I expected because the compounds are a bit huge. Okay, so let me try to do some modifications. I will take this compound, the biotin, and I will go to Inspirator. Now I have to load the data here. That means database is here because it said there is no database. So when you I hope you all have downloaded CISA. There is one more to be downloaded, which is when you go to settings, go to Inspirator. You can click on this button, download recore index file. Click on this, it will open a browser and you can, yes, it will directly go to this particular page. Index based on zinc PDB and CSD. So this is what I was referring to. You have to download this if you wanted to work on fragment based. And this each one will be 1 GB file. So ensure that you have internet data if you're working from home. Once you downloaded it, I already have the downloaded file. You have to click this particular button and go to the specific directory. Let me go to that directory. Yes, I do have CSR sync and these are PDB. I told you it is almost close to 1 GB, right? So I'll just load a zinc probably or PDB probably because most of them are co-crystal. Record index already exists. Okay, they have already unpacked it. It's here. Okay, so I will just select this record because it was already extracted. So I have this record now. I apply it. Now I have the fragment database ready. So this is the procedure how you need to install the fragment database. Now I clicked on this compound. I can see both the side, okay, the 2D and 3D. I wanted to modify. I wanted to replace this particular region. Just I wanted to replace this region, the middle region where it is masked. You can see here also, right? When it is being selected automatically, you can see core replacement requires at least select 2 selected bonds on the one molecule. We did that, right? And I click on this. It will now try to generate all possible replacement for scaffold replacement or lead hopping, whatever you call it. Now you can see the icon here, a bulb icon or maybe inspirator icon. That is what it says. This compound is generated using inspirator. And you can see there's a different replacements happening. Now you could also find some issues. Some of the compounds or fragments are overlapping with amino acids also. So for example, this one, right? You can see this, right? Because we did not define to the software that there is a protein pocket available. So we can define that too. So what we do is we go to Pharmacophore and you can define a constraint and you can say exclude and you can define what all the spiral center or ring atoms, muon smarts, hydrophobic, all those things can be defined. So that particular area can be also being skipped or escaped. So all these features are available within the Pharmacophore. So Pharmacophore here it is done on the receptor, not on the ligand side. Keep that in mind. For the ligand side, we will be using star drop. Yes.
So minor doubt I have. These replacements which it came out, like it was because those 4 we selected already, or it just it did it on itself, like and it
Okay.
how did it?
May I know your name and from which institute?
Asking question, you turn on your video and introduce yourself.
Yeah.
Okay, sir, I'm sorry. This is Nidhi here from Mumbai University of Mumbai. So I wanted to just know that, like, what reference it is using to make this, or maybe just replace this.
Okay. I'll just reframe my explanation. Let's imagine this biotin is already patented molecule, but my professor or I personally interested that I wanted to work on this compound to come up with a better enriched compound, but still considering some parts of the biotin. Now, when you're doing fragment based, the very important part is you should know chemistry. Now, if you say other software doesn't need to know you to know chemistry, then you will have a hard time, because fragment based drug design, the challenge here is synthesizing those compounds. So you need to know chemistry for that, for sure. One question was, how do we know where to put these exit or the vectors or the references? That was one of the questions. I'll come to the different perspective of the reference question also later. So here I'm thinking that I know this particular region is very much active or having very good interactions with my residues. So I don't want to modify that. I'm just trying to modify rest of this region. And I ensure that this oxygen is also hydroxyl group is very, very much required. So I'll just, because I know the shape of the pocket is also less. So I just define this. Now, I should also make sure that when I'm doing a synthesis, I will be able to break this bond and making some derivative is possible or not. That is also there. So it's not simply automatically being put. Now, after doing this reference, on a click of a button, we are replacing, because the database I chosen has already generated fragment database from Zinc database. That's what I was trying to say. All the fragments are there without any duplicates are taken from Zinc databases. That is already available. So we are replacing only with fragments. What it is trying, because there is a presentation for that, due to time limit, I didn't do that. That's why this question came up. So what we are trying to do is, we will not change any 3D positions of this particular bond and this particular bond. The rest of the things we will try to merge them, again considering the 3D conformation. So the position of this particular region and this hydroxyl or oxygen group will never change, but the rest of the region will be changed. How that is done? Through indexing. So they will try to understand the distance, shape, size, everything, and they will search within the database and then try to find out which will be the probable fragment that could fit in there. For example, now if you see within that limit, you can see these are the different fragments. But the disadvantage of this method using any tool, it might not realize there is a protein pocket there. So you can see there is an overlap. That is where we have to define where is the limit or what region has to be excluded, so that the software will take care of that. Okay, this fragment is not okay because it is overlapping with amino acid, which is not acceptable. So those definitions we have to give. So these are the two kinds of reference which I could understand, but if I did answer the question, if not, I didn't not answer the question, please let me know.
Yes, you said it right. Like, but these references which are telling, like 48.1 and whatever we generated right now. So these, what we generated after doing docking site and everything, but I'm not able to, explain what I want to ask is.
Nidhi, what you can do is, I can email
I'll
to
just
Dr.
write
Pillai
to you. Yeah,
and he will
I'll write
reply
to you.
Yeah, let him continue the
Yes.
session.
Yeah.
Yes, sir. Yes,
Yeah,
sir. Please.
no problem, no problem. See, one of the main concern with everybody is how to synthesize them, because this is a software generated fragment being merged. Now, the two simple answer is, based on prediction side, they are confident this is synthesizable because this fragment is taken from a synthesized compound. One. Second, why this fragment is synthesizable or why this could be a replacement? Because they know where the bond formation and bond breakage could happen in organic chemistry. So there are synthetic rules also available. So based on that only, this fragment has been already generated in the database. And that is what is being replaced here. So it is not that simply it is getting merged. Based on linking rules, it has been merged. So there is something called Smirks filter, Smarts filter. I don't know how many of you are into those terminologies. So you will have a little bit more understanding. Now, as Dr. Heyman said, you can always email. So we will be able to respond to you with some paper literature references. Yeah. Another thing is, now we just replaced. Now the next challenge is we wanted to dock and see whether this really works or not. So let us do that. So in this case, what is a replacement I got here is, there is no nitrogen, but there is a epoxide, kind of an epoxide region. Let us try that. So I'll take this replace molecule. You can see here, there is not epoxide, but there's a nitrogen here. So I'll take this and say, add to docking mode. Okay. Now I could see this is my replaced compound. Yeah, that this triangle is there. Keep that in mind. That is identity. Or if you want to rename, you can always rename here. So you double click here. I will say Recore 1. That is my molecule. And if you think that you want to share this project with someone, you want to make some annotation. I'll say I replaced the region within biotin. Check synthetic feasibility with star drop or some other tool, whatever. So I can always include that annotations also. It will tell who has edited all those things. So it is more of a data sharing, all those things. Let us see whether this is able to dock or not. That is the first question. So I'm going to do a docking. Let's see whether this gets docked or not. Yes, it got docked. You can see here recore. Now let's see what is the affinity here. I just selected all of them and I'm calculating the affinity. Okay. I just rearranged, scored them. So biotin is within the nanomolar and micromolar region. Nanomolar and micromolar region, but a recore, what I just replaced, you could see it is not that great. It is having some interactions. It has torsion issues. You can see here, ligand efficiency is not that great. Torsion is also issue. But for this particular conformation, again, the conformation is so far similar to the biotin, but it has a negative contribution on torsion, as well as the binding affinity is not that great. Let us check that. So if you come here, you can see here, yeah, there is a positive energy on that particular atom. So this is what we said, lead optimization, which is 3D, not 2D based, it's a 3D based. The same thing can be done on a 2 molecule. For example, if I'm going to Inspirator, let's imagine I'm doing it in a different way. Rather than selecting 2 of them, I'll just replace this region. Just to resume, I'll just take off one or both of them. And I'm saying just replace this side. Only one side I wanted to replace. That is called growing. Let's say your pocket is a bit larger and your ligand is small, but you wanted to see what are the possible other derivatives that you can generate on the rest of the pocket to be covered so that it will interact with the key amino acids. So that's where you see grow. So when you select only one exit vector, you have not the other one, but this one gets activated. And then it's here it says growing requires a binding site and one selected single bond on one molecule. So here it automatically considers the binding site, right? Automatically. So I'm just selecting this and now it will generate, it will grow the rest of the region where it was masked and it will come up with the possible fragments. Let's see that. Dr. Heyman, can you tell me up to what time I have, because I have star drop also. What is the time limit? Okay, I don't know. Are you able to hear me? Okay.
Sir, we have more 40 minutes, sir.
Another 40 minutes. Okay, thank you. So you can see here when I grown, you can see this particular region. This region gets replaced with some others. You can see that here. So this is what is called the growing. So I'm making it might grow larger or smaller. It depends upon what kind of criteria you are giving in Pharmacophore. You can always define the Pharmacophore, but there'll be a lot of fragments that will be coming as a growing. And there is another approach also where you can merge 2 ligands. Let's say you have a ligand here and you have a ligand here, but you want to link them. So that's what I told you as best example was PROTACs, because in PROTACs you want your job is to find out the linker between the 2 ligands. So those are the opportunities within the Inspirator and the docking. Now, when coming to docking, if you want to export some data, all right, so you can select which of the data that to be exported. I'll uncheck. Yeah, I'll just select some of them. And then you can click the save button and you can export it either as a XLS file or SDF file. So it will export the picture. It will export the smiles. It will export all the affinity other data. Even numerical values also will be there with a range. It will not just tell you this is this nanomolar. No, it will tell you between this nanomolar and this micromolar. It will give you numerical data. Now, if you want to transfer these files directly to StarDrop, you can just click on this. If it is installed in the same machine, it will go to StarDrop. Now, let's say you wanted to generate a 2D depiction structure, hope you have seen in PDB, you have a 2D depiction. So for that, we use Protein Plus. Protein Plus is a seamless which in other. I'll just try one HTTP and go. You will be able to predict the binding pocket. You will be able to generate a ligand interaction sites. All those things can be done. It has a lot more information and load more analysis also can be done. I'm not going too much detail into that. I'll just go to post view, which is a 2D interaction diagram. I'll just click on post view and I'm saying this is my ligand and yeah. So that is getting added here. When you click on the ligand, the BTN is added here and I just calculate. The same way what you can do is you load the protein and you load the SDF file of your docked pose and you will get a 2D interaction picture like this. I hope you remember this is the same picture which comes in RCSP website also. This will be very clean and crisp without any too much of interactions being shown. Only the key ones are being displayed here, including the hydrogen bonds and hydrophobic interactions. So there we end with the first demo session on CSAR. Now we are jumping to the second one, which is a StarDrop. So let's move forward. Now, whatever we do with docking, we're just identifying a hit molecule. That is where we call it as hit identification. We never identified a drug. We just identified a hit molecule. The same is the story when you try to do wet lab studies like bioassay studies or IC analysis. There also we are trying to identify the hit molecule. Hit molecule confirms that you have found the right target for your disease target. But we have something to explore. If there are pharmacology students or much knowing about PKPD studies, pharmacology, we want to understand how far your drug is affecting the organs and vice versa. So we wanted to know how far your drug is safe, how far the drug can be absorbed through the human intestine, and whether the drug will be stable, metabolically stable when it passes through different metabolic pathways, including P450. And what is the permeability, or flexibility, and metabolic stability? All those docking doesn't mean that you found a drug. You have to ensure whether this drug reaches your target in a proper manner. Because when you're doing docking, it is on a micro level where we are assuming your drug has already reached the target and we are docking it. But when you administer through orally or sublingual or dermal, we have to ensure it has to go through several processes of absorption and all. At the end, it has to reach. But when it reaches the target, whether it will reach in a proper way as we docked, or it gets breakdown and forms a metabolite. That is what we are trying to see. So we wanted to look at a multi-parameter optimization step to how far these we have to identify or the chemistry with an optimal balance of these properties. Identify when such a balance is not possible. This is what I was telling you from the beginning. The failures will also increase the cost. So fail fast, fail cheap. Only when confident you move forward and avoid missed opportunities. For example, Lipinski rule of 5. If you ask me, most of the time I have seen many papers, they simply, the first step they do with the database filtering is Lipinski rule of 5. But the question is, how many people have read Lipinski rule of 5's paper? Maybe very few. It is for oral bioavailability. But if you're doing for something else, why do you need to consider Lipinski rule of 5? Now, the student usually tells me, because others have done, I also have done. So it is not that. For me, a tool or an approach is applicable for but for your project, your objectives might be different. Your target might be different. So you have to make sure which is the right approach that you have to use. So avoid missed opportunities by using the right method. Data overload is always a challenge. Other than what is shown in the slide, let me explain, give another example. I hope you will be able to answer this question. I need an answer from the audience. Let's imagine you have 10 different compounds. You did docking, all analysis, ADME, everything fine, and you reached to 10 different compounds. With that 10 different compounds, you wanted to do wet lab studies. It could be metabolic stability, toxicity, absorption rate studies, and many more. So 10 different experiments have been done. Ultimately, you want to choose only 3 molecules. So from the 10, you want to choose 3 molecules based on the 10 different experiments. For example, if I am asking you to select the best 2 molecules of from the 10 compounds from a single experiment, it is easy because either the lowest concentration or the highest value, whatever you will take, the best 3 you will take. But here the challenge is you have 10 different experiments you have to consider in order to choose the best 2 molecules of the 10. Sorry. So could you please tell me how do you choose that best 3 molecules from the 10 considering all the 10 experimental data? I'll wait for a few seconds. I don't know whether it is in the chat box.
We can choose the molecules with maximum better results. Suppose 6 of the from 6 of the methods we get good results. So
you mean to say among the 10, if 6 of them gave good results, 6 compounds good results, which one is having a better result, you would pick up them overall?
Overall, yes. So by comparison, by comparing all of them.
Okay, good. And any other answers? I'm just looking at the chat also, or even in the question Q&A also. I'm okay to see it. Oh, some questions came in, which I will answer that. Okay, since I don't have any answers from you, I'll continue because of time limit. So to partially the answer was correct. What we have to understand is, I'll just tell you a simple example, maybe after the few 2 other slides. So I'll tell you the answer. So data we have from in silico, in vitro, in vivo. Now, how do we select which data we wanted to do? That is based upon prioritize, means importance. It is not which is good or which is bad. Which property or which experimental analysis is more important for you to make decision to choose the compound as a drug candidate? So computational studies are to help you to take decisions, not to find a drug molecule. Keep that in mind. Okay. So another thing is uncertainty. Whenever, see, everybody, including me, during our +2 or pre-degree, we have understood that we did titration, right? During titration, we took 3 readings and we reported deviation, mean, median, whatever it is. In schooling, we learned that we need to have repetitive experiments to overcome errors or uncertainty. But when we grown up with a very advanced research, why we are not doing repetitive experiments? Because this is very much mandatory in order to overcome uncertainty. When experimental variability is also there, and when you predict something using software, do you think it is accurate? No, there should be error. There should be standard deviation should be predicted by a software or a model. Very, very important. So prioritizing the properties based upon importance and uncertainty. These 2 are very much trivial. And finally, the selection of best molecules. Most of the time, how do we select molecules? We click on a button, rank it, which one is having the highest or lowest score or lowest energy, those are the best molecules. Easy job. No, that doesn't work. That is the reason why from experience, many people said that when they just based on best score or best lowest energy, they just choose some compounds. At the end of the day, when they test it, it might not work. This is just because we have not looked into many other aspects that to be considered. That is called multi-parameters. So drug is not a single parameter. It is a multi-parameter. Things has to be sufficed. And one more thing is, as a chemist, when you want to make decision on which chemotype you wanted to synthesize, or what you want to finally patent or whatever others, you have to consider both quality as well as diversity. For example, let's say 100 compounds. From 100 compounds, I did all docking, all testing, everything. My first funnel of filtering, I have to select the best 20 molecules. How do I select the 20 molecules? Do you think just based on ranking of the best values? No. I will give 75% priority to diversity of my molecule, means different chemotypes I wanted to select. Only 25% I'll give to quality. Do you know why? Even if the prediction used by the software is wrong, I still have some space within the diversity where it could be a better molecule. We don't know, we have to try. So it is manual, not software automated, and no software is there to do this job for you. So keep that in mind. So don't think clicking is a job to get the research done with the drug discovery. You have to analyze each and every step, which I used to repeat in all my video sessions. So quality and diversity should be balanced to keep the selection of molecules. I don't want to confuse you, but I'm telling you the right information to make you get through with the right decision making for drug. And another thing is that prioritization. Usually we try to do some kind of prioritization. One take them up. Sorry about that. In between, my internet got disconnected. I think now I'm reconnected. Okay, yeah. So you have set of molecules, assuming one compound will be your best drug molecule, and then you test it for potency, and then you removed some of the molecules which are inactive, and then you have some set of molecules which is selected to be good, and further you carried out absorption rate studies, and again you removed some of the molecules which does not have good absorption rate, and then you have some molecules for the final metabolic stability studies. After doing metabolic stability studies, you found the best molecule. This is usually we think, and I have done it earlier, which I now realize it was a mistake. In most of the cases, from the history of studies and publication, we know that this is most of the time doesn't work well, and we end up getting a bad molecule. This is just because even though your compound is more potent, doesn't mean that that compound is absorbable. Doesn't mean that it is metabolically stable. Doesn't mean it is non-toxic. Now, this is a place where the medicinal chemist or the pharmaceutical chemist comes into the picture, where I can optimize the compound. I cannot simply avoid that compound because it's highly potent. So how I can improve or enrich that compound? That is where we are looking at giving importance to specific property. This is the answer for that question. So we do have specific properties or experiments, and we do have desired values to filter them, but ensure you give the level of importance. Just a small example, Lipinski rule of 5. We say molecular weight less than 500. Okay, that is what is our rule, and we are going to take it. Do you think a compound with 501 molecular weight is a bad molecule? Or do you think a hydrogen bond donor with 6 hydrogen bond donor is a bad molecule? I don't think so. So when you give a hard set desired value, the software automatically obeys you. Okay, anything less than 500 I'll take, others I don't take. But 501 is also a valid molecule for you. So when you give the importance, the software will be able to consider 501 also, but a lesser or a lower priority is being given for that compound. That's all. But it is not that we are completely avoiding it. This is what I was telling you about missed opportunities. If you're not doing the filtering properly, you're missing some compounds. There are many published papers available to give you these examples. So this is one of the published in 2010. Sorry, I didn't put the citation. Sorry about that. So this is about the CNS drugs. So Pfizer candidates, they were able to do find around 60% of the Pfizer candidates on a normal conventional way of filtering. But when they applied multi-parameter optimization, they found extra 14% of marked CNS drugs. Multi-parameter optimization is a terminology in M-Pharm pharmacology CAD paper. I have seen that. So this is what we are trying to say. So we want to give importance with the desired and the properties to understand how an optimal balance of all the properties could be considered for selection criteria. That's where ADME comes into the picture. I need not to tell you what is ADME, what is like A is absorption, D distribution, M for metabolism, and E for excretion. But this is all done based upon QSAR, right? Professor Kunal Roy will be anyway talking about QSAR. Otherwise, you can always check my reviews. There are 2 reviews on QSAR, which I have written in 2012, almost 8 or 9 years back, still valid points. And also have some of the discussions in YouTube by me for QSAR. So please look over that. I don't want to spend too much time here. The main thing I wanted to talk about here is, don't think simply getting a better R-square gives you a meaningful QSAR model. No, never, ever. So if you think that R-square I got 89, and if your descriptors cannot be correlated with your activity, doesn't have any meaning, because we are talking about biological activity, not a physical or a chemical property. Physical chemical property, of course, we can quantify them too much. Biological system, we need to have a causation. So that is always a topic of interest where we talk about correlation versus causation. When you talk about biological activity, there should be physical significance and relevance of your molecular descriptor with its activity. If there is no relevance and just getting R-square doesn't make sense. So please keep in that mind. And too much of descriptors is too much of noise in the model. So select relevant descriptors. Clicking a button, getting too many descriptors doesn't make sense. Try to generate even manual or custom descriptors which is relevant for your activity. Those things has to be taken care. There are several machine learning based methods can be used, of course, in StarDrop also. So like random forest, Gaussian process regression method, then PLS. Now, I know even myself published a lot of papers using multilinear regression methods. Keep in mind, multilinear regression method generates lots of false positives, and it has its own issues on overfitting and many other problems. Unless your data is proper and your validation is proper, MLRs will be a bit tricky. So whenever you are splitting your data set, try to split your data set into 3. I know so far you would have heard only 2, but 3. Training, validate, and test set. Training and test set is where you get, from training set you get R-square, from test set you get Q-square. But validate is what you're trying to do is, you're using the model that is generated from the training set, and you manually try to predict the set in the validate, and you take an R-square. And then you have to see if it is greater than 0.5 or 0.6, something acceptable. So you're revalidating yourself to understand whether your QSAR model is reproducible and reliable. Not said by me, by many experts in this field has said that if when you take 1000 papers of QSAR, only 10 or 15 of them are reproducible. Others are not reproducible. Don't ask me the reason why, I've never tested it. But when you do QSAR, domain of applicability is very important. And let me explain this in a very simple way. Let's imagine you have a set of compounds within this training set, and that is called the domain of applicability. Now you are bringing in your compound to predict the activity for using this model. And if your compound is within the chemotypes of this training set, the standard deviation or the standard error of the prediction for your compound by this model will be less. If the prediction of the activity of your compound is slightly away or the applicability is away from this domain, then the standard deviation will be slightly higher. If your compound is completely dissimilar and away from this training set, the standard deviations will be more. That means uncertainty will be more. The results are unreliable. That doesn't mean that this model is bad. That tells you that the type of chemotype you use for your compound is not present in the training set. That is what you have to understand. So personally, for me, any software which predicts ADME or any property, it has to give standard deviation. The standard deviation tells you how far it is away from the applicability or domain of applicability. That means how far it is away from the training set. If it is being claimed that no standard deviation is not required, everything is accurate, come on, it is prediction. It is statistics based prediction or machine learning based prediction. There should be a standard deviation. So that is what importance of domain of applicability is being said. And the challenge is that data imputation. Most of the time you do not have experimental data or assay data. That's where you do imputed assay. Data imputation is something that is already there in statistics, but now we use deep learning methods to come up with that. So this method is already being applied since 2019 and has seen a great success in imputing the assay data also. So finally, when you can combine all this to put together, you are reducing the communication gap between a chemist, a programmer or a modeler, and a computational chemist, where they all understand each other. So this is the success stories of CAT. These are the below 3 references. There are 2 reviews and 1 blog. It is not that just using software they found the compound. No, softwares were able to assist them. And don't think that just using one software they found this drug. No, I know about 4 of these companies, drug discovery team, where they used more than 6 softwares, commercial softwares, including free. They use in order to come up with the conclusion. So don't think that just with one software they can do everything. There are multiple levels of trivial importance being given. So let me go to the demo for StarDrop. For StarDrop also I have given you for StarDrop. Okay, so everything is fine. Okay. So for StarDrop also I have given you the tutorial material. Just a minute, some presentation. Okay, I hope you are able to see my screen, StarDrop. Let me do it again. Yeah. So StarDrop, I have already given you the tutorial, the PDF file and a sample file. The sample file is a zip file. You just extract it and go to file, open, and just open it. And you will see something similar to this. Okay. Now, what you can do is models. So here you can see others won't be there. The custom won't be there for you, but the StarDrop models will be there. You can predict all the ADME properties here. Aqueous solubility, 2C9, partition coefficient, Hurg liability, that is cardiotoxicity, blood-brain barrier, human intestinal absorption, PGP, and many others. So like here, you can see all this green are predicted. So I was too much talking about standard deviation, applicability domain. Where is it? These are all the values that is predicted from the models. So if I click this, it will also tell you what is a standard deviation. Now it is telling you this particular aqueous solubility 1.03 is a standard deviation. That means this is kind of an okay result, not completely reliable. But this one, this particular structure, 4.5, it is having a standard deviation of 0.7. That means it's much more closer to the training set. So that's what I was trying to tell you. Standard deviation in QSAR or ADME or toxicity predictions are very, very vital to justify to the experimentalist, this is a standard deviation of my predictions. Then only experimentalists will believe your data, which is coming out of prediction, right? Now, Now, let's also look at some other data just to do some analysis. So I just predicted the ADME properties. And now I wanted to talk about the multi-parameter optimization. So here I am choosing this hide PKI. So I am saying the estimated PKI value should be greater than 7. And this is my level of importance. and aqueous solubility should be greater than 1. Just a minute, I will switch off this. Yeah, so aqueous solubility is of should be greater than 1. I want industrial absorption to be positive, and Hugh liability should be less than 5. These are all which is standard, which is something similar to Lipinski rule of 5. But let's see what does this importance does mean. I'll just double click this and you can see what is the coverage. Now let me reduce the importance level. Okay, this doesn't give much example. Let me go to this one. Yes, here I can explain. I'm telling anything from less than 7, I'm 0, rather I'm giving a score as 0.05. That means it is still considered but not given priority. But any compounds which is having greater than 7 as my affinity or estimated pKi value, I'm giving a score as 1 with more confidence. Now let me try to reduce the importance level. I just make it importance like lower. I say this particular property is of less important, maybe 50% important to me. Now you can see anything less than 7 is of 0.5 score. Anything greater than 7, it's still 1. When you're saying importance level less, it is going to consider more score on the data or the compounds which is not satisfying greater than 7. So I'll put back it to the same importance. Okay, so maybe, yeah, 0.95 is the importance level I have done. And then if you think that you wanted to add manually something else, you can do that. You can just drag and drop it here. So that also you can give the flexibility. If you want to delete, you can select and delete it here. So now the question would be, how do I know what is the importance? How do I know what is the desired value? So here you have something called as build profile. This is a patented method where you can again do something similar to QSAR, and it will generate the importance level and desired level. I'm not doing that right now, but I'll quickly show you some value sensitivity and importance sensitivity. So this also we generated using the software we have generated this. So this will be telling you which property is more important to your particular overall decision making, and which one is less sensitive and important sensitive. All those analysis will be given. So this is a I could share the paper if anyone is interested. Now, let me come to the result analysis, a quick result analysis. Based on the pKi value, I'm telling you this compound is the best one. 8 higher the pKi, the best. 8.142, which is a row 731. So I'm saying this is the best compound based on the pKi value. I considered pKi other pharmacokinetic properties together to make a decision, right? And then now I generated a score from 0 to 1. So whatever I'm doing the analysis of scoring, I get from 0 to 1. Let's see which one is having the highest score. I'll click the right button and say descending, and you could see something happened. The compound which is having, that is row 731, the compound which is having 8.142 is having a score of 0.29, and it has gone to the 20th rank. But there is another compound which has come to the top, which is having a high pKi value of 7.52, okay, and the score is 0.41. Let's analyze what has happened. Even though the pKi value was higher for the other compound, but the model did not generate that is the best optimal molecule. Why it did not happen? Let's check that. So I just selected this molecule. Here you can see log S. I'll talk about this color in a moment. So there are some colors like blue. I'll tell you about in a moment. So I selected log S, which is aqueous solubility, which is 4.18, and there is Hugh liability, which is 4.55. Okay, keep these two values in your mind, log S and Hugh, 4.55. Let us go to the 20th molecule, which is having a very good pKi values. So I click on this. You could see the Hugh is 5.6. In our scoring model, we defined the Hugh should be less than 5. I don't want anything more than 5. Good thing is the software did not completely neglect that compound, but it gave a lesser score, lesser importance. So Herg, this particular compound, which is having a higher pKi value, is having 5.6. Let us look at the log S value, that is aqueous solubility. It is less, 3.8. Of course, anything greater than 1, it's acceptable. Higher the value, higher, better, right? So here it is 4.18. So even though your compound was very highly bioactive, biologically active, but it was cardiotoxic, for Herg liability was there, then it will be not a good candidate for you. Let's do another visualization concept, then I will come back to this coloring thing. So here I require this, but let me take this out and then I will tell you. Okay. Yeah, let that be there. And I will plot a snake plot. So snake plot is something that is defining the red color and the yellow color. The red color is defining any compound with highest score, 0 to 1, right? And yellow color dots are compounds with lower score. If you put mouse over your mouse on the points, it will show which is the row and which is the compound, all will be displayed here. Now you have some lines here. What are these lines? These lines are again the standard error or the deviation. So for each prediction, we are giving you standard deviation error. Now you might think that because the y-axis is the score from 0 to 1 and x-axis is 0 to 150, that means the number of compounds. So here we have around 124 compounds. You can see rows 124. So 124 compounds are loaded here. So among the 124, I am very confident to select these many compounds to move forward with my studies for the next level of studies, because the compounds are optimal with all the score, right? Including pKi value, pharmacokinetic properties, and toxicity. And I'm very much confident not to consider these molecules because the particular score is very, very minimal. Not like less minimum, but very minimal, very close to 0. So it is not at all very close, not at all to be considered. Now, when I'm selecting this best, let's say some of the best molecules, okay, I cannot say this is the good decision finally to get into drug because there are many more analysis to be done within this package for many other optimal balance. What I want to show here in this graph, this is called chemical space. I don't know how many of you know difference between chemical space and clustering. Looks similar to clustering, but why I want to showcase you this is, I have colored this based upon shape, size, everything is being colored. I have shaped based upon the estimate, pKi value. Lower the pKi, lesser the size. Higher the pKi, higher the size, larger the size. And the color, yellow color means a lower activity or lower score. Red means higher the score, which I discussed earlier. And anything with a negative symbol, cross symbol means it is positive, means blood-brain barrier positive. Anything with a sphere or circle or round shape is the blood-brain barrier is negative, right? Any compounds having red border is having positive human intestinal absorption. And any one with a black border, I think someone was here, some around here, the black borders, they are having negative human intestinal absorption. Now, finally, what I want to tell you is, even though the structures are similar here in this cluster, you can see there are some compounds still not active or not working, even though it is biologically active. So what we are trying to infer from here is a few things. Even when you're trying to do structure-based similarity search, don't think that the biological activity will be same. Its physiochemical properties could be similar, but biological activity will be same. But bioactive conformer pharmacophore screening is more viable because you will be able to get similar bioactive conformations with those pharmacophore features. So you have to be very careful when you're trying to do 2D similarity search based studies to expecting you will also get similar biological activity. There are many more other parameters
we have
that to be considered.
5 minutes for the question and answer session. After
Sure.
5 minutes, we can have an answer.
Sure. And finally, I'll finish off this. So we have P450 also, which is for predicting the metabolic stability. I saw this was one of the question there. So if you have given a compound, the software will be able to predict which part of the atom or which part of the molecule is unstable or prone to break down in which isoform. So here in 3A4, this particular carbon is prone to break down, and it will also tell you what is the percentage of the ratio. So this we are trying to predict based on quantum chemical calculation. Professor Bharatam also has published some papers a few years back on a specific metabolic stability prediction using quantum chemistry. So similar kinds of technologies being used here on different isoform. Apart from that, in StarDrop, you can do 3D Pharmacophore, designing new molecule, and many more other features. If you want to do some optimizations and also chemical transformations, all are possible here. I'm not extending because already time is up, but finally, if you wanted to make some not isostere, but a replacement or a chemistry transformation, especially by metchem and chemist. For example, if you're transferring from carboxylic acid to phosphonic acid, most of the time you might think whether it is reported, but here there's a database which tells you a literature where they have already reported the transformation from carboxylic acid to phosphonic acid. As well as it will also tell you what kind of toxins has to be removed. Means what are the possible reported toxins or unsuitable drug fragments that can be added to new design of molecule. Those can be also filtered. So by this, I would like to conclude my session, and these are my contact details. So if you have any questions right now, I am happy to answer. Thank you so much.
Yeah, now session is open for question and answer. So whoever have any question, they can ask. Or if they are not having access to the mic, they can write their question.
Hello, sir.
Yes.
Yeah, please turn on your video, introduce yourself, and then ask question.
Hello, sir. I'm Vaidehi.
Yes, please.
Guwahati. I want to ask the question. Like we are performing QSAR using the various other softwares like Maestro and Codesa. Then in what parameters this Gestra innovation it's more useful than the Maestro or Codesa?
Okay. So see, Codesa is from Professor Alan Katruski and Matty Carolson. That's where I did my PhD. So Codesa is very well known. We were working on those descriptors and others. Now Codesa mostly uses MLR, multilinear regression method. Descriptors are, if you ask me, in Codesa, the original descriptors may be only 120 or 160 descriptors. All the others are derived descriptors. I hope when you look at the the manual, you will be able to understand that. And the descriptor calculation is being made from AMPAC or MAPAC. Both of them works there, right? Now, I clearly told you, you have to use 3D bioactive conformation in order to generate 3D descriptors. That means from the docked structure, you have to generate the descriptors. It is possible in the command line in Codesa in order to, without doing any 3D optimization to calculate the descriptor, their option is available. The only disadvantage is that you have only MLR there. That is best multilinear regression method, or PLS will be there. But when you look at machine learning models, I don't think so. It is being updated so far. Coming to other tools, I don't know, because yes, sir.
ANN is there. Artificial neural network is there. Somehow they have incorporated. But anyway, so yeah, you continue.
Yeah, ANN is there since 90s itself anyway. But the problem is reproducibility is always a challenge. So you can always predict the accuracy, but reproducibility is always a challenge. So that's why I didn't mention that. It's a bit old ANN. Maybe recently they might have updated, I don't know. Other softwares, I will be not the right person to talk about, but let me tell you, whatever that here, StarDrop is basically completely machine learning based, where Gaussian process regression is used to avoid overfitting. Reproducibility of the models is seamlessly okay, because when you generate a model, you can use that model to predict the activity for other molecules also. What is the purpose of generating a QSAR and publishing it? Because others have to use it and make the prediction. That is what ultimately looking for. So very few papers only publishing the models for others to use, and that's why Pass Server is very famous, because Pass Server, whatever they publish, they made it as a tool for others to predict the activity. So you cannot compare it. Use all the software. Which one is giving the less standard error or standard deviation with good significance of your descriptor with respect to the biological activity? That is the best one. So if you ask me, I have tried 6 softwares during my PhD days, and each 6 worked in different projects. I published more than 38 papers on QSAR. If you ask me, I never use same software in all papers because some doesn't work for others. So it is not that I keep my gold standard, this only I'll work for all my products. Doesn't work. So for example, recently I started using QSAR-ins also. I have few papers on QSAR-ins from Polar Grammatica. It works fine for some, not for all. So it depends. So you better not to compare, rather use all and understand which one suits with your kind of data available with you.
Okay, so anyone else have any question or any interaction?
I saw one question in the chat. Can we predict the probable metabolic and degradative pathway of any drug on the base? Oh, I think I already showed you at the end of my slides for that question. Yeah, I can see all the questions are the old ones probably.
Yeah. Anyone else want to ask anything?
Okay, no problem. All the licenses will work for more than a week, and you can try with the PDF, and you have the email addresses. If you have any questions, you can always feel free to write me or to Dr. Hemant. Will be able to help you out.
Yeah, so emails are available, and this video is also available on YouTube if you want to rewatch, or if you have missed something due to connectivity or anything, you are always welcome to our YouTube channel and then see that. Thank you so much, Dr. Pillai, for your very informative and detailed discussion and demo, and for your talk. It is really helpful for all of us, and thank you so much.
Thank you so much, sir. Best wishes to all. Bye.
Bye-bye. So now we will continue with our hands-on session, and we will be going from QSAR to molecular dynamics using Gromacs, which is a freeware. This will be taken by Anvesh. Anvesh, you are around?
Yes, sir.
Okay.
Good evening, sir.
So I suggest to start from Gromacs because we have limited time, and if time permits, you can explain Autodoc.
Okay, sir.
So suppose you have already performed Autodoc and you have the dog pose. Now how to do molecular dynamics simulation using Gromacs, starting from very basic till the simulation result analysis and all. So over to you, Anvesh. I don't need to introduce because Anvesh is going to talk maybe a few times in this. So it's already introduction is over. You can directly continue.
Thank you so much, sir. Am I audible? Can anybody confirm?
Yes, you are audible.
Okay, thank you so much, sir.
And your presentation is visible.
Thank you, sir. So good evening, dear participants. So as sir mentioned, although I had to do both session for docking as well as molecular dynamics, but due to scarcity of time, I'll be starting with Gromacs, molecular dynamics, and then later on, if we get some time, we will move on to Autodoc also. So let's begin with the molecular dynamics session first of all. So I would like to mention that to all the participants, the necessary files and other relevant information and even the simulated results have already been mailed. So I would like just ask them to kindly follow, and in whatever step they have any doubt or anything like that, they can either write in the chat box or they can ask in the middle also. That's not a problem. So we will start by molecular dynamic simulation using Gromacs. So first of all, I would like to mention that we need to have following files in our working directory. We need to have a few MDP files, 5 of them. I have already mailed all those files, etc. in the zipped folder. So kindly follow and download and keep on matching the results. And if you have any doubt, you can already ask us, or you can write to us regarding the same.
Turn on your video, Anvesh.
Okay, sir. Is it visible now? So it begins with parameterization of ligand as well as parameterization of the macromolecule. Here the parameterization protocol that we'll be using is amber force field. Why? A lot of studies has been done on the variation of the force fields, like Gromacs has a lot of force fields. We'll be seeing, I think around 15 of them are available. And depending upon our task or the kind of study we want to perform, we would switch on to whatever be the kind of force field that we need to do. Now, the question arises, which force field is better for what system? And I would say that to the best of my knowledge, no clear answer has yet been reached that as to what force field is better, what force field is bad. Everything is good, everything is bad. You just need to stick to your own protocol. You need to stick to your software. You need to believe your procedure. You need to believe your software. You need to believe your results. It's just that you have to interpret them. All the result, it depends upon the interpretation only. So we will start with parameterization the ligand first of all, and for which we have a Python script ACPYPE. This script has already been provided. It reads the mol2 file of the ligand and it generates all the necessary information that is required for the Gromacs topology files, ITP files. All the files are generated using this Python script. For the ligand parameterization, we use this. And once we have obtained all the necessary files, we move on with the simulation, and then we incorporate them in our topology files, and necessary relevant information is extracted from them, those things. And then we proceed with the molecular dynamic simulations. So I think the execution is going on. So I have already mailed you people all the data sets. So I think I should stop this simulation because I have already shown the commands and I have already prepared a separate folder for each and every step. So likewise, we can move on with the simulation instead of waiting for the simulation to complete. If anybody has any problem, they can ask.
Hello, sir.
Yeah.
Is this a script for the preparation of the ligand or just for ITP files?
No, it will produce all the possible ligand parameter files, whether ITP or GRO or mol2 or PDB, all the necessary information which a Gromacs software requires for the ligand, it will generate. This script will generate all the necessary information.
So we don't need to further to improve or modify the ligand.
No,
or
nothing.
Prepare the ligand.
Nothing like that. It's just prepared by the script only. So let's move on to the next folder. I have created, I told you that I have created folders with all the relevant information so that no time is wasted in creating the, in simulations. Now we will open this ligand.acpype folder. We would see the list. You can see so many files that are required. are generated. However, we need for MD simulation, we need only two of it. That is these two files, ligand_gmx.gro file and ligand_gmx.itp file. These two files are only required for our molecular dynamic simulation. These two has the Gromacs parameter and the topology parameter files for ligand. So we would copy them into our folder. Now the next step is parameterizing the macromolecule. The macromolecule that we have chosen for today's demonstration is DNA. The commands have already been sent to all the users. The command that is used to parameterize to generate the topologies for DNA is gmx pdb to gmx minus fdna.pdb. It generates an output file known as conf1.pdb and water model that is used is tip3p. So let's execute this command and see what files are generated. So as I already mentioned, a lot of force fields are available in Gromacs. Since we have parameterized our ligand using Amber force field, AC pipe script is a Python interface between Amber and Gromacs. So it creates Amber topology file necessary for the execution of Gromacs on the Gromacs software platform. So we will also choose the similar Amber force field for our preparation of the DNA also. So we would use here the first Amber 03 protein nucleic acid force field. The citation is already mentioned. So if anybody wants to get more information regarding this force field, they can already go to the citation and download the paper and read about this force field. There are several files generated. It is conf1.pdb and topol.top file. These two files are very important. What we right now need to do is visualize the topol.top file. This is the basic structure of a topol.top file. What it contains? It has some basic information about the version of the software, the command that is used to generate this file. Now, the relevant information starts from this, where the cursor is placed. It has a commented section. It starts with semicolon. So it will always give you a brief idea about as to what is it will give us a brief idea about what the particular line means. So this line says include the force field parameter. What force field? Whatever force field that we have chosen. Currently we chose Amber 03 force field. So it has mentioned the similar force field. We need to do a few editings in this file because we have incorporated the ligand parameterization also. So we need to include the parameters for ligand also in order to make sure that our simulation of a ligand DNA complex system goes well. What are the parameters that are to be included inside this file? Let's see. We have to include the chain topology for ligand, which is highlighted over here on my screen. We would copy this and simply paste it. I would like to mention to all the participants that please be very careful regarding the spaces, the hyphens, the dots, the commas, the full stops, the inverted commas. Any error would cause an error in the simulation protocol. If you make any error inside this writing the topology files, the software will not be able to adapt accordingly and would display an error. Obviously, different people would encounter different errors. So, and mostly I have experienced that most of the errors are already available over internet, and our experts of Gromacs have answered most of the queries, but still it is better to be careful during the simulation and avoid errors. However, human errors can never be avoided. Secondly, we need to incorporate in between chain topologies and water topology. Remember, in between chain topology and in between water topology. At this point only we have to put the information. What information? That has already been sent to all the participants. Towards the end, we have to include the ligand also. Suppose if somebody writes LIG in place of ligand. So as I mentioned, it is case sensitive, word sensitive, text sensitive, special character sensitive. So it's a very sensitive program in terms of what is being written. Computer won't be able to decipher as to what are you trying to communicate, because a definite protocol has been provided between the user and the simulation end, so as to establish a better communication, so as to make sure that whatever the user is trying to do, that only is transferred to that information is only transferred. Suppose if I put LIG instead of ligand, it won't read it. It will display an error. So let's not do that, and make sure that whatever information is provided in the files also, that only we mention in the terminals. Better in writing, the better we produce the writing efforts, the better it will be give us the simulation results. Next, what we need to do is we need to concatenate the ligand, the conf PDB file and ligand PDB file, and generate another conf one, that is the complex PDB file. If we visualize this conf1.pdb file, towards the end we can see the ligand parameter has been concatenated. However, we would like to delete all these lines. So now our basic preparation of MD is done. The system is now ready to be simulated. So the very first step of a molecular dynamic simulation, that was ligand topology and DNA topology. We have successfully covered this step. We have successfully created a ligand topology, as well as we have successfully created the DNA topology. Now we can move on to our next step. Now let us see what's the command for the next step. The command is the screen visible to everybody, or should I? Okay, fine. Okay. This command refers to. Okay, fine. Thank you. This command refers to edit conf. See, every time we'll be writing GMX, because GMX is a definite protocol to call GMX, Gromacs, information, Gromacs softwares, whatever information is provided inside it, we call it using GMX. And then there are different modules like edit conf, solvate, grompp, gen ion. We'll be seeing it in the upcoming session also. Edit conf, it will generate a solvation box. The box will be of dodecahedron type, and the dimension will be of 1.2 angstroms. So let's execute this command and see. We can see towards the end that the information about the solvation box is mentioned. So we can note it down so that we can mention this kind of information in our literature while we are reproducing the literature in the form of a paper or a review article or whatever. So these sort of informations are also mentioned in the log files also. But however, if somebody wants to follow up, they can write it as per their requirement. Next is solvation. Earlier we created a box. Now we are solvating the entire drug DNA system. Solvate is for solvation command. New box, whatever the box that we created in the previous command, we are now solvating it. Topology means whatever parameters that are to be that are required for the solvation has been mentioned in the topol.pov file, and output file that this command will be generating is solve.pdb. Now let's execute this command and see what it says. We can see on the terminal that the output configuration of the system is mentioned. The volume, the density, the number of solvated molecules, all these are already mentioned in the log file also and on the terminal also. So whatever solvation results that we are getting is mentioned here. Now we are trying to ionize the system. Ionizing the system is very important because sometimes in the biomolecular systems, what happens, the system is not neutral. So ionizing it would help the system to get neutralized, because biomolecular systems perform good simulations only when there are neutral systems. So first, this command would neutralize the system. It will give us a ionic information as to what is the current charge of the molecule, and we would then get rid of the charge by editing another command to it. So let's see what is the charge first of all. So overall, we can see that in this line, the system has a non-zero total charge of minus 22 point this much. So what we would do is, in the next command, we would provide a positive ion with plus of this much, that is plus of 22, so as to neutralize the entire solvated system. So let's try to do this. Instead of 20, we would write 22. Why? Because in the previous step, we found that 22 was the positive charge that was required. So we mentioned positive of 22 that was required to neutralize the entire system. Now let's see. Now it is asking, a prompt message has displayed upon the screen, and it is asking us to choose. We have to, since we are solvating the system, so we will choose 6 over here. Choosing 6 will neutralize the entire solvated system. Now let's see what output do we get. See, all the atoms are now replaced with for neutralization sodium atom, and the entire system is now neutralized. Now a very crucial step in molecular dynamics is energy minimization. Why do we need to minimize the energy? Because if the energies are not minimized, a lot of distortion in the system would be offered because of the interactions occurring between biomolecular system. Since it is a biomolecular system well solvated with properly ionized, so we cannot, as of now, we cannot predict as to what are the possible interaction happening inside the system. So we need to bring the system to a energy minimized state before starting our simulation, production simulation, or maybe equilibration, whether NPT or NVT or whatever be the kind of simulation that we have to do. We have to first of all bring the system in its lowest possible energy state. So this command, it brings the system to its lowest possible energy state. It minimizes the energy. So let's see. I would like to mention that in this MD run command, we offers visualization, that is whatever processing that would be going on would be displayed upon the terminal. If we remove this, it will not be displayed. But since we want to follow up with our simulation results as to what is currently happening, we would put it over here. NT refers to the number of cores and the number of processors that would be using. So since I am demonstrating this simulation on my laptop, so I would use 4 here. If somebody is doing it on their desktop or workstation, they could increase it to 8 or 16 or whatever be the amount of cores and processors available. So let's put it 4, and EN is the energy minimization. So let's see the output of this. So as I mentioned that it has used the 4 OpenMPI threads, and we can see that the energy minimization is going on. Once this step is completed, the energy minimized and the force etc. information will be displayed upon our terminal. So let's see the output of this command, and then we will follow up with the simulation protocol. So as I mentioned, we can see that the potential energy of the system is minus 3.5 into 10 raised to power 5. The maximum force that is occurring between the system is this much. The normalization of the force is this much. So moving on, I would also like to mention to the participants that during the preparation of the tupol.top file, we have added a line, that is ligand position restraint. What this line does is it fixes the position of the ligand. And another line that we added is ligand gmx.itp, that is including the ITP topology parameters of the ligand. So right now what we are going to do is we are going to restrict the ligand to a particular position. Let's see how does this happen. It is prompting us for choosing our output, whether system or any other thing or ligand. Since we are using this over ligand the gmx.gro. In the very beginning, before starting the MD simulation, I had demonstrated that we copy several files from the generated using the Python script. The two files were ITP file and GRO file. So that GRO file is the same GRO file that we are using currently. So we would use the two, that is the for ligand, and let's see. And now our ligand has been restrained to a particular position. Now it is prompting us to make an index. It is prompting us to make selection for our simulation. We can see a long list over here: system, DNA, ligand, sodium, others, ligand, sodium, water, solvent, non-water, ions, ligand, and water ions collectively. So since we are performing minimizations over DNA ligand system, so we would choose one. We would insert a pipe. The pipe is inserted by pressing shift and the button over enter. So over the keyboards, just above the enter key, there is this symbols command is there. This is known as pipe. So we press that and we select the ligand by pressing 11. Later on, we would use Q to quit. Now our index file is made. GrowMPP module is used to run the MD simulations, the minimizations. Whenever we would prompt GrowMPP, this would be used to do minimizations. Here, the minimization that we are doing is NVT. NVT refers to constancy of the number of particles, the volume, and the temperature. MDP means molecular dynamics parameter. And the parameters will be given by topol.top file, and the output will be nvt.tpr file. It is a very fast command. It executes within a minute. But the next one is, it takes a lot of time. What are we doing? MD-run will do the minimization step. Minus V prompted. This will display the output over the screen or not, whether we choose to display the output over the screen or not. NT, again, it refers to the choice of the number of processors that we are available. I already mentioned that I am demonstrating this on my laptop, so I would be choosing 4 just for the demonstration purposes. And I would stop the simulation in the middle because I have already prepared the results in another folder. So I would switch after this command to that folder. So let's see how this command operates. So we can see that it is operating over 25,000 steps for 50 picoseconds. However, due to lack of computational efficiency, the steps have not yet been done. So we would stop the command and we would move. The next is, again, we have chosen the module GrowMPP. This again, as I mentioned, that it is used for minimization steps. It is used to perform minimizations. This time we have chosen to do minimization on NPT. NPT refers to number of particles, the pressure, the temperature. MDP refers to molecular dynamics parameter. It will generate a GRO file, a CPT file, the parameters it will read from topol.top file, and at the towards the end it will generate npt.tpr file. Now let's see how this command works. Okay. Can somebody tell why did we get this error? Is there anybody? If they are following. Is there anyone following? Can they tell what is the possibility that what is the possible error that we would have got here?
Sir, it is showing that nvt.gro doesn't exist. It means the file is not there. The executed file is not there in the folder.
Yeah. And why did this happen?
Because the previous command was not properly completed at your desktop right now.
Yes, yes, very nice, very nice. So, as what is your name, please? I would request to all the participants to kindly first give their names.
I'm Anamika Shukla from BBAU.
Okay, Anamika. As Anamika mentioned that since the previous command was not executed properly, so this step is showing a error. Now let's try to make sure since in the previous command I already said that it will take a lot of time and computation, and I'm demonstrating this over my laptop. So let's transfer the files and then get back to the simulations. Now let's check again whether this command works in this or not. See, so as Anamika mentioned that since in the previous step, the command was not executed successfully because I had cancelled the command because of the computation issues. So since the files are already prepared in this folder, so we can see that GromMPP calls for the minimization steps. What minimization? NPT minimization. N refers to the number of particles. P stands for the pressure. T stands for temperature. MDP is the molecular dynamics parameters. And the output that is generated through this is npt.tpr. Again, we need to run the minimizations. That can be done by using mdrun command. I have already mentioned that -v refers to visualization, NT refers to the number of processors available, and NPT is for the NPT, number of particles, pressure, and temperature minimization. So we would do this. I would again interrupt this because it will take around half an hour for execution. Let's see how much time it is prompting. So 1839, that means 640. So around half an hour it will take at current number of processors. Since only these many processors are available in my laptop, so we would again break this command and we would switch to the other folder in which this command has already been completed. Now let us see how the production MD occurs. This command gives us a brief idea about the production MD simulation. Here we have used a 20 nanosecond MD. Let me first of all show you a md.mdp file. In this file, we can see the title is DNA ligand complex MD simulation. The parameters are leapfrog integrator. I would also like to mention the participants that at whatever point they have a doubt or confusion, they can either write to us or they can directly write in the chat box, or they can introduce themselves in the middle of the conversation and ask their doubts directly. The most crucial step while doing a MD simulation is the steps. This line, the highlighted line, gives us an idea about as to how many steps are required to perform the MD simulation. So currently the MD simulation that we are demonstration is going on is for 20 nanoseconds. If somebody wants to reduce or increase, they can alter these lines by increasing or decreasing. Suppose if I want to decrease, I would decrease it by multiples of 2 also. So 20 nanoseconds, currently it is there. The frame output is 0.002, any 2 frames per second we are taking out of it. The bond parameters are mentioned. The cutoff scheme, these are the crucial points that we usually mention in our literature. The cutoff scheme that we mention is the Verlet cutoff algorithm. Particle mesh evolved we use for long range interaction. Then we use Brensden thermostat. All these are very crucial things. What we are using is Parinello-Rahman for pressure coupling.
Hello, sir.
Yeah.
Sir, I want to ask if we want to change the time, suppose I want to do for 50 nanoseconds,
Yeah.
what should I do?
Okay. Who is this?
Anamika Shukla from
Okay.
BBAU.
Okay. So I would like to mention that in this steps, in this line, we have to increase the number of steps. So we can see that for 20 nanoseconds, how many count is there? Can you count? Can you see and count how many steps are mentioned here? How many? What is the digit here?
Around 10 lakhs.
Yeah. It is 1 crore. Okay, 1 and then
crore, okay.
7 zeros. Okay. So for 20 nanoseconds, we have this much. So for 1 nanosecond, you can use unitary method. It's a very basic, class 5 or class 6 calculation is there. So what? So accordingly,
in
you can
which
calculate
file we
for
have
1
to
nanosecond
make these changes?
in the md.mdp file.
Okay, so we need not change, we need not modify other files for this.
No. If those files, that corresponding minimization would be done in those, minimization steps. If you let me demonstrate, let me show you vinvt.mdp. See, if you want to increase, we have opened the NVT equilibration file. Okay. So if you want to increase the equilibration, the NVT, the volume and temperature and particle equilibration for more than 50 picosecond, you can change it. So it all depends, as I mentioned in the very beginning, that it depends upon the user as to for how much time they want to do their equilibration. Standardly for DNA ligand system, this much time is sufficient. But if somebody is trying to do some longer simulation, like suppose for 1000 nanosecond or 500 nanosecond, they can alter this information and see as to what is the deviation that it is being offered. So for production MD, and only md.mdp file is to be altered depending upon what is the length of the simulation you want to perform. So currently it is for 20 nanosecond. If you wish, you can increase it for 50 nanoseconds or 100 nanoseconds, depending upon these multiples and these values. If you want to decrease it, you can decrease it also. So no problem with that. So a slight hint that I would like to give you is that for 20 nanosecond, we have this much, that is twice of 50 lakhs. For 20 nanoseconds, we have twice of 50 lakhs. So for 10 nanoseconds, we would have 1/4 of 50 lakhs. Similarly, for 40 nanoseconds, you can have 4 times of this much. So likewise, you can correlate as to what is the number of steps required for 50 nanosecond or 100 nanosecond. So finally, in the RMSD or RMSF or RG plot, or whatever plot during the analysis, I'll be demonstrating the analysis also just after the complete MD simulation. So that RMSF or RMSD analysis depends upon this line only, this md.mdp file only. Whatever MDP parameters that would be incorporating in this file, that only will be displayed in the final results. However, as I already mentioned, if somebody wants to see their NVT or NPT equilibration for longer durations, they are supposed to change the files according to their needs. Also, I would like to mention that if somebody wants some other cutoff scheme, a lot of cutoff schemes are available apart from Verlet. If somebody wants some other sort of pressure coupling apart from Parallel-Rahman or anything else, they can incorporate it. So it is purely user dependent as to what sort of parameters they want to incorporate in their file, or it also depends upon to what kind of study the user is trying to perform. So let's execute the production MD command and see what result do we get. Prompted very shortly, as I have already mentioned, the longest simulation time that would take is this one. Since this is the production simulation, so it will take a lot of time in the mentioned number of cores and processors available. So let's see how much time it is offering. All the commands, they have similar interpretation and similar explanation. Let's see. We can see, as I already mentioned in the MDP file, that this many number of steps and this many picoseconds. So 20,000 picosecond means 20 nanoseconds. So this simulation is going for 20 nanoseconds. We will wait for 1 or 2 seconds more probably, and it will display as to how much time. See. So prompted that the simulation at this rate, the rate is for using at 4 MP threads and 4 processors, it will take around 2 February to complete, like 26 January to complete the simulation. So it is a very open source program, depending upon the user choice as to what parameter the user wants to incorporate. It is very easy to use at the same time. Also, there are programs like OpenMPI. You can install it and you can couple your Gromacs with OpenMPI, and in that case, you can use all your processors. So it is very, very easy to use this. Also, as I have shown, that the number of processors can also be altered from the single. The number of processors can also be altered using this, whether or 8 or 16 or 32 or whatever be the number of cores or processor, depending upon the availability of computation at your institute, respected institute, you can use it. Now, since this highlighted command was the last command for our production simulation, so assuming that our simulation is done, now let's move on to the analysis of ND results and see what analysis we can perform. So for analysis, the very first command is GMX, calling the Gromacs function, Gromacs software. trjcon is this prompts us to converge the entire trajectory to a minimum. Like if something is scattered or it's not up to the line or up to the desired value or parameter, it will try to converge it. So let's see what it prompts and what option we have to choose, and accordingly we will be explaining. Okay, so it has prompted us to choose from these following options, whether system or DNA or ligand or whatever we want to choose. So what do we need to choose is system. We have to converge our entire system. Since the simulation is for 20 nanoseconds, so this calculation would lead up to 20,000 picoseconds, 2000 picoseconds, beg your pardon. And then we would move on to see as to what output it generates. It would generate a MD0 to no PBC.xtc. XTC refers to converged trajectory. Gromacs trajectory is converged now. We can visualize this GMX XTC file using VMD. So since we have already done this step, I would like to omit it and move on to next command. In the similar manner, this command also converges our trajectory, but now not for the previous one. Previously we have generated the XTC file. Now it will check whether the XTC file is properly converged or not. If it is converged properly, it is fine. If it is not, it would try to converge. So let's see what it prompts and what are the options that we have to choose in order to converge the trajectory obtained. This time we have a DNA ligand system, so we would choose the 14th group, that is DNA ligand, which has 801 number of elements to it. Since it will read all the possible frames, the frames here would be around 2000 because of the 20 nanosecond simulation. So 2000 frames would be generated. Let's see if 2000 frames would be generated. I think it didn't generate. So as I already mentioned that I have completed all the simulation and mailed you the results. So we would not wait for the commands to complete because of the lack of computational facilities over here at my laptop, because of my laptop. Next, this is a very crucial step in obtaining the RMSD. GMX is calling the Gromacs. RMS is for obtaining RMSD plot. Here the RMSD is obtained using XVG format. XVG refers to vector graphics data. RMSD we would use one because already I have done the RMSD evaluation and RMSD.xvg file is already present. So I would draw the output to be RMSD1 so as to not let the computer confuse. See, we have already used the RMSD also and RMSD1 also. So this time we will choose another, and that is RMSD2. Let's label this output to be 2. Why are we choosing all these labelings? So as to not replace the previously calculated files. So let's see what does it prompt. It has again prompted us to choose between DNA and ligand. So this time we would choose 1 to be our DNA and 11 to be our ligand, because the DNA ligand system's RMSD is to be calculated. The result that it would be generated is RMSD.2.xvg. Now let's see if this file is generated or not. RMSD2.xvg is generated, we can see. So in the similar manner, we can now plot RMSF. RMSF function calls for this function calls to plot the RMSF values for all the 20 nanosecond calculation, and at towards the end, since we have already one RMSF1 file already generated, so this time we will label our output file to be RMSF.2.xvg. Now let's see what result does it produce. We have to choose between again, like the previous ones, DNA, ligand, sodium, and lot of other options are there. But since we are simulating DNA ligand system, so we would choose 14. Now what we would do is we would try to bring out the hydrogen bond information. Hydrogen bond is called by another function named as H bond. It will read the 20 nanosecond XTC converged file, and it will bring out a file known as hbond2.xvg. Why are we using 2? Like in the previously I have already mentioned that H bond and H bond 1 has already been done. So let's not overwrite the previously calculated files, and let's see what does it produce. It will again prompt us for results, and we have to choose 1 for DNA and 11 for ligand. So it will calculate the hydrogen bonds formed between the DNA and ligand. That can be later visualized using any plotting tool. The plotting tool that we'll be using today is XMGrace. I'll be demonstrating after this introduction over MD that how to plot graphs, that is RMSD, RMSF, hydrogen bonding, energy, and radius of gyration plots using XMGrace. So let's see. First of all, let's bring out all the information out of the file, and then we would move on to the analysis session. So right now we are doing analysis, but we'll be plotting. This current one is gyrate. Gyrate calculates the radius of gyration. So we know that every biological macromolecule has alphas and beta sheets and alpha helices, and it has twists and turns depending upon what sort of conformation, whether ADNA, BDNA, or ZDNA, or what is the nature of protein that we are using. So in order to calculate the radius of gyration, that is from the standard value, how much deviation has occurred over the period of the simulation because of the presence of the ligand bound to the DNA or maybe protein or any other biological macromolecule. So in order to calculate the variation in the radius of gyration, we use this gyrate command. Gyrate command, what it does, it takes the 20 nanosecond simulation trajectory converged file, and it reads the index file and generates the output file known as gyrate2.xvg. 2 we have added here in order to differentiate between previously generated gyration files and this current gyration file. So it will prompt us to choose between DNA ligand water and ions and everything else mentioned. Since we are choosing the DNA ligand system for MD simulation, so we would use 14 for the calculation of radius of gyration. And the last analysis that we need to do is energy. It is a very crucial command. I would request all the participants to kindly follow through it with this. Let's first of all execute this and see what information it produces. Okay, so I have reviewed a few manuscripts. I have also submitted a few manuscripts to various journals, and the reviewers have asked a common question that energy should have been mentioned, or I would have also queried upon the people that to mention the energy values. So it is a very crucial piece of information as to what are the different sort of energy contribution terms and parameters that are incorporated while MD simulation. In order to calculate this, you can use this file, this command gmx energy for the entire 20 nanosecond, and it will generate an output known as ener.xvg. It can be plotted also using xmgrace. However, if we see this long list, so what we need to do is we need to select whatever energy configuration. Suppose I want to see potential energy out of it. So potential lies on the option 11. So I would simply press 11 here. I would press enter twice and it will calculate the potential energy for 20 nanoseconds simulation. The potential energy is mentioned over here. If somebody is interested in something other, suppose somebody is interested in proper or improper dihedral or angle or Coulomb contribution or volume or density or PV or enthalpy. Suppose we want to do for enthalpy now. So I mentioned 24, press the enter twice and I would get the enthalpy contribution in kilojoules per mole. So in order to make sure that we get all the possible important information, what one can do is they can bring out all out of it, and later on whatever information is required they can keep it and the rest they can discard. So that can be done by simply choosing all the options. Let's see. So we can see that all the options have now been listed on the terminal. The angular contribution, the proper dihedral, the improper dihedral, the Lennard-Jones, the Coulomb, the dispersion correlation, potential energy, kinetic energy, total energy, temperature, pressure, the box dimension, the volume, the density, enthalpy, everything is mentioned. Even the DNA and Lennard-Jones parameter for DNA, the DNA ligand system and the ligand system, everything is mentioned here. So whatever the user needs, they can bring the information out of it and they can use that in the manuscript, whatever they are interested in. Now let us try to make plots. Since all the possible analysis have been done, basics ones, energy, the gyration, the hydrogen bonding, RMSF, RMSD. Now let us try to use XMGrace in plotting the data obtained. For all those who are using Ubuntu, XMGrace can be easily installed by simply typing sudo apt get install XMGrace, or simply you may type grace also, that would also work. Since I have already installed it, so I just need to use it. XMGrace. Now let's see the list of files first of all. So we would start by first of all printing the gyration. Let's see how does gyration plot looks like. See, is the slide visible to everybody? Can somebody confirm amongst the audience?
Yes, sir.
So XMGrace, what we did, we just simply wrote a command, that is XMGrace and the file name. If somebody has more than one file of the similar kind, they can plot all the files simultaneously. Like suppose Suppose I have more than one file of the similar kind. So I can write at likewise, you can plot all the files at once, but since all the files have same information at the same place, so it won't be relevant, to plot the same files every time. So what we need to do is this. This is the radius of gyration plot obtained. One can now save the file by simply taking a screenshot and saving it in paint format. So let's try. And likewise, we can see we have the now radius of gyration plot for our DNA ligand system. Now let us try to plot energy XVG file. If we would have had more than one DNA ligand system or one DNA with many ligands, we would have plotted all the graphs simultaneously over here only. But since we have only one system, so likewise we can now obtain the DNA ligand energy variation curves and graphs, and variation can be seen for entire 20 nanoseconds. As I already mentioned that this 20 nanosecond will be displayed in the analysis part, that in the md.mdp file we can control as to how much time our simulation would go on. So as I have already mentioned, so this is already the same thing that is displayed over here. Now let us try to visualize the RMSD. The RMSD plot can be visualized like this. Again, for the 20 nanoseconds, the RMSD is given as follows. I have one more very interesting information to share with you people. Suppose if somebody wants to change the title or subtitle, so they can open the XVG file in VI editor and see there is a line at the 13th line. There is mentioned RMSD title, RMSD. You can also include your own title like RMSD for DNA ligand system. Likewise, the time is mentioned in picosystem. Since the scaling has been done in picosystem, it's not required. RMSD is in nanometer. Type is XY type of graph is there. Subtitle, if somebody wants to include subtitle, they can keep it. If somebody doesn't want to include, you can simply comment it by putting hash. Once you hash it, it will be commented and not displayed in the actual file. If you want to make it ligand one, you can edit it and make it ligand, or you can keep it like molecule or anything like that. So as I have said that if there are multiple files we are plotting, like suppose if I would have had 4 ligands or 4 molecules simultaneously whose RMSD if I want to plot, I can do it like this. The legend S0 is for the first one. The legend S1 is for the second one. Similarly, more and more. If suppose you have 10, so Y you can copy and paste. 5 times you can paste it, or you can undo it. As many number of ligands you can include or exclude depending upon your nature. So let's undo all the changes. MSD for DNA ligand system. Again, let's visualize it. See. So whatever you want to do or not, you can already visualize it. We made a change in RMSD1 and we plotted RMSD. So that's why the changes were not visible. RMSD for DNA ligand system, uncommented this one, RMSD and time. Molecule instead of ligand, ligand instead of molecule, it makes no difference. So whatever, if you want, suppose we can see that in this current graph, this position is not clear. So we can change the position also. Okay, there is no label to change the position. The visualization of the graph, so it's not considered good. However, we can put it here or any place anywhere else in the blank space. I would send you people the link, or rather I will send you people the entire new file so as to how to change the legend inside the XM Grace file. Now let us try to visualize the RMSF. So likewise, we can visualize the RMSF plot also. It gives us the position of the atom. So around towards the end, we have the ligand, and this is so okay, very good plot we have. Suppose I want to write RMSF here, and I don't want to write fluctuation. I want to write RMSF. Now let's edit the RMSF file. As per our requirement. So in the title, I want to write RMSF. I don't want to write fluctuation. I did that editing. And in the label, I want to write nanometer for RM. Instead of RMSF, I want to write here fluctuation. Fluctuation in nanometer, atom. For the labeling around the label of the atoms, type is XY. So now let's see what is the difference between the previous graph and current graph. See, fluctuation in nanometers instead of fluctuation, RMS fluctuation, we now have RMSF. So like this, you can control the content that is to be displayed in the graph. Whether or not you want to include any information, you can do it. If you don't want to include any information, you can exclude it. Now let us try to plot hydrogen bonds. So we now have hydrogen bonds information, the number along the y-axis and the time in the picosecond along x-axis, and the legend is displaying for the hydrogen bonds. Now let us see the structure of the XVG file and see what changes we can make inside it so as to make it look better. So instead of in the y-axis, instead of writing number, I want to write number of H bonds. I have changed that. Okay, so we can see that a view thing is there. This view refers to as the coordinate of the legend box. Let's see the graph, and then we will come back and edit this view thing and see what how the position of the box changes. I don't want to see this, so I would comment this. I don't want to see this, I would comment this also. If I want to see, I can uncomment it. So let's first of all see the legend box, and let's now try to alter the position of this legend box in order to make sure that whether how we can make our graph look better. Here we have several options, like this view thing is there, then we have the legend thing, then length. So let's first of all begin with the length. I want to make sure that it is written in even smaller fonts. So I will put it 1. Let's see what is the change. See, it is gotten smaller. If somebody might not be able to see because it could not be that 1 or 2 differences cannot be observed. So let's make it bigger rather at this time so as to make sure that clearly we can see whether the thing has been done or not. So let's make it 5 or maybe 10. Let's see. See. So this has been increased to from 2 to 1 to 10. So it is very easy. Why it is required? Because suppose we have simultaneously 5 or 4 hydrogen bonding information and very thin lines is to be drawn here, so we can control the thickness and length of this line in order to differentiate between the different number of lines is present. If more than 1 is present over here, it will be displayed according to the different colors. Let's try to see if we can plot same graph multiple number of times or not. I would change a few coordinates just in order to make sure that we have a different data set. If we do not create a different data set, the graph would be overlapping and we would not get any relevant. So it is just for the sake of the users that we are making a different data set. Now we have H bond 1 and H bond. See how Grace plots them. Okay, can someone tell, since the data sets are same, so as I already said that if we have same files with same data set, only one graph will be generated. So I don't think it is very effective for plotting similar files because of the similar nature of the files. If we would have had multiple files, it can be plotted like this. And in case like this, see earlier the graph was something in red, now the graph is in black. If you have more information like H bond for third or fourth or maybe some fifth conformation, the color there will be multiple colors, and out of this you can identify whether it is for molecule 1 or molecule 2 or system 1 or system 2. So likewise you can plot multiple graphs on XM Grace and they would be easily differentiated using colors. And of course the legends over here mentioned would tell the user that as to what color refers to what system. Let us now try to plot. I think we have plotted everything. Can somebody follow? Can we how many graphs did we plot? Can somebody tell me? 5, you know. And let's check if we generated 5. So we generated RMSD, we generated RMSF, we generated hydrogen bond, gyration and energy, and we plotted all of them. So in this way, your analysis is there.
So if anyone have any question, they are welcome to ask.
Yes, please. If you have any doubt regarding MD or like plotting the graph or anything like that.
Creating the input file, extracting the data from output file. I think you need Python script for that. So he has already explained.
Yes.
And whatever doubt you have, you should interact. Anyone have any question till now?
Hello, sir.
Yeah, go ahead.
This is Nidhi here. Sir, I had
You
this doubt.
turn on your video, Nidhi.
Sure, sir. So, sir, I had this doubt. You had typed some command and there were enthalpy, potential and various other parameters that were shown. So if these parameters we want to save, like how do we save that then? Like the data which you generated at that time.
Okay. Let's first of all get to the command and then so what's your name?
Nidhi.
Sir Nidhi.
Okay. So I think we use this command, the highlighted one. Do you remember?
Yes, yes, sir.
Okay. So we use this command and the output was, let's not use this folder because it's already properly. So we could use this flag, okay? We could use this sign and say if I write summary.txt, it would prompt for all the option, and I'm pretty sure that it will save all those to that summary file. Yes. Now let's visualize that summary file. See. So did you get?
Yes, sir.
Is it clear?
Yes, sir. Yes. Thank you.
I can't hear you. Is it clear?
Yes, sir. It is clear.
Okay.
Anyone else have any questions?
No problem.
Anyone else have any question? Then they are welcome to ask.
Otherwise, we can move on to Autodoc and data analysis with Autodoc and all that stuff.
Anvesh, I think we do not have enough time for Autodoc. It's already going to be 7. So for Autodoc, we will see in the coming days. If any day we will be having some time, we will do Autodoc and data analysis.
No problem. No problem.
So yeah, now I think we can. If no questions are there, Suyash, you are there. You said you want to ask some question, but I don't know. You are having some technical difficulty or what?
I think he's having some.
Sir, I had one more doubt, but I think I have forgotten what command you had used. I'll contact you after, like, I go back and.
No problem.
You can write an email
Yes.
to him with a copy to MMTT-2021.
All the participants have already been sent all the files, the simulated, the doctor results also, the MD simulation results also, with all the analysis, all the graphs have been provided to them in the XVG files. Okay. Commands have already been sent. If somebody doesn't have Gromacs, the list of commands to download Gromacs have already been sent. Apart from this, if anyone has any problem regarding at any step, any analysis, anything like that, you can contact us directly. You can write a mail, you can WhatsApp. There is no problem with that. Okay, we'll directly follow you up with that.
So, sir, I had already Pymol on my laptop. So when you had sent some Gromacs structure to us also. So like, what do we do of that? Like, I had already Pymol, so when I was opening it, it directly opened onto Pymol. I don't know why. So why did that happen? Like, you have sent some Gromacs structure to us.
I would suggest you. Yeah, sir is saying something.
No, sir. I was only speaking.
I would suggest you to use VMD for post MD analysis, for taking snapshots. And I don't know why your files were linked to Pymol. Maybe that default extension or maybe something like that you would have provided.
Right click on those file. What is her name? Nidhi, right?
Yes, sir.
So right click and then open with whatever program you want to use, because you have and if you want to change that, you click on properties and change it. You can change permanently to be opened by VMD and not by Pymol. Whatever you want, you can do it by properties. Okay. Yeah.
Thanks.
Anyone else have any question? Okay, then. So thank you, Anvesh. It was very informative, and I am sure it is really helpful for all the participants, whoever is seeing it at different places, YouTube and Microsoft Teams, and also in the interaction sessions. It will be available on the YouTube in future also. So whoever want, they can come and then see the video, and whenever it is required, they can contact us and they can contact you. So thank you so much, and see you in the next session sometimes for Autodoc.
Thank you so much, sir. Have a good night, sir.
Okay, thank you. So this will be the end of day 3 program. Tomorrow morning we will be having 2 talks, one by Professor Devesh Kumar and another by Professor Priyadarshi Satpathy. One is from Central University Lucknow and one is from IIT Guwahati. After a 15 minutes break, we will be having a talk by Professor Sandeep Pal from IIT Guwahati, and then there will be one very interesting talk by Professor Etienne Derat, who will be giving also hands-on session. And then after Etienne Derat's talk, there will be a talk by Dr. Farhan Ahmed Pasha from Saudi Arabia, and Dr. Thomas Steinrich from Germany, from Schrodinger. So tomorrow also we will be having a packed day. I hope that you are all ready for hands-on session by Professor Etienne Derat. He will be doing it from 2:15 p.m. for around 3 hours after his talk. So good night and have a good day. I hope that this day was useful for all of you. Thank you.